How'd you go? Did you give it a shot? Did you try replicating the train step and the test step function? I hope you did. Otherwise, let's do that in this video, but this time we're going to do it for our custom data sets. And what you'll find is not much, if anything, changes because we've created our train and test loop functions in such a way that they're generic. So we want to create a train step function, and by generic I mean they can be used with almost any model and data loader. So train step takes in a model and data loader and trains the model on the data loader. And we also want to create another function called test step, which takes in a model and a data loader and other things and evaluates the model on the data loader. And of course, for the train step and for the test step, each of them respectively are going to take a training data loader. Oh, I just might make this a third heading so that our outline looks nice and beautiful. Section 7 is turning out to be quite a big section. Of course, we want them to be respectively take in their own data loader. So train takes in the train data loader, test takes in the test data loader. Without any further ado, let's create the train step function. Now we've seen this one in the computer vision section. So let's see what we can make here. So we need a train step, which is going to take in a model, which will be a torch nn.module. And we want it also to take in a data loader, which will be a torch.utils.data loader. And then it's going to take in a loss function, which is going to be a torch nn.module as well. And then it's going to take in an optimizer, which is going to be torch optim.optimizer. Wonderful. And then what do we do? What's the first thing that we do in a training step? Well, we put the model in train mode. So let's go model.train. Then what should we do next? Well, let's set up some evaluation metrics, one of them being loss and one of them being accuracy. So set up train loss and train accuracy values. And we're going to accumulate these per batch because we're working with batches. So we've got train loss and train acc equals 0, 0. Now we can loop through our data loader. So let's write loop through data loader, and we'll loop through each of the batches in this because we've batchified our data loader. So for batch xy in enumerate data loader, we want to send the data to the target device. So we could even put that device parameter up here. Device equals device. We'll set that to device by default. And then we can go x, y equals x.toDevice and y.toDevice. Beautiful. And now what do we do? Well, remember the PyTorch, the unofficial PyTorch optimization song? We do the forward pass. So ypred equals model on x. And then number 2 is we calculate the loss. So calculate the loss. Let's go loss equals loss function, and we're going to pass it in ypred y. We've done this a few times now, so that's why we're doing it a little bit faster. So I hope you notice that the things that we've covered before, I'm stepping up the pace a bit. So it might be a bit of a challenge, but that's all right. You can handle it. And then, so that's accumulating the loss. So we're starting from 0 up here, and then each batch we're doing a forward pass, calculating the loss, and then adding it to the overall train loss. And so we're going to optimize a 0 grad, so 0 the gradients of the optimizer for each new batch. And then we're going to perform back propagation. So loss backwards, and then 5, what do we do? Optimize a step, step, step. Wonderful, look at that. Look at us coding a train loop in a minute or so. Now let's calculate the accuracy and accumulate it. Calculate the... You notice that we don't have an accuracy function here. That's because accuracy is quite a straightforward metric to calculate. So we'll first get the ypred class because this is going to output model logits. as we've seen before, the raw output of a model is logits. So to get the class, we're going to take the argmax torch.softmax, so we'll get the prediction probabilities of ypred, which is the raw logits, what we've got up here, across dimension 1, and then also across dimension 1 here. Beautiful. So that should give us the labels, and then we can find out if this is wrong by checking it later on. And then we're going to create the accuracy by taking the ypred class, checking for equality with the right labels. So this is going to give us how many of these values equal true, and we want to take the sum of that, take the item of that, which is just a single integer, and then we want to divide it by the length of ypred. So we're just getting the total number that are right and dividing it by the length of samples. So that's the formula for accuracy. Now we can come down here outside of the batch loop. We know that because we've got this helpful line drawn here. And we can go adjust metrics to get the average loss and accuracy per batch. So we're going to set train loss is equal to train loss divided by the length of the data loader, so the number of batches in total, and the train accuracy is the train acc divided by the length of the data loader as well. So that's going to give us the average loss and average accuracy per epoch across all batches. So train acc. Now that's a pretty good looking function to me for a train step. Do you want to take on the test step? So pause the video, give it a shot, and you'll get great inspiration from this notebook here. Otherwise, we're going to do it together in 3, 2, 1. Let's do the test step. So create a test step function. So we want to be able to call these functions in an epoch loop. And that way, instead of writing out training and test code for multiple different models, we just write it out once and we can call those functions. So let's create def test step. We're going to do model, which is going to be, if I could type, torch nn module. And then we're going to do data loader, which is torch utils.data.data loader. Capital L there. And then we're going to just pass in a loss function here because we don't need an optimizer for the test function. We're not trying to optimize anything. We're just trying to evaluate how our model did on the training data set. And let's put in the device here. Why not? That way we can change the device if we need to. So put model in eval mode because we're going to be evaluating or we're going to be testing. Then we can set up test loss and test accuracy values. So test loss and test acc. We're going to make these 0. We're going to accumulate them per batch. But before we go through the batch, let's turn on inference mode. So this is behind the scenes going to take care of a lot of PyTorch functionality that we don't need. That's very helpful during training, such as tracking gradients, but during testing, we don't need that. So loop through data loader or data batches, and we're going to go for batch x, y in enumerate data loader. You'll notice that above we didn't actually use this batch term here, and we probably won't use it here either, but I just like to go through and have that there in case we wanted to use it anyway. So send data to the target device. So we're going to go x, y equals x.to device, and same with y.to device. Beautiful. And then what do we do for an evaluation step or a test step? Well, of course, we do the forward pass. Forward pass, and we're going to, let's call these test pred logits and get the raw outputs of our model. And then we can calculate the loss on those raw outputs. Calculate the loss. We'll get the loss is equal to loss function on test pred logits versus y. And then we're going to accumulate the loss. So test loss plus equals loss.item. Remember, item just gets a single integer from whatever term you call it on. And then we're going to calculate the accuracy. Now we can do this exactly how we've done for the training data set or the training step. So test pred labels, we're going to, I just want to highlight the fact that you actually don't need to take the softmax here. You could just take the argmax directly from this. The reason why we take the softmax, so you could do the same here. You could just directly take the argmax of the logits. The reason why we get the softmax is just for completeness. So if you wanted the prediction probabilities, you could use torch.softmax on the prediction logits, but it's not 100% necessary to get the same values. And you can test this out yourself. So try this with and without the softmax and see if you get the same results. So we're going to go test accuracy plus equals. Now we'll just create our accuracy calculation on the fly. Test pred labels, we'll check for equality on the Y. And then we'll get the sum of that, we'll get the item of that, and then we'll divide that by the length of the test pred labels. Beautiful. So it's going to give us accuracy per batch. And so now we want to adjust the metrics to get average, loss, and accuracy per batch. So test loss equals test loss divided by length of the data loader. And then we're going to go test acc equals test acc divided by length of the data loader. And then finally, we're going to return the test loss, not lost, and test accuracy. Woohoo! Look at us go. Now, in previous videos, that took us, or in previous sections, that took us a fairly long time, but now we've done it in about 10 minutes or so. So give yourself a pat on the back for all the progress you've been making. But now let's, in the next video, we did this in the computer vision section as well. Did we create a train function? Oh no, we didn't, but we could. So let's create a function to functionize this. We want to train our model. I think we did actually. Def train. We've done so much. I'm not sure what we've done. Oh, okay. So looks like we might not have. But in the next video, give yourself this challenge. Create a function called train that combines these two functions and loops through them both with an epoch range. So just like we've done here in the previous notebook, can you functionize this? So just this step here. So you'll need to take in a number of epochs, you'll need to take in a train data loader and a test data loader, a model, a loss function, an optimizer, and maybe a device. And I think you should be pretty on your way to all the steps we need for train. So give that a shot, but in the next video, we're going to create a function that combines train step and test step to train a model. I'll see you there. How'd you go? In the last video, I issued you the challenge to combine our train step function as well as our test step function together in their own function so that we could just call one function that calls both of these and train a model and evaluate it, of course. So let's now do that together. I hope you gave it a shot. That's what it's all about. So we're going to create a train function. Now, the role of this function is going to, as I said, combine train step and test step. Now, we're doing all of this on purpose, right? Because we want to not have to rewrite all of our code all the time. So we want to be functionizing as many things as possible so that we can just import these later on if we wanted to train more models and just leverage the code that we've written before as long as it works. So let's see if it does. We're going to create a train function. I'm going to first import tqdm.auto, because I'd like to get a progress bar while our model is training. There's nothing quite like watching a neural network train. So step number one is we need to create a train function that takes in various model parameters, plus optimizer, plus data loaders, plus a loss function, a whole bunch of different things. So let's create def train, and I'm going to pass in a model here, which is going to be torch nn.module. You'll notice that the inputs of this are going to be quite similar to our train step and test step. I don't actually need that there. So we also want a train data loader for the training data, torch.utils.data.data loader. And we also want a test data loader, which is going to be torch.utils.data data loader. And then we want an optimizer. So the optimizer will only be used with our training data set, but that's okay. We can take it as an input. Optimizer. And then we want a loss function. This will generally be used for both our training and testing step, because that's what we're combining here. Now, since we're working with multi-class classification, I'm going to set our loss function to be a default of nn.crossEntropy loss. Then I'm going to get epochs. I'm going to set 5. We'll train for 5 epochs by default. And then finally, I'm going to set the device equal to the device. So, what do we get wrong here? That's all right, we'll just keep coding. We'll ignore these little red lines. If they stay around, we'll come back to them. So, step number 2. I'm going to create, this is a step you might not have seen, but I'm going to create an empty results dictionary. Now, this is going to help us track our results. Do you recall in a previous notebook, we outputted a model dictionary for how a model went? So, if we look at model 1 results, yeah, we got a dictionary like this. So I'd like to create one of these on the fly, but keep track of the result every epoch. So what was the loss on epoch number 0? What was the accuracy on epoch number 3? So we'll show you how I'll do that. We can use a dictionary and just update that while our model trains. So results, I want to keep track of the train loss. So I'm going to set that equal to an empty list and just append to it. I also want to keep track of the train accuracy. We'll set that as an empty list as well. I also want to keep track of the test loss, and I also want to keep track of the test accuracy. Now, you'll notice over time that what you can track is actually very flexible, and what your functions can do is also very flexible. So this is not the gold standard of doing anything by any means. It's just one way that works. And you'll probably find in the future that you need different functionality, and of course, you can code that out. So let's now loop through our epochs. So for epoch in TQDM, let's create a range of our epochs above. And then we can set the train loss. Have I missed a comma up here somewhere? Type annotation not supported for that type of expression. Okay, that's all right. We'll just leave that there. So we're going to go train loss and train acc. Recall that our train step function that we created in the previous video, train step returns our train loss and train acc. So as I said, I want to keep track of these throughout our training. So I'm going to get them from train step. Then for each epoch in our range of epochs, we're going to pass in our model and perform a training step. So the data loader here is of course going to be the train data loader. The loss function is just going to be the loss function that we pass into the train function. And then the optimizer is going to be the optimizer. And then the device is going to be device. Beautiful, look at that. We just performed a training step in 5 lines of code. So let's keep pushing forward. It's telling us we've got a whole bunch of different things here. Epochs is not defined. Maybe we just have to get rid of this. We can't have the type annotation here. And that'll stop Google Colab getting angry at us. If it does any more, I'm just going to ignore it for now. Epochs. Anyway, we'll leave it at that. We'll find out if there's an error later on. Test loss, you might be able to find it before I do. So test step, we're going to pass in the model. We're going to pass in a data loader. Now this is going to be the test data loader. Woohoo, look at us go. Creating training and test step functions. Loss function, and then we don't need an optimizer. We're just going to pass in the device. And then behind the scenes, both of these functions are going to train and test our model. How cool is that? So, still within the loop, right? This is important. Within the loop, we're going to have number 4 is we're going to print out. Let's print out what's happening. Print out what's happening. We can go print, and we'll do a fancy little print statement here. We'll get the epoch, and then we will get the train loss, which will be equal to the train loss. We'll get that to, let's go 4 decimal places. How about that? And then we'll get the train accuracy, which is going to be the train acc. We'll get that to 4, maybe 3 decimal 4, just so it looks nice, looks aesthetic. And then we'll go test loss. We'll get that coming out here, and we'll pass in the test loss. We'll get that to 4 decimal places as well. And then finally, we'll get the test accuracy. So a fairly long print statement here, but that's all right. We'd like to see how our model's doing while it's training. Beautiful. And so again, still within the epoch, we want to update our results dictionary so that we can keep track of how our model performed over time. So let's pass in results. We want to update the train loss. And so this is going to be this. And then we can append our train loss value. So this is just going to expend the list in here with the train loss value every epoch. And then we'll do the same thing on the train accuracy. Append train acc. And then we'll do the same thing again with test loss. Dot append test loss. And then we will finally do the same thing with the test accuracy. Test accuracy. Now this is a pretty big function, but this is why we write the code now so that we can use it multiple times later on. So return the filled results at the end of the epoch. So outside the epoch's loop. So our loop, we're outside it now. Let's return results. Now, I've probably got an error somewhere here, and you might be able to spot it. Okay, train data loader. Where do we get that invalid syntax? Maybe up here? Oh, we don't have a comma here. Was that the issue the whole time? Wonderful. You might have seen that. I completely missed that. But we now have a train function to train our model. And the train function, of course, is going to call out our train step function and our test step function. So what's left to do? Well, nothing less than train and evaluate model 0. So our model is way back up here. How about in the next video, we leverage our functions, namely just the train function, because it's going to call our train step function and our test step function and train our model. So I'm going to encourage you to give that a go. You're going to have to go back to the workflow maybe, or maybe you already know this. So what have we done? We've got our data ready and we turned it into tensors using a combination of these functions. We've built and picked a model. Well, we've built a model, which is the TinyVGG architecture. Have we created a loss function yet? I don't think we have. Or an optimizer? I don't think we've done that yet. We've definitely built a training loop though. We aren't using torch metrics, we're just using accuracy, but we could use this if we want. We haven't improved through experimentation yet, but we're going to try this later on. And then save and reload the model. We've seen this before. So I think we're up to picking a loss function and an optimizer. So give that a shot. In the next video, we're going to create a loss function and an optimizer, and then leverage the functions we've spent the last 2 videos creating to train our first model, model 0, on our own custom data set. This is super exciting. I'll see you in the next video. Who's ready to train and evaluate model 0? Put your hand up. I definitely am, so let's do it together. We're going to start off section 7.7, and we're going to put in train and evaluate model 0, our baseline model on our custom data set. Now, if we refer back to the PyTorch workflow, I issued you the challenge in the last video to try and create a loss function and an optimizer. I hope you gave that a go, but we've already built a training loop. So we're going to leverage our training loop functions, namely train, train step, and test step. All we need to do now is instantiate a model, choose a loss function and an optimizer, and pass those values to our training function. So let's do that. All right, this is so exciting. Let's set the random seeds. I'm going to set torch manual seed 42 and torch CUDA manual seed 42. Now remember, I just want to highlight something. I read an article the other day about not using random seeds. The reason why we are using random seeds is for educational purposes. So to try and get our numbers on my screen and your screen as close as possible. But in practice, you quite often don't use random seeds all the time. The reason why is because you want your model's performance to be similar regardless of the random seed that you use. So just keep that in mind going forward. We're using random seeds to just exemplify how we can get similar numbers on our page, but ideally, no matter what the random seed was, our models would go in the same direction. That's where we want our models to eventually go. But we're going to train for 5 epochs, and now let's recreate an instance of tinyVGG. We can do so because we've created the tinyVGG class. So tinyVGG, which is our model 0. We don't have to do this, but we're going to do it anyway, just so we've got all the code in one place. TinyVGG, what is our input shape going to be? That is the number of color channels of our target images. And because we're dealing with color images, we have an input shape of 3. Previously, we used an input shape of 1 to deal with grayscale images. I'm going to set hidden units to 10 in line with the CNN Explainer website. And the output shape is going to be the number of classes in our training data set. And then, of course, we're going to send the target model to the target device. So what do we do now? Well, we set up a loss function and an optimizer. Loss function and optimizer. So our loss function is going to be, because we're dealing with multi-class classification, NN cross entropy, if I could spell, cross entropy loss. And then we're going to have an optimizer. This time, how about we mix things up? How about we try the Atom optimizer? Now, of course, the optimizer is one of the hyperparameters that you can set for your model, and a hyperparameter being a value that you can set yourself. So the parameters that we want to optimize are our model 0 parameters, and we're going to set a learning rate of 0.001. Now, recall that you can tweak this learning rate if you like, but I believe, did I just see that the default learning rate of Atom is 0.001? Yeah, there we go. So Atom's default learning rate is 1 to the power of 10 to the negative 3. And so that is the default learning rate for Atom. And as I said, oftentimes different variables in the PyTorch library, such as optimizers, have good default values that work across a wide range of problems. So we're just going to stick with the default. If you want to, you can experiment with different values of this. But now let's start the timer, because we want to time our models. We're going to import from timeIt. We want to get the default timer class, and I'm going to import that as timer, just so we don't have to type out default timer. So the start time is going to be timer. This is going to just put a line in the sand of what the start time is at this particular line of code. It's going to measure that, and then we're going to train model 0. Now, this is using, of course, our train function. So let's write model 0 results. I only wrote model 1, but we're not up to there yet. So let's go train model equals model 0. And this is just the training function that we wrote in a previous video. And the train data is going to be our train data loader. And we've got train data loader simple because we're not using data augmentation for model 1. And then our test data loader is going to be our test data loader simple. And then we're going to set our optimizer, which is equal to the optimizer we just created, the friendly Atom optimizer, and the loss function is going to be the loss function that we just created, which is NN cross entropy loss. Finally, we can send in epochs is going to be num epochs, which is what we set at the start of this video to 5. And of course, we could train our model for longer if we wanted to, but the whole idea of when you first start training a model is to keep your experiments quick. So that's why we're only training for 5. Maybe later on you train for 10, 20, tweak the learning rate, do a whole bunch of different things. But let's go down here, let's end the timer, see how long our model took to train. End the timer and print out how long it took. So in a previous section, we created a helper function for this. We're just going to simplify it in this section, and we're just going to print out how long the training time was. Total training time. Let's go end time minus start time, and then we're going to go we'll take it to 3 decimal places, hey? Seconds. You ready to train our first model, our first convolutional neural network on our own custom data set? On pizza, steak, and sushi images? Let's do it. You ready? 3, 2, 1, no errors. Oh, there we go. Okay. Should this be trained data loader? Did you notice that? What does our train data take as input? Oh, we're not getting a docstring. Oh, there we go. We want train data loader. Data loader, and same with this, I believe. Let's try again. Beautiful. Oh, look at that lovely progress bar. Okay, how's our model is training quite fast. Okay, all right, what do we get? So we get an accuracy on the training data set of about 40%, and we get an accuracy on the test data set of about 50%. Now, what's that telling us? It's telling us that about 50% of the time our model is getting the prediction correct, but we've only got 3 classes. So even if our model was guessing, it would get things right 33% of the time. So even if you just guessed pizza every single time, because we only have 3 classes, if you guessed pizza every single time, you get a baseline accuracy of 33%. So our model isn't doing too much better than our baseline accuracy. Of course, we'd like this number to go higher, and maybe it would if it trained for longer. So I'll let you experiment with that. But if you'd like to see some different methods of improving a model, recall back in section number 02, we had an improving a model section, improving a model. Here we go. So here's some things you might want to try. We can improve a model by adding more layers. So if we come back to our tiny VGG architecture, right up here, we're only using 2 convolutional blocks. Perhaps you wanted to add in a convolutional block 3. You can also add more hidden units. Right now we're using 10 hidden units. You might want to double that and see what happens. Fitting for longer, this is what we just spoke about. So right now we're only fitting for 5 epochs. So if you maybe wanted to try double that again, and then even double that again. Changing the activation functions. So maybe ReLU is not the ideal activation function for our specific use case. Change the learning rate, we've spoken about that before. So right now our learning rate is 0.001 for Atom, which is the default, but perhaps there's a better learning rate out there. And change the loss function. This is probably not, in our case, not going to help too much because cross-entropy loss is a pretty good loss for multi-class classification. But these are some things that you could try, these first 3 especially, you could try quite quickly. You could try doubling the layers, you could try adding more hidden units, and you could try fitting for longer. So I'd give that a shot, but in the next video, we're going to take our Model 0 results, which is a dictionary, or at least it should be, and we're going to plot some loss curves. So this is a good way to inspect how our model is training. Yeah, so we've got some values here. Let's plot these in the next video. I'll see you there. In the last video, we trained our first convolutional neural network on custom data. So you should be very proud of that. That is no small feat to take our own data set of whatever we want and train a PyTorch model on it. However, we did find that it didn't perform as well as we'd like it to. We also highlighted a few different things that we could try to do to improve it. But now let's plot our model's results using a loss curve. So I'm going to write another heading down here. We'll go, I believe we're up to 7.8. So plot the loss curves of model 0. So what is a loss curve? So I'm going to write down here. A loss curve is a way of tracking your model's progress over time. So if we just looked up Google and we looked up loss curves, oh, there's a great guide, by the way. I'm going to link this. But I'd rather, if in doubt, code it out than just look at guides. Yeah, loss curves. So yeah, loss over time. So there's our loss value on the left, and there's, say, steps, which is epochs or batches or something like that. Then we've got a whole bunch of different loss curves over here. Essentially, what we want it to do is go down over time. So that's the ideal loss curve. Well, let's go back down here. And a good guide for different loss curves can be seen here. We're not going to go through that just yet. Let's focus on plotting our own model's loss curves, and we can inspect those. let's get the model keys. Get the model 0 results keys. I'm going to type in model 0 results.keys because it's a dictionary. Let's see if we can write some code to plot these values here. So yeah, over time. So we have one value for train loss, train ACK, test loss, and test ACK for every epoch. And of course, these lists would be longer if we train for more epochs, but how about we create a function called def plot loss curves, which will take in a results dictionary, which is of string and a list of floats. So this just means that our results parameter here is taking in a dictionary that has a string as a key, and it contains a list of floats. That's what this means here. So let's write a docstring plots training curves of a results dictionary. Beautiful. And so we're in the section of our workflow, which is kind of like we're kind of doing something similar to TensorBoard, what it does. I'll let you look into that if you want to, otherwise we're going to see it later on. But we're really evaluating our model here. So let's write some plotting code. We're going to use matplotlib. So we want to get the loss values of the results dictionary. So this is training and test. Let's set loss equal to results train loss. So this is going to be the loss on the training data set. And then we'll create the test loss, which is going to be, we'll index on the results dictionary and get the test loss. Beautiful. Now we'll do the same and we'll get the accuracy. Get the accuracy values of the results dictionary. So training and test. And then we're going to go accuracy equals results. This will be the training accuracy, train ACK, and accuracy, or we'll call this test accuracy actually. Test accuracy equals results test ACK. Now let's create a number of epochs. So we want to figure out how many epochs we did. We can do that by just counting the length of this value here. So figure out how many epochs there were. So we'll set epochs equal to a range because we want to plot it over time. Our model's results over time. That's the whole idea of a loss curve. So we'll just get the length of our results here, and we'll get the range. So now we can set up a plot. Let's go plt.figure, and we'll set the fig size equal to something nice and big because we're going to do 4 plots. We want one for, or maybe 2 plots, one for the loss, one for the accuracy. And then we will go plot the loss. plt.subplot. We're going to create 1 row, 2 columns, and index number 1. We want to put plt.plot, and here's where we're going to plot the training loss. So we'll give that a label of train loss, and then we'll add another plot with epochs and test loss. The label here is going to be test loss, and then we'll add a title, which will be loss. plt, let's put a label on the X, which will be epochs, so we know how many steps we've done. This plot over here, loss curves, it uses steps. I'm going to use epochs. They mean almost the same thing. It depends on what scale you'd like to see your loss curves. We'll get a legend as well so that the labels appear. Now we're going to plot the accuracy. So plt.subplot. Let's go 1, 2, and then index number 2 that this plot's going to be on. plt.plot. I'm going to go epochs, accuracy, and the label here is going to be train accuracy. And then we'll get on the next plot, which is actually going to be on the same plot, we'll put the test accuracy. That way we have the test accuracy and the training accuracy side by side. Test accuracy, same with the train loss and test loss. And then we'll give our plot a title. This plot's going to be accuracy. And then we're going to give it an X label, which is going to be epochs as well. And then finally we'll get the plot legend. A lot of plotting code here, but let's see what this looks like, eh? If we've done it all right, we should be able to pass it in a dictionary just like this and see some nice plots like this. let's give it a go. And I'm going to call plot loss curves, and I'm going to pass in model 0 results. Alrighty then, okay, so that's not too bad. Now, why do I say that? Well, because we're looking here for mainly trends. We haven't trained our model for too long. Quantitatively, we know that our model hasn't performed at the way we'd like it to do. So we would like the accuracy on both the train and test data sets to be higher. And then of course, if the accuracy is going higher, then the loss is going to come down. So the ideal trend for a loss curve is to go down from the top left to the bottom right. In other words, the loss is going down over time. So that's the trend is all right here. So potentially if we train for more epochs, which I'd encourage you to give it a go, our model's loss might get lower. And the accuracy is also trending in the right way. Our accuracy, we want it to go up over time. So if we train for more epochs, these curves may continue to go on. Now, they may not. You never really know, right? You can guess these things, but until you try it, you don't really know. So in the next video, we're going to have a look at some different forms of loss curves. But before we do that, I'd encourage you to go through this guide here, Interpreting Loss Curves. So I feel like if you just search up loss curves, you're going to find Google's guide, or you could just search Interpreting Loss Curves. Because as you'll see, there's many different ways that loss curves can be interpreted. But the ideal trend is for the loss to go down over time and metrics like accuracy to go up over time. So in the next video, let's cover a few different forms of loss curves, such as the ideal loss curve, what it looks like when your model's underfitting, and what it looks like when your model's overfitting. And if you'd like to have a primer on those things, I'd read through this guide here. Don't worry too much if you're not sure what's happening. We're going to cover a bit more about loss curves in the next video. I'll see you there. In the last video, we looked at our model's loss curves and also the accuracy curves. And a loss curve is a way to evaluate a model's performance over time, such as how long it was training for. And as you'll see, if you Google some images of loss curves, you'll see many different types of loss curves. They come in all different shapes and sizes, and there's many different ways to interpret loss curves. So this is Google's testing and debugging and machine learning guide. So I'm going to set this as extra curriculum for this section. So we're up to number 8. Let's have a look at what should an ideal loss curve look like. So we'll just link that in there. Now, loss curve, I'll just rewrite here, is a loss curve is, I'll just make some space. A loss curve is one of the most helpful ways to troubleshoot a model. So the trend of a loss curve, you want it to go down over time, and the trend typically of an evaluation metric like accuracy, you want it to go up over time. So let's go into the keynote, loss curves. So a way to evaluate your model's performance over time. These are 3 of the main different forms of loss curve that you'll face, but again, there's many different types as mentioned in here, interpreting loss curves. Sometimes you get it going all over the place. Sometimes your loss will explode. Sometimes your metrics will be contradictory. Sometimes your testing loss will be higher than your training loss. We'll have a look at what that is. Sometimes your model gets stuck. In other words, the loss doesn't reduce. Let's have a look at some loss curves here in the case of underfitting, overfitting, and just right. So this is the Goldilocks zone. Underfitting is when your model's loss on the training and test data sets could be lower. So in our case, if we go back to our loss curves, of course we want this to be lower, and we want our accuracy to be higher. So from our perspective, it looks like our model is underfitting. And we would probably want to train it for longer, say 10, 20 epochs to see if this trend continues. If it keeps going down, it may stop underfitting. So underfitting is when your loss could be lower. Now, the inverse of underfitting is called overfitting. And so 2 of the biggest problems in machine learning is trying to reduce underfitting, so in other words, make your loss lower, and also reduce overfitting. These are both active areas of research because you always want your model to perform better, but you also want it to perform pretty much the same on the training set as it does the test set. And so overfitting would be when your training loss is lower than your testing loss. And why would this be overfitting? So it means overfitting because your model is essentially learning the training data too well. And that means the loss goes down on the training data set, which is typically a good thing. However, this learning is not reflected in the testing data set. So your model is essentially memorizing patterns in the training data set that don't generalize well to the test data set. So this is where we come to the just right curve, is that we want ideally our training loss to reduce as much as our test loss. And quite often you'll find that the loss is slightly lower on the training set than it is on the test set. And that's just because the model is exposed to the training data and it's never seen the test data before. So it might be a little bit lower on the training data set than on the test data set. So underfitting, the model's loss could be lower. Overfitting, the model is learning the training data too well. Now this would be equivalent to say you were studying for a final exam and you just memorized the course materials, the training set, and when it came time to the final exam, because you'd only memorized the course materials, you couldn't adapt those skills to questions you hadn't seen before. So the final exam would be the test set. So that's overfitting. The train loss is lower than the test loss. And just right, ideally, you probably won't see loss curves this exact smooth. I mean, they might be a little bit jumpy. Ideally, your training loss and test loss go down at a similar rate. And of course, there's more combinations of these. If you'd like to see them, check out the Google's loss curve guide that you can check that up there. That's some extra curriculum. Now, you probably want to know, how do you deal with underfitting and overfitting? Let's look at a few ways. We'll start with overfitting. So we want to reduce overfitting. In other words, we want our model to perform just as well on the training data set as it does on the test data set. So one of the best ways to reduce overfitting is to get more data. So this means that our training data set will be larger, our model will be exposed to more examples, and will thus, in theory, it doesn't always work. These all come with a caveat, right? They don't always work, as with many things in machine learning. So get more data. Give your model more chance to learn patterns, generalizable patterns in a data set. You can use data augmentation, so make your model's training data set harder to learn. So we've seen a few examples of data augmentation. You can get better data, so not only more data, perhaps the data that you're using the quality isn't that good. So if you enhance the quality of your data set, your model may be able to learn better, more generalizable patterns and in turn reduce overfitting. Use transfer learning. So we're going to cover this in a later section of the course, but transfer learning is taking one model's that works, taking its patterns that it's learned and applying it to your own data set. So for example, I'll just go into the Torch Vision models library. Many of these models in here, in Torch Vision, the models module, have already been trained on a certain data set, and such as ImageNet, and you can take the weights or the patterns that these models have learned, and if they work well on an ImageNet data set, which is millions of different images, you can adjust those patterns to your own problem. And oftentimes that will help with overfitting. If you're still overfitting, you can try to simplify your model. Usually this means taking away things like extra layers, taking away more hidden units. So say you had 10 layers, you might reduce it to 5 layers. What's the theory behind this? Well, if you simplify your model and take away complexity from your model, you're kind of telling your model, hey, use what you've got, and you're going to have to, because you've only got 5 layers now, you're going to have to make sure that those 5 layers work really well because you've no longer got 10. And the same for hidden units. Say you started with 100 hidden units per layer, you might reduce that to 50 and say, hey, you had 100 before, now use those 50 and make your patterns generalizable. Use learning rate decay. So the learning rate is how much your optimizer updates its or your optimizer updates your model's weights every step. So learning rate decay is to decay the learning rate over time. So you might look this up. You can look this up, go PyTorch learning rate scheduling. So what this means is you want to decrease your learning rate over time. Now I know I'm giving you a lot of different things here, but you've got this keynote as a reference, so you can come across these over time. So learning rate scheduling. So we might look into here. Do we have schedule? Scheduler. Beautiful. So this is going to adjust the learning rate over time. So for example, at the start of when a model is training, you might want a higher learning rate. And then as the model starts to learn patterns more and more and more, you might want to reduce that learning rate over time so that your model doesn't update its patterns too much in later epochs. So that's the concept of learning rate scheduling. The closer you get to convergence, the lower you might want to set your learning rate. Think of it like this. If you're reaching for a coin at the back of a couch, can we get an image of that? Coin at back of couch. Images. So if you're trying to reach a coin in the cushions here, so the closer you get to that coin, at the beginning you might take big steps, but then the closer you get to that coin, the smaller the step you might take to pick that coin out. Because if you take a big step when you're really close to the coin here, the coin might fall down the couch. The same thing with learning rate decay. At the start of your model training, you might take bigger steps as your model works its way down the loss curve. But then you get closer and closer to the ideal position on the loss curve. You might start to lower and lower that learning rate until you get right very close to the end and you can pick up the coin. Or in other words, your model can converge. And then finally, use early stopping. So if we go into an image, is there early stopping here? Early stopping. Loss curves, early stopping. So what this means is that you stop. Yeah, there we go. So there's heaps of different guides. Early stopping with PyTorch, beautiful. So what this means is before your testing error starts to go up, you keep track of your model's testing error, and then you stop your model from training, or you save the weights, or you save the patterns where your model's loss was the lowest. So then you could just set your model to train for an infinite amount of training steps. And as soon as the testing error starts to increase for, say, 10 steps in a row, you go back to this point here and you go, I think that was where our model was the best, and the testing error started to increase after that, so we're going to save that model there instead of the model here. So that's the concept of early stopping. So that's dealing with overfitting. There are other methods to deal with underfitting. So recall, underfitting is when we have a loss that isn't as low as we'd like it to be. Our model is not fitting the data very well, so it's underfitting. So to reduce underfitting, you can add more layers/units to your model. You're trying to increase your model's ability to learn by adding more layers or units. You can again tweak the learning rate. Perhaps your learning rate is too high to begin with and your model doesn't learn very well. So you can adjust the learning rate again, just like we discussed with reaching for that coin at the back of a couch. If your model is still underfitting, you can train for longer. So that means giving your model more opportunities to look at the data. So more epochs, that just means it's got looking at the training set over and over and over and over again and trying to learn those patterns. However, you might find again, if you try to train for too long, your testing error will start to go up. Your model might start overfitting if you train too long. So machine learning is all about a balance between underfitting and overfitting. You want your model to fit quite well. And so this is a great one. So you want your model to start fitting quite well, but then if you try to reduce underfitting too much, you might start to overfit, and then vice versa, right? If you try to reduce overfitting too much, your model might underfit. So this is one of the most fun dances in machine learning, the balance between overfitting and underfitting. Finally, you might use transfer learning. So transfer learning helps with overfitting and underfitting. Recall, transfer learning is using a model's learned patterns from one problem and adjusting them to your own. We're going to see this later on in the course. And then finally, use less regularization. So regularization is holding your model back. So it's trying to prevent overfitting. So if you do too much preventing of overfitting, in other words, regularizing your model, you might end up underfitting. So if we go back, we have a look at the ideal curves. Underfitting, if you try to prevent underfitting too much, so increasing your model's capability to learn, you might end up overfitting. And if you try to prevent overfitting too much, you might end up underfitting. We are going for the just right section. And this is going to be a balance between these two throughout your entire machine learning career. In fact, it's probably the most prevalent area of research is trying to get models not to underfit, but also not to overfit. So keep that in mind. A loss curve is a great way to evaluate your model's performance over time. And a lot of what we do with the loss curves is try to work out whether our model is underfitting or overfitting, and we're trying to get to this just right curve. We might not get exactly there, but we want to keep trying getting as close as we can. So with that being said, let's now build another model in the next video, and we're going to try a method to try and see if we can use data augmentation to prevent our model from overfitting. Although that experiment doesn't sound like the most ideal one we could do right now, because it looks like our model is underfitting. So with your knowledge of what you've just learned in the previous video, how to prevent underfitting, what would you do to increase this model's capability of learning patterns in the training data set? Would you train it for longer? Would you add more layers? Would you add more hidden units? Have a think, and we'll start building another model in the next video. Welcome back. In the last video, we covered the important concept of a loss curve and how it can give us information about whether our model is underfitting. In other words, our model's loss could be lower, or whether it's overfitting. In other words, the training loss is lower than the test loss, or far lower than the validation loss. That's another thing to note here, is that I've put training and test sets here. You could also do this with a validation data set. And that the just right, the Goldilocks zone, is when our training and test loss are quite similar over time. Now, there was a fair bit of information in that last video, so just wanted to highlight that you can get this all in section 04, which is the notebook that we're working on. And then if you come down over here, if we come to section 8, what should an ideal loss curve look like? We've got underfitting, overfitting, just right, how to deal with overfitting. We've got a few options here. We've got how to deal with underfitting, and then we've got a few options there. And then if we wanted to look for more, how to deal with overfitting. You could find a bunch of resources here, and then how to deal with underfitting. You could find a bunch of resources here as well. So that is a very fine line, very fine balance that you're going to experience throughout all of your machine learning career. But it's time now to move on. We're going to move on to creating another model, which is TinyVGG with data augmentation this time. So if we go back to the slide, data augmentation is one way of dealing with overfitting. Now, it's probably not the most ideal experiment that we could take because our model 0, our baseline model, looks like it's underfitting. But data augmentation, as we've seen before, is a way of manipulating images to artificially increase the diversity of your training data set without collecting more data. So we could take our photos of pizza, sushi, and steak and randomly rotate them 30 degrees. And increased diversity forces a model to learn, or hopefully learn. Again, all of these come with a caveat of not always being the silver bullet, to learn more generalizable patterns. Now, I should have spelled generalizable here rather than generalization, but similar thing. Let's go here. Let's create, to start off with, we'll just write down. Now let's try another modeling experiment. So this is in line with our PyTorch workflow, trying a model, then trying another one, and trying another one, so and so over again. This time using the same model as before, but with some slight data augmentation. Oh, maybe we want not slight, that's probably not the best word. We'll just say with some data augmentation. And if we come down here, we're going to write section 9.1. We need to first create a transform with data augmentation. So we've seen what this looks like before. We're going to use the trivial augment data augmentation, create training transform, which is, as we saw in a previous video, what the PyTorch team have recently used to train their state-of-the-art computer vision models. So train transform trivial. This is what I'm going to call my transform. And I'm just going to, from Torch Vision, import transforms. We've done this before. We don't have to re-import it, but I'm going to do it anyway just to show you that we're re-importing or we're using transforms. And we're going to compose a transform here. Recall that transforms help us manipulate our data. So we're going to transform our images into size 64 by 64. Then we're going to set up a trivial augment transforms, just like we did before. Trivial augment wide. And we're going to set the number of magnitude bins here to be 31, which is the default here, which means we'll randomly use some data augmentation on each one of our images, and it will be applied at a magnitude of 0 to 31, also randomly selected. So if we lowered this to 5, the upper bound of intensity of how much that data augmentation is applied to a certain image will be less than if we set it to, say, 31. Now, our final transform here is going to be 2 tensor because we want our images in tensor format for our model. And then I'm going to create a test transform. I'm going to call this simple, which is just going to be transforms.compose. And all that it's going to have, oh, I should put a list here. All that it's going to have, I'll just make some space over here, is going to be transforms. All we want to do is resize the image. Size equals 64, 64. Now, we don't apply data augmentation to the test data set because we only just want to evaluate our models on the test data set. Our models aren't going to be learning any generalizable patterns on the test data set, which is why we focus our data augmentations on the training data set. And I've just readjusted that. I don't want to do that. Beautiful. So we've got a transform ready. Now let's load some data using those transforms. So we'll create train and test data sets and data loaders with data augmentation. So we've done this before. You might want to try it out on your own. So pause the video if you'd like to test it out. Create a data set and a data loader using these transforms here. And recall that our data set is going to be creating a data set from pizza, steak, and sushi for the train and test folders. And that our data loader is going to be batchifying our data set. So let's turn our image folders into data sets. Data sets, beautiful. And I'm going to write here train data augmented, just so we know that it's been augmented. We've got a few of similar variable names throughout this notebook, so I just want to be as clear as possible. And I'm going to use, I'll just re-import Torch Vision data sets. We've seen this before, the image folder. So rather than use our own custom class, we're going to use the existing image folder class that's within Torch Vision datasets. And we have to pass in here a root. So I'll just get the doc string there. Root, which is going to be equal to our train dir, which recall is the path to our training directory. I've got that saved. And then I'm going to pass in here, the transform is going to be train transform trivial. So our training data is going to be augmented thanks to this transform here, and transforms trivial augment wide. You know where you can find more about trivial augment wide, of course, in the PyTorch documentation, or just searching transforms trivial augment wide. And did I spell this wrong? Trivial. Oh, train transform. I spelled that wrong. Of course I did. So test data, let's create this as test data simple equals datasets.image folder. And the root dir is going to be here, the test directory. And the transform is just going to be what? The test transform simple. Beautiful. So now let's turn these data sets into data loaders. So turn our data sets into data loaders. We're going to import OS. I'm going to set the batch size here to equal to 32. The number of workers that are going to load our data loaders, I'm going to set this to os.cpu count. So there'll be 1 worker per CPU on our machine. I'm going to set here the torch manual seed to 42 because we're going to shuffle our training data. Train data loader, I'm going to call this augmented, equals data loader. Now I don't need to re-import this, but I just want to show you again. From torch.utils, you can never have enough practice, right? .data, let's import data loader. So that's where we got the data loader class from. Now let's go train data augmented. We'll pass in that as the data set. And I'll just put in here the parameter name for completeness. That's our data set. And then we want to set the batch size, which is equal to batch size. I'm going to set shuffle equal to true, and I'm going to set num workers equal to num workers. Beautiful. And now let's do that again with the test data loader this time. Test data loader, I'm going to call this test data loader simple. We're not using any data augmentation on the test data set, just turning our images, our test images, into tensors. The data set here is going to be test data simple. I'm going to pass in the batch size equal to batch size, so both our data loaders will have a batch size of 32. I'm going to keep shuffle on false, and num workers I'm going to set to num workers. Look at us go. We've already got a data set and a data loader. This time our data loader is going to be augmented for the training data set, and it's going to be nice and simple for the test data set. So this is really similar, this data loader, to the previous one we made. The only difference in this modeling experiment is that we're going to be adding data augmentation, namely trivial augment wide. So with that being said, we've got a data set, we've got a data loader. In the next video, let's construct and train model 1. In fact, you might want to give that a go. So you can use our tinyVGG class to make model 1, and then you can use our train function to train a new tinyVGG instance with our training data loader augmented and our test data loader simple. So give that a go, and we'll do it together in the next video. I'll see you there. Now that we've got our data sets and data loaders with data augmentation ready, let's now create another model. So 9.3, we're going to construct and train model 1. And this time, I'm just going to write what we're going to be doing. This time we'll be using the same model architecture, but we're changing the data here. Except this time we've augmented the training data. So we'd like to see how this performs compared to a model with no data augmentation. So that was our baseline up here. And that's what you'll generally do with your experiments. You'll start as simple as possible and introduce complexity when required. So create model 1 and send it to the target device, that is, to the target device. And because of our helpful selves previously, we can create a manual seed here, torch.manual seed, and we can create model 1 leveraging the class that we created before. So although we built tinyVGG from scratch in this video, in this section, in subsequent coding sessions, because we've built it from scratch once and we know that it works, we can just recreate it by calling the class and passing in different variables here. So let's get the number of classes that we have in our train data augmented classes, and we're going to send it to device. And then if we inspect model 1, let's have a look. Wonderful. Now let's keep going. We can also leverage our training function that we did. You might have tried this before. So let's now train our model. I'm just going to put here, wonderful. Now we've got a model and data loaders. Let's create, what do we have to do? We have to create a loss function and an optimizer and call upon our train function that we created earlier to train and evaluate our model. Beautiful. So I'm going to set the random seeds, torch.manual seeds, and torch.CUDA, because we're going to be using CUDA. Let's set the manual seed here, 42. I'm going to set the number of epochs. We're going to keep many of the parameters the same. Set the number of epochs, num epochs equals 5. We could, of course, train this model for longer if we really wanted to by increasing the number of epochs. But now let's set up the loss function. So loss fn equals nn cross entropy loss. Don't forget, this just came into mind, loss function often as well in PyTorch is called criterion. So the criterion you're trying to reduce, but I just like to call it loss function. And then we're going to have optimizer. Let's use the same optimizer we used before, torch.optim.atom. Recall, SGD and atom are two of the most popular optimizers. So model1.parameters, they're the parameters we're going to optimize. We're going to set the learning rate to 001, which is the default for the atom optimizer in PyTorch. Then we're going to start the timer. So from timeIt, let's import the default timer as timer. And we'll go start time equals timer. And then let's go train model 1. How can we do this? Well, we're going to get a results dictionary as model 1 results. We're going to call upon our train function. Inside our train function, we'll pass the model parameter as model 1. For the train data loader parameter, we're going to pass in train data loader augmented, so our augmented training data loader. And for the test data loader, we can pass in here test data loader simple. And then we can write our optimizer, which will be the atom optimizer. Our loss function is going to be nn cross entropy loss, what we've created above. And then we can set the number of epochs is going to be equal to num epochs. And then if we really wanted to, we could set the device equal to device, which will be our target device. And now let's end the timer and print out how long it took. End time equals timer, and we'll go print total training time for model 1 is going to be end time minus start time, and it would help if I could spell. We'll get that to 3 decimal places, and that'll be seconds. So you're ready? Look how quickly we built a training pipeline for Model 1. And look how easily we created it. So go us for coding all of that stuff up before. Let's train our second model. Our first model using data augmentation. You ready? 3, 2, 1, let's go. No errors. Beautiful. We're going nice and quick here. So, about just over 7 seconds. So what GPU do I have currently? Just keep this in mind that I'm using Google Colab Pro, so I get preference in terms of allocating a faster GPU. Your model training time may be longer than what I've got, depending on the GPU. It also may be faster, again, depending on the GPU. But we get about 7 seconds, but it looks like our model with data augmentation didn't perform as well as our model without data augmentation. So how long did our model before without data augmentation take to train? Just over 7 seconds as well. But we got better results in terms of accuracy on the training and test data sets for model 0. So maybe data augmentation doesn't help in our case. And we kind of hinted at that because the loss here was already going down. We weren't really overfitting yet. So recall that data augmentation is a way to help with overfitting generally. So maybe that wasn't the best step to try and improve our model. But let's nonetheless keep evaluating our model. In the next video, we're going to plot the loss curves of model 1. So in fact, you might want to give that a go. So we've got a function, plot loss curves, and we've got some results in a dictionary format. So try that out, plot the loss curves, and see what you see. Let's do it together in the next video. I'll see you there. In the last video, we did the really exciting thing of training our first model with data augmentation. But we also saw that quantitatively, it looks like that it didn't give us much improvement. So let's keep evaluating our model here. I'm going to make a section. Recall that one of my favorite ways, or one of the best ways, not just my favorite, to evaluate the performance of a model over time is to plot the loss curves. So a loss curve helps you evaluate your model's performance over time. And it will also give you a great visual representation or a visual way to see if your model is underfitting or overfitting. So let's plot the loss curves of Model 1 results and see what happens. We're using this function we created before. And oh my goodness, is that going in the right direction? It looks like our test loss is going up here. Now, is that where we want it to go? Remember, the ideal direction for a loss curve is to go down over time, because loss is measuring what? It's measuring how wrong our model is. And the accuracy curve looks like it's all over the place as well. I mean, it's going up kind of, but maybe we don't have enough time to measure these things. So an experiment that you could do is train both of our models, Model 0 and Model 1, for more epochs and see if these loss curves flatten out. So I'll pose you the question. Is our model underfitting or overfitting right now? Or both? So if we want to have a look at the loss curves, our just right is for the loss, that is, this is not for accuracy, this is for loss. Over time, we want it to go down. So for me, our model is underfitting because our loss could be lower, but it also looks like it's overfitting as well. So it's not doing a very good job because our test loss is far higher than our training loss. So if we go back to section 4 of the learnpytorch.io book, what should an ideal loss curve look like? I'd like you to start thinking of some ways that we could deal with overfitting of our model. So could we get more data? Could we simplify it? Could we use transfer learning? We're going to see that later on, but you might want to jump ahead and have a look. And if we're dealing with underfitting, what are some other things that we could try with our model? Could we add some more layers, potentially another convolutional block? Could we increase the number of hidden units per layer? So if we've got currently 10 hidden units per layer, maybe you want to increase that to 64 or something like that. Could we train it for longer? That's probably one of the easiest things to try with our current training functions. We could train for 20 epochs. So have a go at this, reference this, try out some experiments with, see if you can get these loss curves more towards the ideal shape. And in the next video, we're going to keep pushing forward. We're going to compare our model results. So we've done 2 experiments. Let's now see them side by side. We've looked at our model results individually, and we know that they could be improved. But a good way to compare all of your experiments is to compare your model's results side by side. So that's what we're going to do in the next video. I'll see you there. Now that we've compared our model's loss curves on their own individually, how about we compare our model results to each other? So let's have a look at comparing our model results. And so I'm going to write a little note here that after evaluating our modeling experiments on their own, it's important to compare them to each other. And there's a few different ways to do this. Number 1 is hard coding. So like we've done, we've written functions, we've written helper functions and whatnot, and manually plotted things. So I'm just going to write in here, this is what we're doing. Then of course there are tools to do this, such as PyTorch plus TensorBoard. And so I'll link to this, PyTorch TensorBoard. We're going to see this in a later section of the course. TensorBoard is a great resource for tracking your experiments. If you'd like to jump forward and have a look at what that is in the PyTorch documentation, I'd encourage you to do so. Then another one of my favorite tools is weights and biases. So these are all going to involve some code as well, but they help out with automatically tracking different experiments. So weights and biases is one of my favorite, and you've got platform for experiments. That's what you'll be looking at. So if you run multiple experiments, you can set up weights and biases pretty easy to track your different model hyperparameters. So PyTorch, there we go. Import weights and biases, start a new run on weights and biases. You can save the learning rate value and whatnot, go through your data and just log everything there. So this is not a course about different tools. We're going to focus on just pure PyTorch, but I thought I'd leave these here anyway because you're going to come across them eventually. And ML Flow is another one of my favorites as well. We have ML tracking, projects, models, registry, all that sort of stuff. If you'd like to look into more ways to track your experiments, there are some extensions. But for now, we're going to stick with hard coding. We're just going to do it as simple as possible to begin with. And if we wanted to add other tools later on, we can sure do that. So let's create a data frame for each of our model results. We can do this because our model results, recall, are in the form of dictionaries. So model 0 results. But you can see what we're doing now by hard coding this, it's quite cumbersome. Can you imagine if we had, say, 10 models or even just 5 models? We'd have to really write a fair bit of code here for all of our dictionaries and whatnot, whereas these tools here help you to track everything automatically. So we've got a data frame here. Model 0 results over time. These are our number of epochs. We can notice that the training loss starts to go down. The testing loss also starts to go down. And the accuracy on the training and test data set starts to go up. Now, those are the trends that we're looking for. So an experiment you could try would be to train this model 0 for longer to see if it improved. But we're currently just interested in comparing results. So let's set up a plot. I want to plot model 0 results and model 1 results on the same plot. So we'll need a plot for training loss, we'll need a plot for training accuracy, test loss, and test accuracy. And then we want 2 separate lines on each of them, one for model 0 and one for model 1. And this particular pattern would be similar regardless if we had 10 different experiments or if we had 10 different metrics we wanted to compare. You generally want to plot them all against each other to make them visual. And that's what tools such as weights and biases, what TensorBoard, and what ML Flow can help you to do. So I'm just going to get out of that, clean up our browser. So let's set up a plot here. I'm going to use matplotlib, going to put in a figure. I'm going to make it quite large because we want 4 subplots, one for each of the metrics we want to compare across our different models. Now let's get number of epochs. So epochs is going to be length, or we'll turn it into a range actually. Range of len model 0 df, so that's going to give us 5. Beautiful, range between 0 and 5. Now let's create a plot for the train loss. We want to compare the train loss across model 0 and the train loss across model 1. So we can go plt.subplot. Let's create a plot with 2 rows and 2 columns, and this is going to be index number 1 will be the training loss. We'll go plt.plot. I'm going to put in here epochs and then model 0 df. Inside here, I'm going to put train loss for our first metric, and then I'm going to label it with model 0. So we're comparing the train loss on each of our modeling experiments. Recall that model 0 was our baseline model, and that was tinyVGG without data augmentation. And then we tried out model 1, which was the same model, but all we did was we added a data augmentation transform to our training data. So PLT, and we'll go X label, they both used the same test data set. And PLT.legend. Let's see what this looks like. Wonderful. So there's our training loss across 2 different models. So we notice that model 0 is trending in the right way. Model 1 kind of exploded on epoch number, that would be 0, 1, 2, or 1, depending how you're counting. Let's just say epoch number 2, because that's easier. The loss went up, but then it started to go back down. So again, if we continued training these models, we might notice that the overall trend of the loss is going down on the training data set, which is exactly what we'd like. So let's now plot, we'll go the test loss. So I'm going to go test loss here, and then I'm going to change this. I believe if I hold control or command maybe, nope, or option on my Mac keyboard. Yeah, so it might be a different key on Windows, but for me, I can press option and I can get a multi-cursor here. So I'm just going to come back in here, and that way I can backspace there and just turn this into test loss. Wonderful. So I'm going to put this as test loss as the title, and I need to change the index. So this will be index 1, index 2, index 3, index 4. Let's see what this looks like. Do we get the test loss? Beautiful, that's what we get. However, we notice that model 1 is probably overfitting at this stage, so maybe the data augmentation wasn't the best change to make to our model. Recall that even if you make a change to your model, such as preventing overfitting or underfitting, it won't always guarantee that the change takes your model's evaluation metrics in the right direction. Ideally, loss is going from top left to bottom right over time. So, looks like model 0 is winning out here at the moment on the loss front. So now let's plot the accuracy for both training and test. So I'm going to change this to train. I'm going to put this as accuracy. And this is going to be index number 3 on the plot. And did we save it as, yeah, just ACK. Wonderful. So I'm going to option click here on my Mac. This is going to be train, and this is going to be accuracy here. And then I'll change this one to accuracy. And then I'm going to change this to accuracy. And this is going to be plot number 4. 2 rows, 2 columns, index number 4. And I'm going to option click here to have 2 cursors, test ACK, and then I'll change this to test ACK. And I'm going to get rid of the legend here. It takes a little bit to plot because we're doing 4 graphs in one hit. Wonderful. So that's comparing our models, but do you see how we could potentially functionize this to plot however many model results that we have? But if we had, say, another 5 models, we did another 5 experiments, which is actually not too many experiments on a problem. You might find that sometimes you do over a dozen experiments for a single modeling problem, maybe even more. These graphs can get pretty outlandish with all the lines going through. So that's again what tools like TensorBoard, weights and biases, and MLflow will help with. But if we have a look at the accuracy, it seems that both of our models are heading in the right direction. We want to go from the bottom left up in the case of accuracy. But the test accuracy, that's training. Oh, excuse me. Is this not training accuracy? I messed up that. Did you catch that one? So training accuracy, we're heading in the right direction, but it looks like model 1 is, still overfitting. So the results we're getting on the training data set aren't coming over to the testing data set. And that's what we really want our models to shine, is on the test data set. So metrics on the training data set are good, but ideally we want our models to perform well on the test data set, data it hasn't seen before. So that's just something to keep in mind. Whenever you do a series of modeling experiments, it's always good to not only evaluate them individually, evaluate them against each other. So that way you can go back through your experiments, see what worked and what didn't. If you were to ask me what I would do for both of these models, I would probably train them for longer and maybe add some more hidden units to each of the layers and see where the results go from there. So give that a shot. In the next video, let's see how we can use our trained models to make a prediction on our own custom image of food. So yes, we used a custom data set of pizza, steak, and sushi images, but what if we had our own, what if we finished this model training and we decided, you know what, this is a good enough model, and then we deployed it to an app like Nutrify.app, which is a food recognition app that I'm personally working on. Then we wanted to upload an image and have it be classified by our PyTorch model. So let's give that a shot, see how we can use our trained model to predict on an image that's not in our training data and not in our testing data. I'll see you in the next video. Welcome back. In the last video, we compared our modeling experiments. Now we're going to move on to one of the most exciting parts of deep learning, and that is making a prediction on a custom image. So although we've trained a model on custom data, how do you make a prediction on a sample / image in our case that's not in either the training or testing data set? So let's say you are building a food recognition app such as Nutrify, take a photo of food and learn about it. You wanted to use computer vision to essentially turn foods into QR codes. So I'll just show you the workflow here. If we were to upload this image of my dad giving 2 thumbs up for a delicious pizza, and what is Nutrify predicted as? Pizza. Beautiful. So macronutrients, there you get some nutrition information and then the time taken. So we could replicate a similar process to this using our trained PyTorch model, albeit it's not going to be too great of results or performance because we've seen that we could improve our models based on the accuracy here and based on the loss and whatnot. But let's just see what it's like, the workflow. So the first thing we're going to do is get a custom image. Now we could upload one here, such as clicking the upload button in Google Colab, choosing an image, and then importing it like that. But I'm going to do so programmatically, as you've seen before. So let's write some code in this video to download a custom image. I'm going to do so using requests. And like all good cooking shows, I've prepared a custom image for us. So custom image path, but again, you could use this process that we're going to go through with any of your own images of pizza, steak, or sushi. And if you wanted to train your own model on another set of custom data, the workflow will be quite similar. So I'm going to download a photo called Pizza Dad, which is of my dad, 2 big thumbs up. And so I'm going to download it from GitHub. So this image is on the course GitHub. And let's write some code to download the image if it doesn't already exist in our Colab instance. So if you wanted to upload a single image, you could click with this button. Just beware that like all of our other data, it's going to disappear if Colab disconnects. So that's why I like to write code so we don't have to re-upload it every time. So if not custom image path.is file, let's open a request here or open a file. Going to open up the custom image path with write binary permissions as F, short for file. And then when downloading, this is because our image is stored on GitHub. When downloading an image or when downloading from GitHub in general, you typically want the raw link, need to use the raw file link. So let's write a request here equals request.get. So if we go to the PyTorch deep learning repo, then if we go into, I believe it might be extras, not in extras, it's going to be in images. That would make a lot more sense, wouldn't it, Daniel? Let's get O4 Pizza Dad. So if we have a look, this is PyTorch deep learning, images, O4 Pizza Dad. There's a big version of the image there. And then if we click download, is this going to give us the raw link? Yeah, there we go. So that's the image. Hey Dad, how you doing? Is that pizza delicious? It looks like it. Let's see if our model can get this right. What do you think? Will it? So of course we want our model to predict pizza for this image because it's got a pizza in it. So custom image path, we're going to download that. I've just put in the raw URL above. So notice the raw GitHub user content. That's from the course GitHub. Then I'm going to go f.write. So file, write the request content. So the content from the request, in other words, the raw file from GitHub here. Similar workflow for if you were getting another image from somewhere else on the internet. And else, if it is already downloaded, let's just not download it. So print f custom image path already exists, skipping download. And let's see if this works. We'll run the code. So downloading data 04pizzadad.jpg. And if we go into here, we refresh. There we go. Beautiful. So our data, or our custom image, sorry, is now in our data folder. So if we click on this, this is inside Google Colab now. Beautiful. We got a nice big image there. And there's a nice big pizza there. So we're going to be writing some code over the next few videos to do the exact same process as what we've been doing to import our custom data set. For our custom image, what do we still have to do? We still have to turn it into tensors, and then we have to pass it through our model. So let's see what that looks like over the next few videos. Woohoo! We are up to one of the most exciting parts of building deep learning models, and that is predicting on custom data. In our case, a custom image of a a photo of my dad eating pizza. So of course we're training a computer vision model on here on pizza, steak and sushi. So hopefully the ideal result for our model to predict on this image will be pizza. So let's keep going. Let's figure out how we can get our image, our custom image, our singular image into tensor form. Loading in a custom image with PyTorch, creating another section here. So I'm just going to write down here, we have to make sure our custom image is in the same format as the data our model was trained on. So namely, that was in tensor form with data type torch float32 and then of shape 64 by 64 by 3. So we might need to change the shape of our image, and then we need to make sure that it's on the right device. Command MM. Beautiful. So let's see what this looks like, hey? So if I'm going to import Torch Vision, now the package you use to load your data will depend on the domain you're in. So let's open up the Torch Vision documentation. We can go to models, that's okay. So if we're working with text, you might want to look in here for some input and output functions, so some loading functions. Torch Audio, same thing. Torch Vision is what we're working with. Let's click into Torch Vision. Now we want to look into reading and writing images and videos because we want to read in an image, right? We've got a custom image, we want to read it in. So this is part of your extracurricular, by the way, to go through these for at least 10 minutes each. So spend an hour if you're going through Torch Vision. You could do the same across these other ones. It will just really help you familiarize yourself with all the functions of PyTorch domain libraries. So we want to look, here's some options for video. We're not working with video. Here's some options for images. Now, what do we want to do? We want to read in an image. So we've got a few things here. Decode image. Oh, I've skipped over one. We can write a JPEG if we wanted to. We can encode a PNG. Let's jump into this one. Read image. What does it do? Reads a JPEG or PNG into a 3-dimensional RGB or grayscale tensor. That is what we want. And then optionally converts the image to the desired format. The values of the output tensor are uint8. Okay, beautiful. So let's see what this looks like, eh? Mode, the read mode used optionally for converting the image. Let's see what we can do with this. I'm going to copy this in. So I'll write this down. We can read an image into PyTorch using, we'll go with that. So let's see what this looks like in practice. Read in custom image. I can't explain to you how much I love using deep learning models to predict on custom data. So custom image, we're going to call it uint8 because as we read from the documentation here, it reads it in uint8 format. So let's have a look at what that looks like rather than just talking about it. torchvision.io, read image. What's our target image path? Well, we've got custom image path up here. This is why I like to do things programmatically. So if our Colab notebook reset, we could just run this cell again, get our custom image, and then we've got it here. So custom image uint8. Let's see what this looks like. Oh, what did we get wrong? Unable to cast Python instance. Oh, does it need to be a string? Expected a value type of string. Oh, but found POSIX path. So the path needs to be a string. Okay, if we have a look at our custom image path, what did we get wrong? Oh, we've got a POSIX path. So let's convert this custom image path into a string and see what happens. Look at that. That's our image in integer form. I wonder if this is plottable. Let's go plt.imshow custom image uint8. Maybe we get a dimensionality problem here. Invalid shape. Okay, let's permute it. Permute, and we'll go 1, 2, 0. Is this going to plot? It's a fairly big image. There we go, 2 thumbs up. Look at us. So that is the power of torchvision.io. IO stands for input output. We were just able to read in our custom image. Now, how about we get some metadata about this? Let's go, we'll print it up here actually. I'll keep that there because that's fun to plot it. Let's find the shape of our data, the data type, and Yeah, we've got it in tensor format, but it's uint8 right now. So we might have to convert that to float32. We want to find out its shape, and we need to make sure that if we're predicting on a custom image, the data that we're predicting on, the custom image, needs to be on the same device as our model. So let's print out some info. Print, let's go custom image tensor, and this is going to be a new line, and then we will go custom image uint8. Wonderful. And then let's go custom image shape. We will get the shape parameter, custom image shape, or attribute, sorry. And then we also want to know the data type, custom image data type, but we have a kind of an inkling because the documentation said it would be uint8, uint8, and we'll go dtype. Let's have a look. What do we have? So there's our image tensor, and it's quite a big image, so custom image shape. So what was our model trained on? Our model was trained on images of 64 by 64. So this image encodes a lot more information than what our model was trained on. So we're going to have to change that shape to pass it through our model. And then we've got an image data type here, or tensor data type of torch uint8. So maybe that's going to be some errors for us later on. So if you want to go ahead and see if you can resize this tensor to 64, 64 using a torch transform or torch vision transform, I'd encourage you to try that out. And if you know how to change a torch tensor from uint8 to torch float32, give that a shot as well. So let's try and make a prediction on our image in the next video. I'll see you there. In the last video, we loaded in our own custom image and got 2 big thumbs up from my dad, and we turned it into a tensor. So we've got a custom image tensor here. It's quite big though, and we looked at a few things of what we have to do before we pass it through our model. So we need to make sure it's in the data type torch float32, shape 64, 64.3, and on the right device. So let's make another section here. We'll go 11.2, and we'll call it making a prediction on a custom image with a PyTorch model, or with a trained PyTorch model. And albeit our models aren't quite the level we would like them at yet, I think it's important just to see what it's like to make a prediction end to end on some custom data. Because that's the fun part, right? So try to make a prediction on an image. Now, I want to just highlight something about the importance of different data types and shapes and whatnot, and devices. 3 of the biggest errors in deep learning. Let's see what happens if we try to predict on uint8 format. So we'll go model1.eval, and with torch.inference mode, let's make a prediction. We'll pass it through our model 1. We could use model 0 if we wanted to here. They're both performing pretty poorly anyway. Let's send it to the device and see what happens. Oh no, what did we get wrong here? Runtime error, input type. So we've got uint8. So this is one of our first errors that we talked about. We need to make sure that our custom data is of the same data type that our model was originally trained on. So we've got torch CUDA float tensor. So we've got an issue here. We've got a uint8 image data or image tensor trying to be predicted on by a model with its data type of torch CUDA float tensor. So let's try fix this by load in the custom image and convert to torch.float32. So one of the ways we can do this is we'll just recreate the custom image tensor, and I'm going to use torchvision.io.readImage. We don't have to fully reload our image, but I'm going to do it anyway for completeness and a little bit of practice. And then I'm going to set the type here with the type method to torchFloat32. And then let's just see what happens. We'll go custom image. Let's see what this looks like. I wonder if our model will work on this. Let's just try again. We'll bring this up, copy this down to make a prediction, and custom image.toDevice. Our image is in torchFloat32 now. Let's see what happens. Oh, we get an issue. Oh my goodness, that's a big matrix. Now I have a feeling that that might be because our Our custom image is of a shape that's far too large. Custom image.shape. What do we get? Oh my gosh, 4,000 and 3,024. And do you notice as well that our values here aren't between 0 and 1? Whereas our previous images, do we have an image? There we go. That our model was trained on were between 0 and 1. So how could we get these values to be between 0 and 1? Well, one of the ways to do so is by dividing by 255. Now, why would we divide by 255? Well, because that's a standard image format, is to store the image tensor values in values from 0 to 255 for red, green, and blue color channels. So if we want to scale them, so this is what I meant by 0 to 255, if we wanted to scale these values to be between 0 and 1, we can divide them by 255 because that is the maximum value that they can be. So let's see what happens if we do that. Okay, we get our image values between 0 and 1. Can we plot this image? So plt.imshow, let's plot our custom image. We got to permute it so it works nicely with matplotlib. What do we get here? Beautiful, we get the same image, right? But it's still quite big. Look at that. We've got a pixel height of, or image height of almost 4,000 pixels and a width of over 3,000 pixels. So we need to do some adjustments further on. So let's keep going. We've got custom image to device. We've got an error here. So this is a shape error. So what can we do to transform our image shape? And you might have already tried this. Well, let's create a transform pipeline to transform our image shape. So create transform pipeline or composition to resize the image. Because remember, what are we trying to do? We're trying to get our model to predict on the same type of data it was trained on. So let's go custom image transform is transforms.compose. And we're just going to, since our image is already of a tensor, let's do transforms.resize and we'll set the size to the same shape that our model was trained on, or the same size that is. So let's go from Torch Vision. We don't have to rewrite this, it's already imported, but I just want to highlight that we're using the transforms package. We'll run that. There we go, we've got a transform pipeline. Now let's see what happens when we transform our target image. Transform target image, what happens? Custom image transformed. I love printing the inputs and outputs of our different pipelines here. So let's pass our custom image that we've just imported. So custom image transform. Our custom image is, recall, of shape, quite large. We're going to pass it through our transformation pipeline and let's print out the shapes. Let's go original shape. And then we'll go custom image dot shape, and then we'll go print transformed shape is going to be custom image underscore transformed dot shape. Let's see the transformation. Oh, would you look at that? How good. We've gone from quite a large image to a transformed image here. So it's going to be squished and squashed a little. So that's what happens. Let's see what happens when we plot our transformed image. We've gone from 4,000 pixels on the height to 64, and we've gone from 3,000 pixels on the height to 64. So this is what our model is going to see. Let's go custom image transformed, and we're going to permute it to be 120. Okay, so quite pixelated. Do you see how this might affect the accuracy of our model? Because we've gone from custom image, is this going to, oh yeah, we need to plot.imshow. We've gone from this high definition image to an image that's of far lower quality here. And I can kind of see myself that this is still a pizza, but I know that it's a pizza. So just keep this in mind going forward, is that another way that we could potentially improve our model's performance if we increased the size of the training image data. So instead of 6464, we might want to upgrade our model's capability to deal with images that are of 224, 224. So if we have a look at what this looks like, 224, 224. wow, that looks a lot better than 6464. So that's something that you might want to try out later on, but we're going to stick in line with the CNN explainer model. How about we try to make another prediction? So since we've transformed our image to be the same size as the data our model was trained on, so with Torch inference mode, let's go custom image pred equals model1 on custom image underscore transformed. Does it work now? Oh my goodness, still not working. Expected all tensors on the same device. Of course, that's what we forgot here. Let's go to device. Or actually, let's leave that error there. And we'll just copy this code down here. And let's put this custom image transform back on the right device and see if we finally get a prediction to happen with our model. Oh, we still get an error. Oh my goodness, what's going on here? Oh, we need to add a batch size to it. So I'm just going to write up here, this will error, no batch size, and this will error, image not on right device, and then let's try again. We need to add a batch size to our image. So if we look at custom image transformed dot shape, recall that our images that pass through our model had a batch dimension. So this is another place where we get shape mismatch issues. Is if our model, because what's going on in a neural network is a lot of tensor manipulation, if the dimensions don't line up, we want to perform matrix multiplication, and the rules, if we don't play to the rules, the matrix multiplication will fail. So let's fix this by adding a batch dimension. So we can do this by going a custom image transformed. Let's unsqueeze it on the first dimension and then check the shape. There we go. We add a single batch. So that's what we want to do when we make a prediction on a single custom image. We want to pass it to our model as an image or a batch of one sample. So let's finally see if this will work. Let's just not comment what we'll do. This, or maybe we'll try anyway. This should work. Added a batch size. So do you see the steps we've been through so far? I'm just going to unsqueeze this. Unsqueeze on the 0th dimension to add a batch size. Oh, it didn't error. Oh my goodness. It didn't error. Have a look at that. Yes, that's what we want. We get a prediction logit because the raw outputs of our model. We get a logit value for each of our custom classes. So this could be pizza, this could be steak, and this could be sushi, depending on the order of our classes. Let's just have a look. Class to IDX. Did we not get that? Class names. Beautiful. So pizza, steak, sushi. We've still got a ways to go to convert this into that, but I just want to highlight what we've done. So note, to make a prediction on a custom image, we had to, and this is something you'll have to keep in mind for almost all of your custom data. It needs to be formatted in the same way that your model was trained on. So we had to load the image and turn it into a tensor. We had to make sure the image was the same data type as the model. So that was Torch float 32. And then we had to make sure the image was the same shape as the data the model was trained on, which was 64, 64, 3 with a batch size. So that was 1, 3, 64, 64, and excuse me, this should actually be the other way around. This should be color channels first because we're dealing with PyTorch here. 64, and then finally we had to make sure the image was on the same device as our model. So they are three of the big ones that we've talked about so much. Same data type or data type mismatch will result in a bunch of issues. Shape mismatch will result in a bunch of issues, and device mismatch will also result in a bunch of issues. If you want these to be highlighted, they are in the learnpytorch.io resource. We have putting things together. Where do we have it? Oh yeah, no, it's in the main takeaway section, sorry. Predicting on your own custom data with a trained model is possible as long as you format the data into a similar format to what the model was trained on. So make sure you take care of the 3 big PyTorch and deep learning errors: wrong data types, wrong data shapes, and wrong devices. Regardless of whether that's images or audio or text, these 3 will follow you around. So just keep them in mind. But now we've got some code to predict on custom images, but it's kind of all over the place. Like we've got about 10 coding cells here just to make a prediction on a custom image. How about we functionize this and see if it works on our pizza dad image? I'll see you in the next video. Welcome back. We're now well on our way to making custom predictions on our own custom image data. Let's keep pushing forward. In the last video, we finished off getting some raw model logits, so the raw outputs from our model. Now, let's see how we can convert these logits into prediction labels. Let's write some code. So, convert logits to prediction labels, or let's go convert logits. Let's first convert them to prediction probabilities. So how do we do that? Let's go custom image pred probs equals torch.softmax to convert our custom image pred across the first dimension. So the first dimension of this tensor will be the inner brackets, of course. So just this little section here. Let's see what these look like. This will be prediction probabilities. Wonderful. So you'll notice that these are quite spread out. Now, this is not ideal. Ideally, we'd like our model to assign a fairly large prediction probability to the target class, the right target class, that is. However, since our model, when we trained it, isn't actually performing all that well, the prediction probabilities are quite spread out across all of the classes. But nonetheless, we're just highlighting what it's like to predict on custom data. So now let's convert the prediction probabilities to prediction labels. Now, you'll notice that we used softmax because why? We are working with multi-class classification data. And so we can get the custom image pred labels, or the integers, by taking the argmax of the prediction probabilities. Custom image pred probs across the first dimension as well. So let's go custom image pred labels. Let's see what they look like. 0. So the index here with the highest value is index number 0. And you'll notice that it's still on the CUDA device. So what would happen if we tried to index on our class names with the custom image pred labels? Or maybe that doesn't need to be a plural. Oh, there we go. We get pizza. But you might also have to change this to the CPU later on. Otherwise, you might run into some errors. So just beware of that. So you notice how we just put it to the CPU. So we get pizza, we got a correct prediction, but this is as good as guessing in my opinion, because these are kind of spread out. Ideally, this value would be higher, maybe something like 0.8 or above for our pizza dad image. But nonetheless, our model is getting 2 thumbs up, even on this 64 by 64 image. But that's a lot of code that we've written. Let's functionize it. So we can just pass in a file path and get a custom prediction from it. So putting custom image prediction together, let's go building a function. So we want the ideal outcome is, let's plot our image as well. Ideal outcome is a function where we plot or where we pass an image path to and have our model predict on that image and plot the image plus the prediction. So this is our ideal outcome, and I think I'm going to issue this as a challenge. So give that a go, put all of our code above together, and you'll just have to import the image, you'll have to process it and whatnot. I know I said we were going to build a function in this video, but we're going to save that to the next video. I'd like you to give that a go. So start from way back up here. import the image via Torch Vision IO read image, format it using what we've done, change the data type, change the shape, change the device, and then plot the image with its prediction as the title. So give that a go, and we'll do it together in the next video. How'd you go? I just realized I had a typo in the previous cell, but that's all right. Did you give it a shot? Did you put together the custom image prediction in a function format? I'd love it if you did, but if not, that's okay. Let's keep going. Let's see what that might look like. And there are many different ways that you could do this, but here's one of the ways that I've thought of. So we want a function that's going to pred and plot a target image. We want it to take in a torch model. And so that's going to be ideally a trained model. We want it to also take in an image path, which will be of a string. It can take in a class names list so that we can index it and get the prediction label in string format. So let's put this as a list of strings. And by default, this can equal none, just in case we just wanted the prediction. It wants to take in a transform so that we can pass it in some form of transform to transform the image. And then it's going to take in a device, which will be, by default, the target device. So let's write a little doc string here. Makes a prediction on a target image with a trained model and plots the image and prediction. Beautiful. Now, what do we have to do first? Let's load in the image. Load in the image just like we did before with Torch Vision. So target image equals torchvision.io.read image, and we'll go string on the image path, which will be the image path here, and we convert it to a string just in case it doesn't get passed in as a string. And then let's change it into type torch float 32, because we want to make sure that our custom image or our custom data is in the same type as what we trained our model on. So now let's divide the image pixel values by 255 to get them between 0 or to get them between 0, 1 as a range. So we can just do this by target image equals target image divided by 255. And we could also just do this in one step up here, 255, but I've just put it out there just to let you know that, hey, read image imports image data as between 0 and 255. So our model prefers numbers between 0 and 1. So let's just scale it there. Now, we want to transform our data if necessary. In our case, it is, but it won't always be. So we want this function to be pretty generic, pred and plot image. So if the transform exists, let's set the target image to the transform, or we'll pass it through the transform, that is. Wonderful. And the transform we're going to get from here. Now what's left to do? Well, let's make sure the model is on the target device. It might be by default, but if we're passing in a device parameter, we might as well make sure the model is there too. And now we can make a prediction. So let's turn on eval/inference mode and make a prediction with our model. So model, we'll call eval mode, and then with torch.inference mode, because we're making a prediction, we want to turn our model into inference mode or put it in inference mode context. Let's add an extra dimension to the image. Let's go target image. We could do this step above actually, but we're just going to do it here. I'm kind of remembering things on the fly here of what we need to do. We're adding let's write this down. This is the batch dimension, e.g. our model will predict on batches of 1x image. So we're just unsqueezing it to add an extra dimension at the 0th dimension space, just like we did in a previous video. Now let's make a prediction on the image with an extra dimension. Otherwise, if we don't have that extra dimension, we saw that we get a shape issue. So right down here, target image pred, and remember this is going to be the raw model outputs, raw logit outputs. We'll go target image pred, and yeah, I believe that's all we need for the prediction. Oh wait, there was one more thing, to device. need to also make sure the target image is on the right device. Beautiful. So a fair few steps here, but nothing we can't handle. All we're really doing is replicating what we've done for batches of images, but we want to make sure that if someone passed any image to our pred and plot image function, that we've got functionality in here to handle that image. And do we get this? Oh, we want just target image to device. Did you catch that error? So let's keep going. Now let's convert the logits. Our model's raw logits. Let's convert those to prediction probabilities. This is so exciting. We're getting so close to making a function to predict on custom data. So we'll set this to target image pred probs, which is going to be torch.softmax. And we'll pass in the target image pred here. We want to get the softmax of the first dimension. Now let's convert our prediction probabilities, which is what we get in the line above. We want to convert those to prediction labels. So let's get the target image pred labels equals torch.argmax. We want to get the argmax of, or in other words, the index, which is the maximum value from the pred probs of the first dimension as well. Now, what should we return here? Well, we don't really need to return anything. We want to create a plot. So let's plot the image alongside the prediction and prediction probability. Beautiful. So plot.imshow, what are we going to pass in here? We're going to pass in here our target image. Now we have to squeeze this, I believe, because we've added an extra dimension up here. So we'll squeeze it to remove that batch size. And then we still have to permute it because matplotlib likes images in the format color channels last, 1 to 0. So remove batch dimension and rearrange shape to be HWC, that is, color channels last. Now, if the class names parameter exists, so we've passed in a list of class names, this function is really just replicating everything we've done in the past 10 cells, by the way. So right back up here, we're replicating all of this stuff in one function. So pretty large function, but once we've written it, we can pass in our images as much as we like. So if class names exist, let's set the title to showcase that class name. So the pred is going to be class names. Let's index on that, pred image or target image pred label. And this is where we'll have to put it to the CPU, because if we're using a title with matplotlib, matplotlib cannot handle things that are on the GPU. This is why we have to put it to the CPU. And then I believe that should be enough for that. Let's add a little line in here so that we can have it. Oh, I've missed something. An outside bracket there. Wonderful. Let's add the prediction probability because that's always fun to see. So we want target image pred probs, and we want to get the maximum pred prob from that, and we'll also put that on the CPU. And I think we might get this to 3 decimal places. Now this is saying, oh, pred labels, we don't need that. We need just non-plural. Beautiful. Now, if the class names doesn't exist, let's just set the title equal to f string. We'll go pred target image pred label. Is Google Colab still telling me this is wrong? Target image pred label. Oh no, we've still got the same thing. It just hasn't caught up with me yet. I'm coding a bit fast here. And then we'll pass in the prob, which will be just the same as above. I could even copy this in. Beautiful. And let's now set the title to the title, and we will turn the axes off. PLT axes false. Fair bit of code there, but this is going to be a super exciting moment. Let's see what this looks like when we pass it in a target image and a target model, some class names, and a transform. Are you ready? We've got our transform ready, by the way. It's back up here. Custom image transform. It's just going to resize our image. So let's see. Oh, this file was updated remotely or in another tab. Sometimes this happens, and usually Google Colab sorts itself out, but that's all right. Doesn't affect our code for now. Pred on our custom image. Are you ready? Save failed. Would you like to override? Yes, I would. So you might see that in Google Colab. Usually it fixes itself. There we go. Save successfully. Pred and plot image. I was going to say, Google Colab, don't fail me now. We're about to predict on our own custom data. Using a model trained on our own custom data. Image path, let's pass in custom image path, which is going to be the path to our pizza dad image. Let's go class names equals class names, which is pizza, steak, and sushi. We'll pass in our transform to convert our image to the right shape and size. Custom image transform. And then finally, the target device is going to be device. Are you ready? Let's make a prediction on custom data. One of my favorite things, one of the most fun things to do when building deep learning models. 3, 2, 1. How did it go? Oh no, what did we get wrong? CPU. Okay, so close, but yet so far. Has no attribute CPU. Oh, maybe we need to put this to CPU. That's where I got the square bracket wrong. So that's what we needed to change. We needed to, because this is going to be potentially on the GPU, targ image pred label, we need to put it on the CPU. We need to do that. Why? Because this is going to be the title of our matplotlib plot, and matplotlib doesn't interface too well with data on a GPU. Let's try it again. 3, 2, 1, running. Woohoo! Look at that. Prediction on a custom image, and it gets it right. 2 thumbs up. I didn't plan this. Our model is performing actually quite poorly, so this is as good as a guess to me. You might want to try this on your own image, and in fact, if you do, please share it with me. I would love to see it. But you could potentially try this with another model, see what happens. Steak. Okay, there we go. So even though model 1 performs worse quantitatively, it performs better qualitatively. So that's the power of visualize, visualize, visualize. And if we use model 0, also, which isn't performing too well, it gets it wrong with a prediction probability of 0.368, which isn't too high either. So we've talked about a couple of different ways to improve our models. Now we've even got a way to make predictions on our own custom images. So give that a shot. I'd love to see your custom predictions. Upload an image here if you want, or download it into Google Colab using code that we've used before. But we've come a fairly long way. I feel like we've covered enough for custom data sets. Let's summarize what we've covered in the next video. And I've got a bunch of exercises and extra curriculum for you. So this is exciting stuff. I'll see you in the next video. In the last video, we did the very exciting thing of making a prediction on our own custom image. Although it's quite pixelated, and although our model's performance quantitatively didn't turn out to be too good, qualitatively, it happened to work out. But of course, there are a fair few ways that we could improve our model's performance. But the main takeaway here is that we had to do a bunch of pre-processing to make sure our custom image was in the same format as what our model expected. And this is quite a lot of what I do behind the scenes for Nutrify. If you upload an image here, it gets pre-processed in a similar way to go through an image classification model to output a label like this. So let's get out of this. To summarize, I've got a colorful slide here, but we've already covered this. Predicting on custom data. These are 3 things to make sure of, regardless of whether you're using images, text, or audio. Make sure your data is in the right data type. In our case, it was torch float 32. Make sure your data is on the same device as the model. So we had to put our custom image to the GPU, which was where our model also lived. And then we had to make sure our data was in the correct shape. So the original shape was 64-64-3. Actually, this should be reversed because it was color channels first, but the same principle remains here. We had to add a batch dimension and rearrange if we needed. So in our case, we used images of this shape, batches first, color channels first, height, width. But depending on your problem will depend on your shape, depending on the device you're using will depend on where your data and your model lives, and depending on the data type you're using will depend on what you're using for Torch Float 32 or something else. So let's summarize. If we go here, main takeaways, you can read through these, but some of the big ones are PyTorch has many built-in functions to deal with all kinds of data, from vision to text to audio to recommendation systems. So if we look at the PyTorch docs, you're going to become very familiar with these over time. We've got Torch audio data, Torch text, Torch vision is what we practiced with. And we've got a whole bunch of things here for transforming and augmenting images, data sets, utilities, operators, and Torch data is currently in beta, but this is just something to be aware of later on. So it's a prototype library right now, but by the time you watch this, it might be available. But it's another way of loading data. So just be aware of this for later on. And if we come back to up here, if PyTorch built-in data loading functions don't suit your requirements, you can write your own custom dataset classes by subclassing torch.utils.data.dataset. And we saw that way back up here in option number 2. Option 2, here we go. Loading image data with a custom dataset. We wrote plenty of code to do that. And then a lot of machine learning is dealing with the balance between overfitting and underfitting. We've got a whole section in the book here to check out what an ideal loss curve should look like and how to deal with overfitting, how to deal with underfitting. It is a fine line. So much of the research in machine learning is actually dedicated towards this balance. And then 3 big things for being aware of when you're predicting on your own custom data: wrong data types, wrong data shapes, and wrong devices. This will follow you around, as I said, and we saw that in practice to get our own custom image ready for a trained model. Now, we have some exercises here. If you'd like the link to it, you can go to learnpytorch.io, section number 4, exercises, and of course, extra curriculum. A lot of the things I've mentioned throughout the course that'd be a good resource to check out contained in here. But the exercises, this is your time to shine, your time to practice. Let's go back to this notebook, scroll right down to the bottom. Look how much code we've written. Goodness me. Exercises. For all exercises and extra curriculum, see here. Turn that into Markdown. Wonderful. And so if we go in here, you've got a couple of resources. There's an exercise template notebook for number 4 and example solutions for notebook number 4, which is what we're working on now. So of course, I'd encourage you to go through the PyTorch custom datasets exercises template first. Try to fill out all of the code here on your own. So we've got some questions here, we've got some dummy code, we've got some comments. So give that a go. Go through this. Use this book resource to reference, use all the code we've written, use the documentation, whatever you want, but try to go through this on your own. And then if you get stuck somewhere, you can look at an example solution that I created, which is here, PyTorch Custom Datasets Exercise Solutions, and just be aware that this is just one way of doing things. It's not necessarily the best, it's just a way to reference what you're writing to what I would do. And there's actually now live walkthroughs of the solutions, errors and all, on YouTube. So if you go to this video, I'm just going to mute. So this is me live streaming the whole thing, writing a bunch of PyTorch code. If you just keep going through all of that, you'll see me writing all of the solutions, running into errors, trying different things, etc., etc. But that's on YouTube. You can check that out on your own time. But I feel like we've covered enough. Exercises. Oh, by the way, this is in the Extras Exercises tab of the PyTorch Deep Learning repo. So extras, exercises, and solutions are contained in there. Far out. We've covered a lot. Look at all that. So that has been PyTorch Custom Datasets. I will see you in the next section. Welcome to the next section. Going modular with PyTorch. Now this is a very exciting section, but before we get started, let's start how we always start. Where can you get help? Number 1 rule, follow along with the code. If in doubt, run the code. All of the code resources you need will be on the GitHub, so if you get stuck, you can reference them. Then of course, try it for yourself. Write the code, try it out, see what comes out. Press Shift, Command, and Space if you'd like to read the doc string. If you're still stuck, I'd recommend searching for it. You'll come across resources such as Stack Overflow or the very helpful PyTorch documentation, which we've had plenty of practice with so far. Then, of course, try again, refer back to the motto, if in doubt, run the code. Finally, if you're still stuck, you can always ask a question on the PyTorch Deep Learning discussions page. So the discussions page for this course. You can go new discussion. You can select a category, Q&A, or anything else here that you like, such as maybe section 05, and then what is going modular? And then if we come down in here, and then video number, doing this will really help us out, help you. So video number might be 171 or something like that. I'm not sure exactly what video number this is. This is just an example. And I'm not sure what going modular is. And then you could click start discussion, and then someone will help you out answering that question. But speaking of what is going modular, how about we answer that question? So this is the whole goal of this entire section, is to go modular. And what do I mean by that? Well, you might have written some nice code in a notebook. You might be wondering, can I reuse it elsewhere? And in fact, we have. We have written lots of nice code in plenty of notebooks so far. And a lot of that code, we've had a bit of practice now writing it a few times, and I've done that on purpose because one of the best ways to practice code is to write more code. But now that we've had some practice writing training loops and data loading and whatnot, we might want to reuse it. So the whole premise of going modular is that yes, you can reuse your helpful code, and that's what we want to cover in this section. Reuse the most useful code from our previous notebook in Python scripts. Let's get a little bit more specific here. Food Vision Mini is what we built in the last section. We loaded in some data, or we wrote some PyTorch code to load in some data of steak, sushi, and pizza images. We built and trained a model to identify different foods. Then we made some predictions with the model, albeit they weren't as good as what this graphic is showing. It did get a fair few wrong, but that's okay. What we want to focus on in this section is turning all of the code here that we use to load our data, to build a model, to train a model, into a series of Python scripts. We're going to finish up with a directory structure like this. So we'll have a top-level directory called going modular after this section. Then we'll have a subdirectory also called going modular. And then within that going modular subdirectory, we'll have a series of Python scripts. So one to prepare the data, one to train and test the model in the engine.py, one to build our PyTorch model. We've built a PyTorch model a fair few times now, so rather than rewrite the code every time, we can put that into a Python script. Then we'll have train.py, and then we'll have utils.py, and finally we'll also end up with a models directory that's going to contain our different trained PyTorch models. And our data is going to be in the same format that we've used over the past couple of sections. And that is standard image classification format, our images of pizza, steak, and sushi. But this is another thing to note. You could customize this in almost any way, shape, or form you like. And the same with your data. It really depends on the problem you're working on. But this kind of structure here is often how you'll find PyTorch code in the wild. But we'll get to that in a second. Here's what we really want to do. We want to be able to train a PyTorch model with a single line of code. And with that single line of code, it would be great if we could pass in different hyperparameters, such as which model to train. How big should our batch size be? What learning rate should we use? How long should we train for? Now, this is a command on the command line. We could run Python, train.py, that's our target script. We want to train some model. We want to use a batch size of batch size. We want to use a learning rate of learning rate. We want to train for num epochs. Now, these flags here are called argument flags. We'll have a look at that later on. But here's an example. If we wanted to train our tiny VGG model from the last section, we could write Python, train.py, model tiny VGG, batch size 32, learning rate 0.001, number of epochs 10. And of course, you might be guessing, could we add more hyperparameters here, such as number of hidden units or number of layers or something like that? And the answer is yes. This could really extend out to 20 different hyperparameters, to 30, to 10. Doesn't really matter. It's infinitely customizable. And so what this line is essentially saying is train the tiny VGG model with a batch size of 32 and a learning rate of 0.01 for 10 epochs. Now, as I mentioned before, this is often how you'll find PyTorch code in the wild. Yes, of course, you'll find them in different notebooks, but this is the Detectron 2 documentation. Now, Detectron 2 is a computer vision library from Meta or Facebook that uses PyTorch. And so if we see here, we've got trainnet.py. That's going to train your neural network on 8 GPUs, it looks like, with a certain configuration file. And then if you wanted to train with 1 GPU, you notice how there's another argument flag here. You just change that to 1 GPU. And you can change a few hyperparameters here. But that's trainnet.py. That's a Python script. The same thing goes for this Torch Vision. So we've been using Torch Vision. So that's from the actual PyTorch library itself. This is how they do object detection. So if you go to PyTorch/vision/references/detection, object detection, you'll see there's a bunch of Python scripts here. There's train.py, utils.py, engine.py. The same thing here on the PyTorch blog post where they train state-of-the-art computer vision models with Torch Vision. They use Torch Run, which is a way of running your PyTorch scripts or your Python scripts. I'll leave that as extra curriculum if you want to look into it. But here's train.py. There's the model. They're using ResNet 50 with a batch size of 128, a learning rate of 0.5, a learning rate scheduler of cosine annealing LR, a learning rate warm-up epochs of 5, learning rate warm-up method linear. There's a lot of different hyperparameters here, a fair few, a bit more that are outside the scope of this course, but the principles we're going to cover are much the same. We want to write a train.py script by the end of this section that's able to train our model. And then same thing here. This is a brand new paper at the time of recording called convmae paper on GitHub. Now they run Python, submit it, finetune.py, a Python script. So I just want to share with you my workflow. It's not necessarily the be all and end all of workflows. It is just one example. So this is one of many options to turn your useful notebook code into Python scripts. So I start with Jupyter/Google Colab notebooks because they are great at experimenting and visualizing different things. And then if I've written some useful notebook code in some code cells, I move the most useful code to Python scripts. So it's still PyTorch code here, import OS, from Torch Vision, import datasets, transforms, from Torch utils.data, import data loader. And this might be called datasetup.py. And this is what's going to set up my data. And here we return a train data loader, a test data loader, and class names. We're going to have a look at how to create one of these files, or many of these files actually, in the upcoming coding sections. Now, there's two parts of this section, or two notebooks of this section that you need to be aware of. One is cell mode, and one is script mode. What we're going to be doing is we're going to start with a cell mode notebook. So this is Notebook 05 Part 1, Cell Mode. This is nothing different from a normal Jupyter notebook, a normal Google Colab notebook. We're going to run it from top to bottom. It just executes Python code in cells just as we've been doing throughout the rest of the course. Now, this is Part 1. We're going to use that as the basis to move to Part 2. Now, the script mode notebook is going to turn our useful code into Python scripts using a Jupyter magic command. Now, this is something to be aware of, or something you can look up as well. A magic command is something that starts with double percentage sign. Now, there's other magics that start with a single percentage sign, but ours specifically starts with a double percentage sign. Then we're going to write file, that's the command, and then going modular/modelbuilder.py will write whatever is in this code cell to a script of the name modelbuilder.py in the going modular directory. Now we're going to see this in action later on, but this is just something to be aware of. This section comes in two parts. Part 1 is a notebook that is cell mode. Part 2 is script mode, which is going to turn the code from cell mode into Python scripts. We're going to adhere to our workflow, of course. We've seen this a few times now, so we can jump through it a bit. But what I want you to be aware of is that each of these little sections here, because they kind of function within themselves, they do interact with each other, but they can all be individualized into different Python scripts. And that's what we're going to see throughout this section. So each of these could be turned into a Python script. So one to get your data ready, one to build a model, one to train the model, one to, well, fitting is part of training the model, one to evaluate, one to save, etc., etc. And finally, what we're going to cover broadly, well, we've already gone through a fair bit of this, but we'll see how we can transform data for use with a model. We've already done a bit of that. We're loading custom data with pre-built functions. We're going to build Field Vision Mini to classify pizza, steak, and sushi images. This is the main one we're focused on, turning useful notebook code, all of the above, into Python scripts. And finally, we're going to see how we can train a PyTorch model from the command line. And how, well, this is a machine learning cooking show, so we're going to be cooking up lots of code. And with that being said, let's code. I'll see you in Google Colab. Alrighty, let's write some code. This is one of my favorite sections of the whole course. Now, I just want to get you familiar with some resources that we're going to be using. So the first one is going modular, so section 5. A whole text-based version of this section is contained in this section. Now, of course, that is part of the book version of the course, so 05 PyTorch going modular. Everything you need for the upcoming videos will be in here, such as what is going modular, why would you want to go modular, a few things that we've covered, pros and cons of notebooks versus Python scripts. Now, this is really exciting for me because if you're like me, I learned to code Python in a Jupyter notebook, whereas a lot of code you'll find in the wild is not in a Jupyter notebook, but in Python scripts. So that's what we're focused on doing in this section, is going from notebook to Python scripts. There's my workflow that I talked about, how you'll find PyTorch code in the wild, and a lot more. But here's what we're going to cover. Oh, and there's a typo there. I better fix that. But the main concept of this section is to turn useful notebook code cells into reusable Python files. So specifically, there are 2 notebooks for this section. Part 1 is in cell mode. So this is just run as a normal notebook, top to bottom, and it's a condensed version of Notebook 04. So what we did in the last section, PyTorch custom datasets, we wrote a lot of code, right? Look how much there is. So all I've done for part 1 of section 05, what we're going to cover, is for cell mode, I've condensed all of the code from Notebook 04. And then script mode builds upon cell mode. So the reason we're doing 2 parts is so that you can see the changes I've made in part 2 compared to part 1. So if you'd like to reference what we're working towards, part 2 is what we're working towards. So there's the notebook there. But we're going to start with part 1. So let's open that, part 1. And if you'd like to find this as well, another section that you should be aware of. So this is back on the PyTorch Deep Learning homepage. Going modular, in here is another explainer of what we're going to do. So there's part 1, cell mode. We're working from part 1 towards part 2. So I could open it up from here. This is again, PyTorch Deep Learning within the going modular section, or from 0.5. So going modular, I just opened up the cell mode part 1. And now to make a copy of this, I'm going to click this button here, open in Colab. So let's see what happens when we do this. I'm just going to X out of all these extra tabs. So just to remind you, I went from the home page, going modular, and then opened up part number 1. And then while it's loading up here, I clicked open in Colab. So that's what's going to give us this, part 1, cell mode. Now to make a copy of this, I can click copy to drive. So this is going to create a copy in my own Google Drive, because you'll notice the difference here. This is running from GitHub. Now this is running from Google Drive. So I'd recommend you do that if you'd like a copy of this notebook in your own Google Drive. So because this is a video notebook for me, I'm going to just append the video tag here. That way you know that I've run this notebook in the videos. And it will end up in PyTorch Deep Learning in the video notebooks folder at the end of this section. So let's close the GitHub version of this one. So notice the GitHub symbol. I'm running the one with the Google Drive symbol because I just copied that to my Google Drive. I'm going to make sure that I have a GPU, save, and then we'll connect, we'll start our runtime. Connecting. Beautiful. So you'll notice that there's some information. This is part 1 of 2. There's some links to the notebooks we've talked about. What is cell mode? So cell mode is we're just going to run this notebook exactly how it is. No changes. And what's the difference between part 1 and part 2? Well, you can read on that there, but I prefer to show you. Where can you get help? So this is a little bit different to how we've started notebooks before. This one we're starting with some code. Now the reason we're starting with some code is because we've written all of the code in the previous section in Notebook 04. So let's just see what happens if we run all of these cells. So section 1 is going to get the data. That's going to download the pizza steak sushi zip file from GitHub. It's going to set up a training and test directory. It's going to create some data sets and data loaders, more specifically a train data loader and a test data loader. It's going to make a model, tinyVGG. We've seen all of this code in the previous sections. It's going to set up device agnostic code here and create an instance of tinyVGG. Then we've got a dummy forward pass. We create a train and test step functions and train to combine them. So you'll see train step here. You'll notice I've also added doc strings to these functions that we've written in the previous notebook. And that's in the format of Google's Python functions and methods style guide. So this is just a way to style your Python code. And if you're going to be writing code that you're going to reuse and share, oftentimes you'll want to have a doc string here that explains what's going on. Not only for other people that read it, but for your future self, if you were to reread your code, what's going on. And so to make a doc string in a style that's well respected and used quite widely, I used Google's style guide for Python. Then if we keep going, we have a test step function. We have a doc string as well. We have a train function, which is going to leverage test step and train our model. We have a function called save model, which is going to save a model to file. Then we have a series of code steps here that's going to train, evaluate, and save the model. So there we go, train model 0, and we get some epochs here, we get some training, and finally it finishes with saving the model to the models directory. So we come over here, data directory, that's created when we run the first cell, get data. Sample data, this comes with Google Colab, so don't worry about this one. And models, there is our saved model. So what we want to do, this notebook runs end to end by using code cells, so in cell mode. What we want to do is turn all of our useful code cells into Python scripts. Now, that's where part 2 notebook comes in. So that's what we're working towards. So if you want to have a look at what we're working towards, you can leverage or you can go and look at part 2. But in the next video, now that we've started off with cell mode, we're going to start writing some code to turn the most useful notebook cells here into Python scripts. Namely, what do we want to end up with? We want to end up with a file called going modular that has datasetup.py, engine.py, modelbuilder.py, train.py, and utils.py. So that's what we're working towards. I'll see you in the next video. Welcome back. In the last video, we checked out the lay of the land for our going modular section. And the two best places to find information about the going modular section are 05, PyTorch going modular, and the going modular directory. So we started off by going to notebook part 1, which is cell mode. We opened that in Google Colab using this button here. I then made a copy of that in my Google Drive, and then I ran all of the cells in this notebook here. So if we go down, have a look, this is all of the code that we wrote for notebook 04, section 04, custom datasets. It's just being condensed into a few useful code cells, because that's the name of the game, right, for the going modular section. We want to turn useful notebook code cells into reusable Python script. In other words, .py files, specifically the files that are in here. So let's just have a look. What if we were to restart this runtime? I just want to emphasize what we're doing with these cells in here. Let's go up to section number 1, and that's get data. So I've just restarted the runtime. I'll restart it again just to make sure. Restarting. And do we have any files over here? We still do, so I might remove these files over here, just so rmrf, the bang, by the way, this exclamation point in a code cell, means that I want to run this line on the command line. I'm going to remove the data folder, just to emphasize the fact that this was generated by the notebook. So that's gone. And I'm also going to remove models. Wonderful. So if we refresh that, we've got a new notebook, and the sample data, this comes with Google Colab, so don't worry too much about that. So the get data code cell is the same one that we used in notebook 04. So section 1, get data. If you'd like to read up on how we got it, you can read this section here. So we're not going to spend too much time on how this works because we've already written this code. But let's just see what happens when we run it. So we import OS, zip file, we set up a path to a data folder. If the image folder doesn't exist, we download and prepare it. We download some pizza, steak, and sushi data, sushi images that is, pizza, steak, and sushi images. We unzip it, and then we remove the zip file because we don't need that anymore. Let's see what happens if we run this cell. Didn't find, so we download and we unzip. If we have a look over here now, we've got data. Now this is going to download some images in standard image classification format. So if we have a look in here, we've got test directory, we've got the train directory, and within each of those, we have training images for the pizza class. Then if we close that, for the steak, for sushi, and the label for each of those images is the directory name. So the pizza images are in here, same for the testing folder. Now we've covered that in a previous module, but that's just all this cell is doing is getting the data. And in fact, you might want to, with what you're about to learn in this section, turn this into a script of itself. In fact, that's your first exercise for this section. But now, what do we do next? Well, we set up the training and testing paths. So let's create a path here for the training data and the testing data. Again, we've already written code to do this. The whole premise of this section is to reuse useful code. So we're going to leave that how it is. All that this cell is doing is replicating the same code we used in Notebook 04 to download the pizza, steak, and sushi dataset. Now from here on out, we want to turn all of these subsections into Python scripts. That's exactly what the script mode notebook contains. So if we have a look, let's get a little preview of what's going on. If you run these two side by side, part 1 and part 2, you'll see the differentiation. So we've got the get data, exact same code in this notebook. Then we've got section 2. The difference in part 2, script mode notebook, is that we have sections that are 2.1, create datasets and data loaders in script mode. So if you want to jump ahead and have a look at that, you can. Otherwise, let's create a script to create data loaders in the next video. I'll see you there. Welcome back. In the last video, we ran a code cell to get some data. Now, if you'd like, you can try to turn this into a Python script using what we're about to learn, but we also discussed that this is what we're working towards. We're working towards creating Python scripts, so the script mode notebook. So this section comes with 2 parts. We start with part 1, we're trying to move towards part 2. So let's keep pushing forward with that. We're up to part 2 of the cell mode notebook. Create datasets and data loaders. So we've got a dataset over here, which is in standard image classification format. And in the previous section, section 04, we learned how we can use Torch Vision datasets and transforms to load in our data in its current form and turn it into datasets. We also learned that we can turn our datasets into data loaders. However, we've written code like this before. So wouldn't it be good if we could functionize this or turn it into a Python script that we could reuse? So let's just run this and see what happens. Shift and enter, shift and enter. We can get the class names. We can get a class dictionary if we want. We can check the length and we can turn train and test datasets into data loaders. Wonderful. And then we can check out a single image size and shape. So let's have a look at how we could go modular with this particular section. Let's create section 2.1. And this is going to be a script for create data sets and data loaders script mode. Now, I want to emphasize that this is only one way of creating a script like we're doing here. So we could just copy this into a .py file, but there's a Jupyter Magic command called write file that we're going to use. So I'll just write this down. So let's use the Jupyter Magic function to create a .py file for creating data loaders. So let's look this up. Jupyter Cell Magic. And if you're wondering why am I using Jupyter and not Google Colab, well, Google Colab runs a version of Jupyter under the hood. So Jupyter notebooks are a very popular way to run different data science code. And Google Colab builds on top of Jupyter, which is why if you save your notebook, it saves it as an IPyNB. Jupyter, before it was called Jupyter, was called IPython. But it's now a Jupyter notebook, Colab notebook, same thing, just running in different areas. So built-in magic commands. Notice that there are magics here with a single percentage sign, that's a line magic. And then I believe if we look up the double percentage sign, what do we have here? Are we going to get, yeah, cell magics. So a cell magic runs in the whole cell. So if we look up percentage write file, here we go. Write the contents of the cell to a file. That's exactly what we want. So what are we trying to do? We're trying to save our most useful code cells to reusable Python scripts. So we can save a code cell's contents to a file using the Jupyter Magic. Now let's write in write file, and then it's going to be file name after that. Beautiful. So let's see this in practice. How about we create a file, we write a file called, we're going to save it to a going modular directory, and we're going to go data setup.py. Now, I just want to re-highlight the fact that we're turning this code here into a Python script. And if you're wondering where this code came from, create data sets and data loaders. If we go back to Notebook 04, we loaded in image data using image folder, and then we created the data sets there, and then we turn in the data loaders there. So that's where this code came from. We're just going to get out of that, so we have less tabs open. Let's see what we can do here, hey? How about at the top of the file, we write a docstring, which explains what the file will do. Functionality for creating PyTorch data loaders, and for image classification data. So this is going to appear at the top of our .py file, and it tells anyone who uses it that, hey, this is what this file does. So let's start off. We need to import the same things that we have here. So we need to copy this from Torch Vision datasets, import datasets and transforms. Wonderful. And we need to also import data loader, because this is going into a Python script. So our Python script needs all of the modules that our scripts have access to. And there's one more thing that we're going to use, which is import OS. We'll see where that comes into play in a second. Or actually, how about we just do it right now? Num workers equals os.cpu count. Beautiful. So let's keep pushing forward. We're going to go def create data loaders. Now this is going to be a function that we can use to create our data loaders. So let's put some inputs to this function. We want it to look up a training directory. This can be a string. We want it to also look up a testing directory path. This can also be a string. And then we'll pass in a transform to transform our data in some way, shape, or form. And we want to let it know that it's a composition of transforms from the transforms library. What else would we need? Maybe a batch size. This can be an integer. And then finally, let's set num workers for the data loaders to be an int. and we'll set it to num workers. So num workers is just going to be however many CPUs we have access to. So if we were to run this, get rid of this line, otherwise it's going to save it to file. Num workers is 2 in the case of Google Colab. It might be more if you're using num workers /os.cpu count on your local machine. So let's just get rid of this and see what happens if we just run this. Oh, no such file or directory going modular. Well, what we're going to have to do is create a directory for going modular scripts. So we could of course come over here and add a file, but let's just create one using code. We're going to go os make dirs going modular. We're going to store all of our scripts here. So if we have a look, going modular, that's all we created. This is going to be empty now. And that's why we got that error, because going modular didn't exist. So let's run this and see what happens. Oh, look at that. We've written our first Python script, albeit it doesn't do too much. Let's have a look. Going modular, data setup.py. Look at that. That is the power of this Jupyter magic. We write this line and then we get this. So you can imagine later on, if we have some useful code and we want to write it to file, we can use this line here. So let's complete this file setup, hey? We'll get rid of that and we'll get rid of this. Let's just go back to finishing off this. We'll write a doc string here. I'm going to spend a bit of time on this first one, writing a doc string, just so you can see what it's like. Testing data loaders. Maybe I'll leave that as a challenge to you. And I'm using Google's style guide for Python. We've covered this before, briefly mentioned it. But if you're writing a function, oh, we're going to have a lot of, we search for docstring. Yeah, comments and doc strings. Here we go. This is your extra curriculum. To read up how you should structure the doc strings of your functions, this is Google's style guide. You don't necessarily have to use this. It's just, I find it fairly easy to read, and you might see it in a fair few places where Python scripts are written. So this is what we did at the start of our module. And if you're working with functions and methods, you can write args, returns, raises. So we have one line at the top of our function describing exactly what the function does. We can describe it a little bit longer here. We can type in what args it takes, so arguments here, table handle, explain what that is. Then we have returns, what comes out of it. So in this case, a dictionary comes out and it looks like this. So that's what we're going to replicate for our function here. Let's go back. Takes in a training directory and testing directory path and turns them into PyTorch datasets and then into PyTorch data loaders. And that line is a bit too long for Python, so we're just going to enter that. Beautiful. And now, what args do we take? Let's write in here, train_dir, which is the path to training directory. So all I'm doing is writing information about train_dir and test_dir and the arguments that our function takes here. Test_dir, path to testing directory. Now this is important to do not only for people that you share your code with, because that's what you eventually want to do, right? Is write code that's so good you can share it with others. But it's also for your future self. What if you were to look up some code that you've written a few months ago and you don't know what's going on? So this is transformed to perform on the training and testing data. You can customize, this is important to know, you can customize these functions however which way you want. What I am writing now is just one way of doing things. So batch size is going to be number of samples per batch in each of the data loaders. And then finally, we're going to set num workers, which will be an integer for number of workers per data loader. And then finally, we can type out returns. What do we get from this? a tuple of, we're going to get a train data loader back. We're also going to get a test data loader, and we're also going to get class names. Beautiful. We'll just explain what class names is. Class names is a list of the target classes. And after we write the example usage, we'll finish this video off so it doesn't get too long. And then I'll set you the challenge of actually writing the entire function here by condensing the code that we've got, the train data loaders and the dataset creation and the transformation creation. I think you can do this. Once we have the example usage down, that'll be your challenge for this notebook. So train data loader, test data loader, class names equals, we want to create a function here called create data loaders like we've written above. Train dir equals the path to the train directory. And then the test dir, I might just tab across here. Test dir equals path to test dir, where the test data is. And then transform equals some transform that you can create. Let's say the batch size is by default 32, and then the num workers, let's just say that's 4. But we've already hard-coded num workers, so we don't necessarily have to do that. So give that a go. Down here, by the end, it should return train data loader, test data loader, and class names. So in here, it's going to be some code. So that's your challenge for this video, to prevent it from getting too long. What we're doing is we're turning this code, data loaders and data set, into a Python script called datasetup.py. And what we just did was we wrote a docstring, so if someone uses our code in the future, or we do, in Google style, they know what's going on and they have an example of what happens. So give that a go, write in the code there, and we'll do it together in the next video. Welcome back. In the previous video, we wrote the outline for our first Python script, which is super exciting, datasetup.py. Namely, we created a function here to create some data loaders given a training directory, a testing directory, a transform, a batch size, and some number of workers. We wrote the docstring here in Google Python style guide. We're going to be continuing to do that throughout the rest of this section for writing our various scripts. So I'm going to get out of that. And we use the built-in Jupyter Magic, I was about to say Python, but it's a Jupyter Magic, also IPython, write file to turn this cell into a script. So let's keep going forward. I set you the challenge of filling in the logic for this code. So I hope you gave it a shot, but let's now try it out together. And I think the tabbing is a bit off with this. I'm just gonna shift tab there and then tab that across. Okay, beautiful. Tab. Wonderful. So let's load in our data sets. I'm going to here use image folder to create data sets. So we can go train data equals, let's do datasets dot image folder, and then we're going to pass in train dir, which is our parameter from up here, train dir. And then we can also pass in the transform, which equals transform. Wonderful. And then we can create test data equals datasets dot image folder. Then we'll pass it in the test dir and the transform. In this case, we're using the same transform for test and train, which is, you don't always have to do that, but just for simplicity, just to exemplify what we're doing, we're just going to keep it straightforward. Same transform for training and test data. And that's because we've got a transform parameter here. Now we've got data sets. What do we have to do? Well, we can get the class names, because you see down here, our function returns a train data loader, a test data loader. We haven't created those yet, but it also returns class names. So let's set the class names equal to train data dot classes. We've seen that before in a previous module. Now we can turn our images into data loaders. So PyTorch data loaders. And we can do this because in our script, we've imported from torch.utils.data import data loader. So let's create the train data loader, which is going to be equal to data loader, and then we'll pass it a train data set. Then we'll pass it in the batch size as equal to batch size. Then we'll set shuffle equals to true for the training data. And then we'll set the number of workers, so num workers. This is going to be how many cores are used to load our data, equals our num workers parameter, which is this one here, num workers argument. And I might just tab this over as well, and tab this over. Formatting is very important in Python, as you'd be aware of. And then we're going to use this other parameter called pin memory. We haven't seen this one before, I don't think. But where could we find out about pin memory? Well, let's look up the documentation for data loader. We could look it up here, Shift Command Space, but I personally find this a little bit hard to read in Google Colab. So let's go PyTorch data loader, torch.utils.data, and let's find pin memory. What does this do? You might see this somewhere, so that's why I'm highlighting it. It is generally not recommended to return CUDA tensors in multiprocess. Instead, we recommend using automatic memory pinning, i.e. setting pin memory equals true, which enables fast data transfer to CUDA-enabled GPUs. So this is an important thing. As we might have discussed previously, if not, I'm going to discuss it now. A lot of your time will be spent transferring data from non-GPU, so say a CPU, to a GPU. And so what pin memory equals true does is it enables pinning memory, so keeping memory in place on a GPU where possible. So rather than spend time continually transferring data, wasting compute time there, it tries to store as much data as it can permanently on the GPU and does computing there. So instead of doing lots and lots of transferring, it pins that memory. And if you want to look up more about this, pin memory equals true, you've got the documentation. Otherwise, you can look up how to make deep learning models go brrr. And I'm being serious about that. Make deep learning go brrr from first principles. Brrr is as in your GPU is spinning really fast and going brrr. So Horace.io, brrr intro. This is how to speed up your deep learning models from first principles. Highly, highly recommend. Compute, bandwidth, in other words, transferring information. Yeah, see, this is what you want to do. You want to compute as much as possible, reduce the number of memory transfers. That's where pin memory equals true comes into play. And you can read more about that here. That's some extra curriculum for you there. But let's just save that. Pin memory equals true. Hopefully get a little speed up, maybe not with our smaller data set. That's more for larger data sets, but I thought I'd just make you aware of it because you're probably going to come across it in your PyTorch travels. Batch size equals batch size. We're not going to shuffle the testing data. So false. Num workers equals the num workers, not num workers. That's a great Linkin Park song, actually, num. And then pin memory equals true. Wonderful. Now, if this all goes to plan, we should have a train data loader and a test data loader and some class names, but it's going to save it to a script. So if we run this, overwriting, beautiful. Let's have a look at our updated file. Going modular, we have our first Python script. My friends, look at what we've done. We've got a Python script here. Do you know what we can do with this now? We can import this function and create our train data loader and our test data loader and our class names. So let's give that a shot, hey? What have we done? We've replicated these couple of cells up here. So that's working towards our goal of saving to Python scripts the most useful code cells of our notebook so that we don't have to keep rewriting them over and over again. So let's try this out. How about, where were we? We've got datasetup.py. Now let's go from going modular, which is our directory that we created, from going modular, import data setup. Run this. What do we get? Oh, beautiful. And now if we go data setup, do we have autocomplete? Create data loaders. Beautiful. Now, do we get a doc string with this? We do. creates training and testing data loaders. This is the doc string that we wrote. Takes in a training directory and a testing directory path. There's the arguments. See, this is why we write it in that specific style, because I like this style of formatting. Returns, example usage. We could really format that a little bit better maybe. But this is, where's that coming from? That doc string is coming from here. The one that we wrote. How cool is that? So maybe we format this a little bit more so it works better, but that's good enough for me for now. Let's see how it works, hey? Let's make our train data loader, test data loader, class names, traindir equals traindir, because we've already got traindir as a path and testdir, I believe. Yes, we do. Testdir equals testdir. What are the other parameters we can pass in? Transform. Transform equals data transform, which is the transform that we wrote above. So we can see this here. Data transform. Compose, we do a resize and we do a 2 tensor. This was just up here. We didn't write this section, but we wrote this previously. Create a simple transform. And then finally, I know I'm jumping all over the place, but we're going to bring this back in a second. Let's pass in a batch size. What should we use as our batch size? Let's say 32. And then num workers get set by default. So let's just do that. And then let's see what our train data loader looks like, our test data loader, and our class names. Woohoo! Have a go at that. Look, we're using data setup, the script that we just wrote, create data loaders. We've created a data loader, train data loader, test data loader, and now we have the class names, pizza, steak, sushi. Beautiful. So going forward, instead of writing the code that we've got above here, so instead of writing all of this stuff again and again and again, we could just leverage our data setup.py. We could save this somewhere and just import this script and create our data loaders by passing in a training and testing directory. How cool is that? So let's not stop there. Let's keep pushing forward. I'd like to do the same thing for the rest of the sections. So what are we up to? Making a model, tinyVGG. Now we've written the tinyVGG model a few times now. How about we turn this into a script? You might want to give it a go before we go to the next video. So try that out. See if you can turn this code cell into a script called modelbuilder.py. And we'll do it together in the next video. I'll see you there. In the last video, we created our first Python script, datasetup.py, to create our training and testing data loader, as well as return a list of the class names that we're working with. But let's not stop there. Let's now see if we can turn our making a model code into a Python script. Now this is the same model we used in Notebook 04. We've seen this before, so I'm not going to spend too much time as coding the model. I just want to focus on how we could turn it into a Python script. So if you want a step through of it, we have model 0 tinyVGG. This is where we created it in the previous section. But let's see what happens if we run this cell. And then if we run this one, creates an instance of our model. We've got a forward method. If we wanted to leverage the benefits of operator fusion, that'll be contained in that post that I showed before, how to make your deep learning models go brr. You could use that. Then we have device agnostic code. Then we do a dummy forward pass to make sure that the model works. And it looks like it does. So let's see how we can turn this modeling code into a Python script. So we'll come down here to the end of section 3, and I'm going to create a little text cell. And rather than rewrite all of our modeling code, so let's go call this making a model tinyVGG with a script. And we'll call this one modelbuilder.py. You can call it whatever you want. Sometimes you just see it saved as model.py. I'm going to call mine modelbuilder.py. And let's turn our model building code into a Python script we can import. So that's what we want to do. We want to be able to import our model from a Python script. So how do you think we could do that? Well, previously we wrote some code to turn our data set up using a magic function. So you might have already given this a go yourself. So we're going to write file, going modular, and I'm going to save it as modelbuilder.py. So that's going to turn whatever is in this cell into modelbuilder.py. So if we just print, hello, I'm about to build a model in here. Let's see what happens. Beautiful. Then if we have modelbuilder.py, there we go. Beautiful. Now, what if we just ran a Python? This is a Python program. So if we just go Python, going modular, modelbuilder.py, there we go. It does whatever's in that script. So ideally, we want to end up later on with train.py and it trains a model. But let's cover that later. We're up to here. So I'm going to put this into a string here. So this contains PyTorch model code to instantiate a tiny VGG model from the CNN explainer website, just as we've seen before in previous sections. So we're going to cheat a little bit with this one. Rather than rewrite all of our modeling code, let's just copy what's in this cell above here. I'll show you how quickly we can turn this into a Python script. So we import torch, from torch import nn, then we just have our class tinyVGG with a doc string here. We come down and we're just going to copy that there. Now, do you think that's enough? Well, let's find out, hey? So if we overwrite, going modular, modelbuilder.py, look what we have in there. Contains PyTorch model code to instantiate a tiny VGG model from the CNN explainer website. And there's all of our modeling code. So how about we try to create a model and we replicate what we've got up above here. We've got a single forward pass, but this time we want to leverage our modelbuilder.py script instead of our cell up here. So we have to replicate something like this. Let's see what this looks like. We'll go import torch. What we're trying to do is a dummy forward pass with the model that we create from modelbuilder.py, just to make sure that it works. So from going modular, import model builder. So this is going to import the model builder script that we just created. And then we can set up device agnostic code. We don't have to do this again, but I'm just going to do it anyway for completeness. If .torch.CUDA is available, else CPU. Beautiful. Now let's instantiate a model from the modelbuilder.py script. We can do this how? Well, let's find out, hey? Torch manual seed. We want to go model1 equals, instead of just writing plain tiny VGG, we can go modelbuilder.tinyVGG. And then if we look up, can we look up the doc string here? Oh, we haven't imported this yet. So if we just run that, .tinyVGG, there we go, look at that. Creates the tiny VGG architecture. Replicates the tiny VGG architecture from the CNN explainer website. Here's our args, input shape, hidden units, output shape. Where do we get this from? That's the doc string that's in here. Class tiny VGG. That's all I've done. I've written the doc string here in the style of Google docstring, Google Python docstring. All right, let's keep pushing forward. This is so exciting. Look how quickly we can create a model now. Hidden units, let's just stick with 10 like we've been using in previous sections. Then the output shape equals length of class names. And then we're going to send this to the target device. And then let's have a look at model 1. Do I have enough brackets there? I think I might need one more. Oh no, that's correct number of brackets. Let's run that. We get a tiny VGG model from our going modular script, model builder. How good is that? Now let's try a dummy forward pass. I'm just going to copy the code from up here just to make sure it works with the exact same code. This is a dummy forward pass here. We've seen what this looks like. All we do is we get a batch of images and we get a single image from the batch and unsqueeze it so that the single image fits the model, the shape fits its model. We want to perform a forward pass on a single image, but instead of model 0 that we created from within the notebook, we want to use model 1, which we created. We still created it from within the notebook, but we used the code from modelbuilder.py. So let's just make sure it works. And yes, it does. Woohoo! Look at us go. We are slowly but surely turning in, well, not even slowly, we're going quite fast. We are turning our useful notebook code into Python scripts. So do you remember how long it took us to first write this model? And we've written it a few times now, but now we've got it saved in modelbuilder.py. So we could just import this script and we have a tiny VGG model ready to go. And of course, you could use modelbuilder.py for any of your PyTorch models and use similar PyTorch code that we've written here, or Python code, to import it and instantiate it ready to go. This is the power of going modular. But we started with a notebook and we practiced writing functions like train step, test step, and train to see if they worked. And we used the notebook to experiment. This is my workflow. What I do day to day as a machine learning engineer is I try things out in a notebook, and once they start to work, I save them to Python scripts so that I can use my useful code over and over and over again. So let's keep pushing forward. You might want to try it yourself. We've got train step, test step, functions, and train. These are all from Notebook 4. Nothing different here. All I've done is I've added a doc string to each of them. You might want to practice writing these using Google's Python functions and methods style guide, as we've discussed before. Let's turn these 3 functions in the next video into a Python script called engine.py, because that's what drives our model training, right? These 3 functions. So let's call the script something relatable, engine.py. I'll see you in the next video. Over the last 2 videos, we've created datasetup.py, modelbuilder.py. Now it's time to move on to the next step, and that is turning our training and testing step functions and our train function into their own Python script so we don't have to rewrite all of these test loops over and over again. I know it is fun writing them, but we've done enough practice here, I think, already. Okay, so let's see how we can create a script called engine.py. And if you're wondering, for reference, all I've done is I've taken these functions that we wrote in Notebook 04. So if we come up here, Notebook 04, create train and test loop functions. There's train step, all of the steps with that, test step, and then there's train, which combines test step and train step. And I've added a doc string to each in Google's Python functions and methods style guide. So let's run this code. Oh, and by the way, if you're wondering what's going on here, they might be new too. If you haven't seen this before, this is your extra curriculum. It's Python type annotations. So that's just going to give people a hint, namely people who use your code in the future or yourself, as to what types these arguments should be and what gets returned. Now they're only hints, so they aren't going to really enforce it. They're just hints. So you can check out some resources for that. But it's just telling it, hey, this model is a type torch nn.module, and that this function is going to return a tuple containing 2 floats. So let's see it in action, hey? Run train step, and then we'll get test step, and then we'll combine test step and train step into train. Now you'll notice all I've done is I've added a doc string here. It's quite lengthy, but it's going to help later on if we wanted to look up what our code actually did. And then if we wanted to run that, beautiful. So we could write code here, train, and then pass in some parameters, a model, a train data loader, a test data loader, an optimizer, a loss function, epochs, and a device. But let's just see how we can turn this into a script called engine.py. What I'm going to do is I'm going to create a subheading here. This is 4.1. Turn training functions into a script. And this is going to be called engine.py. So you might have already tried this yourself. let's see one way of doing it. So we're going to use the Jupyter Magic write file, going modular, .engine.py. Now we want within our engine.py file to have access to the train step function, to the test step function, and to the train function. So let's see what this might do. We'll write a information, a heading about our Python script, contains functions for training and testing a PyTorch model. Easy as you like, right? And then we can put up the top, the imports. Just a thing to note that if you don't import the things within your engine.py script or whatever script that you're using, if you don't import the necessary imports, the necessary modules, your functions, your classes will error out. So that's what we're doing here. These functions require a few different modules from the typing module, from TQDM for progress bars, and yeah, typing tuple. So let's see what this looks like in practice. From typing, import dict, list, and tuple. That's going to help with our type annotations. Then of course we can import torch, and then from tqdm.auto, import tqdm for progress bars. Wonderful. So what can we do now? Well, we could rewrite all of our functions, but we've already done that. So let's just leverage the fact that we've written some great code up here, and I'm going to get this train step function. We don't need the import up the top there. So we'll scroll back down to our script where we're creating engine.py, and we'll give the first one, which is train step. Then we'll enter down to another line. I'm going to go up and get the test step. Beautiful. And then we're going to come down here, test step. And then finally, instead of rewriting the train function, we've already tested this in our notebook before. So we're just going to copy it down below. Wonderful. So this is our longest script here, but there's a fair bit of functionality going on. And so to save us rewriting all of this code over and over again, let's just save it to engine.py. And if we refresh, hey, look at that. So now if we go from going modular, import engine, and then if we have engine.train, what happens? Oh, train missing 7 required positional arguments, model, train data loader, test data loader, optimizer, loss function, epochs. Well, we're going to see how that in action later on, but now we've got access to our engine functions. So let's keep pushing forward. In the next video, how about we create a function to save our model? And we've seen how to save a model before, so you might want to charge forward and try to recreate this function yourself, or to focus on what we're covering in this section, try turning this save model function or this entire code cell into a script called utils.py, which is short for utilities. Give that a go, and I'll see you in the next video. Welcome back. In the last video, we created engine.py, our biggest script yet. Have a go at this. Remember how much time we spent writing all of our training code? Now look what we can do. Now, you might be wondering, Daniel, why didn't we do this from the start? Why didn't we just save all of our training code to a file and our testing code, all of that sort of stuff? Why didn't we save this to a Python file from the beginning? And well, we definitely could have done that, but the reason why I've spent so much time on these steps is because yes, it's one thing to just import functions from a file, but I thought we better practice writing the code before we just copy it and save it to a file and use it later on. So we've had plenty of practice writing all of this code now. So if we were to inspect our engine.py, well, we kind of know what's going on there. So let's get out of that. How about we work on creating a utilities.py or utils.py? So if we look up PyTorch state of the art, this is a recent PyTorch blog post for training state-of-the-art computer vision models. And if we look up in here, there's a script, a training reference script. You'll notice that this is the actual PyTorch GitHub repo. This is their vision, so torch vision, references, classification. We've got detection, segmentation, classification. Let's focus on that because that's what we're doing. they've got a train.py file. That's what we're working towards. There's transforms.py. We could create that if we wanted to, if we had some data transforms that we wanted to save to file. And then there's utils.py. So let's have a look at what's in here. Okay, smooth value. Is there a save method in here? I wonder. Save on master. Okay, torch.save. There we go. All right. But the purpose of the utils.py file is to save any utility functions. Yeah, there we go. Store model weights, which could be considered save model weights. Now, there's a fair few things going on here, but do you see how this has got a doc string in the similar style that we've got? Now, we're practicing a simplified version of this, but the principle is still the same. Take the useful code that you've been writing and save it to a Python file. Now, of course, you could just start with Python files, but for me, I find that I like starting with notebooks because they're so exploratory. You can experiment, and you can visualize. But I just want to reference that this is the style that the actual PyTorch team are using for their modeling code. So just keep that in mind, but we're going to create a utils.py to save our model. We'll get out of that. So if we run this gives us a function to save the model. So you can step through this code here if you like, but we've covered this in a previous section. Let's write another subheading here. Create a file called utils.py with utility functions. So utils in Python is generally reserved for various utility functions. And right now we only have one utility function, save model, but as our code grows, we'll likely have more. So that's just something to keep in mind. You can always update these Python scripts with whatever you like. You can create them using the write file magic as we've been doing, or you can just go in here and edit them by hand. So print hi. Then if you save that, it's going to override engine.py, but we actually don't want that. So I'll just save that back or comment that out. Just something to keep in mind. And let's copy all this in here, put it down there. You might have already done this before because I set this as a challenge, but let's create write file. I'm going to save this as going modular, and we'll keep this as utils.py. Let's put a little heading here, and this is a file containing various utility functions for PyTorch model training. And now again, we've only got one utility function, but as your code grows, you'll likely have a fair few other utility functions that you could put in here. So let's see what happens. Oh, if we run this, oh, going modular, utils.py. I love creating Python scripts. Look at that. Oh my goodness. Now, instead of, oh, you know what we're missing? We haven't imported Torch. That's a good catch. Thank you, Google Colab. So, as we've said before, you have to make sure that your scripts import the modules that are required for your various code and functions that are within that script. So let's rerun that again, overriding, and then we get a new utils.py, open it up, and now that it imports Torch, we don't get that red squiggly line. Beautiful. So let's keep pushing forward. We've now got to train, evaluate, and save the model. Oh my goodness, we are almost at the train.py script. So, in fact, that can be your challenge for the next video. Try to turn this train, evaluation, and saving model code into a script that is train.py, just as we've created here, but with all of this functionality built in. So that ideally, we can finish off by running Python, going modular, train.py. And it's going to train a model that is going to result in something like this. So give that a shot, and I'll see you in the next video. We'll create a train.py script. We've created 4 Python scripts so far: datasetup.py, engine.py, modelbuilder.py, and utils.py. Now it's time to leverage all the code that we've written before and create train.py. But let's see what happens in here. You might have already tried to replicate this into a train.py script, and if you have, well, kudos to you. Otherwise, that's what we're going to do now. So we set some random seeds for reproducibility. We don't necessarily need to do that. We set the number of epochs to 5, nice and simple, keep our training time short just to make sure our code works. We create an instance of tinyVGG. Note that this is not using the tinyVGG from modelbuilder.py. It's using it from the code cell above. We set up a loss function and an optimizer as we've seen before. We start the timer to time our model training code, and we train model 0 using our train function, which does a train step and a test step. Then we have an end timer, and finally we save the model using our save model code. Now, how would we replicate this using all of the functionality that we've saved to our Python scripts? Well, let's see. This is what we want to end up with. Something like this. Python going modular, train.py, and train.py leverages all of these other Python files to replicate the code in this cell. So I'm going to create another section here, which is 6.1. I'm going to call this train, evaluate, and save the model. And this is going to be script mode. And we want to call it train.py. So let's create a file called train.py to leverage all of our other code scripts to train a PyTorch model. Essentially, we want to replicate the functionality of notebook 04, because remember, all of the code in this notebook is a conjunced or a summarized version of the ones of the code in notebook 04. All of the functionality of notebook 04 in one line. So let's see. I'm going to create, using write file, going modular, train.py, and what should we say that this does? This trains a PyTorch image classification model using device agnostic code. I think that's pretty good. Again, you can put whatever you want here, whatever's descriptive of whatever problem you're working on. So we're going to need a few things. We need OS and we need Torch. Remember, whatever modules we need to run this code here, we're going to need in our train.py file. And so we're going to import Torch Vision because we need to create a transform, import transforms. And I'm also going to import data setup. Now, I don't have to put going modular here because train.py is going to be within going modular. So that's something to keep in mind for file paths. So because train.py will be inside going modular, I can just import data setup instead of writing like we have before. Instead of writing from going modular, import data setup, I can just write import data setup, and that will get that module. The same thing with engine, the same thing with model builder, and the same thing with utils.py. That is because train.py will be inside this going modular file. So let's get rid of that. Let's just run that. Beautiful. And let's set up some hyperparameters. And I'll just show you. We refresh. So train.py is inside going modular. So that's why we can just straight away import data setup, engine, model builder, and utils. So we set up the hyperparameters. Num epochs equals 5. And then we go batch size equals 32. And then we go hidden units equals 10. And then we'll set the learning rate equals to 001. We can keep going on. We'll set up the directories. So traindir equals, we'll go data dot pizza steak sushi slash train, and then we'll set up the test directory equals data pizza steak sushi slash test. Beautiful. Now let's set up device agnostic code. Now, the wonderful thing is that because all of our other code leverages device agnostic code, we set it up once here, and then all of our other code falls into place. That's what we've been working towards this whole time. Else the CPU, and then we're going to create transforms. Now, we don't necessarily have to create the transforms in train.py. You could create a transforms.py and import it, but for simplicity, we're just going to create one here because our transform is actually quite straightforward. It's a resize and then a 2 tensor. But if you wanted to create multiple transforms, you could do that within a transforms.py file if you wanted to. What did we get wrong here? Oh, transforms. Excellent. Now we can create our data loaders. So create data loaders and get class names. How can we do this? Well, we created a function in data setup to do just that. So train data loader and test data loader and class names equals, we're going to use data setup. Recall within data setup, we have create data loaders. Beautiful. So we're going to go data setup.create data loaders. And we're going to pass in the train dir, which is equal to train dir, which is what we've set above, train dir here. And then we can go test dir, which is equal to test dir. We've set that above as well. Then we can keep pushing forward. We have transform, which is equal to data transform, which is what we just created above too. Data transform. Now we have batch size, which is equal to the batch size parameter that we've set above, hyperparameter that is. And then num workers, we don't have to set number of workers because it automatically gets set within datasetup.py. What's next? Well, we can create the model. So let's create the model. All we're doing is we're replicating what happens here. So in this code, the data is already created, but in our script, it's not yet created. So now we're up to here. We recreate an instance of tinyVGG. So let's do that. Create model. We can just call it model equals model builder. Now, this is beautiful. We can just leverage our tinyVGG class from within our model builder script. I'll set the input shape to 3 for color channels in our images. I'll set the hidden units to hidden units. And then we'll get the output shape here. Now, the output shape is going to be the length of the class names because we've got that above, which will be 3 because we have 3 target classes, pizza, steak, or sushi. And I'm going to send this to the target device with the device agnostic code. And now what do? Well, as we have done plenty of times before now, set up loss and optimizer so we can use this in our training loop and our testing loop, of course. So the loss function, because we're working with multi-class classification, will be cross entropy loss. And our optimizer will be, well, we could use a few different options here, but I'm going to stick with Atom. And we want to optimize our model's parameters, and our LR learning rate is going to be learning rate, the hyperparameter that we set above here. Now, of course, you might have guessed that these could all be argument flags. Now, if you didn't guess that, that's completely fine, but that will be one of your extracurriculum exercises, is see how you can use Python's argparse to turn these into argument flags. But more on that later. Let's keep pushing forward. Set up loss and optimizer. Now let's start training with help from engine.py. So engine.train, let's pass in the model. Model equals model. Now where does .train come from? It comes from engine. If we go down here, this is our train function. We have to pass in a few things here. We've written all this code before, so we're leveraging it in train.py. We're linking together all of the pieces of the puzzle. Train data loader equals train data loader, which will be this one up here. And then the next parameter is the test data loader equals test data loader. Wonderful. And then we pass in our loss function, and then the optimizer. And then what else? Well, we have epochs, num epochs. This is another hyperparameter that we set above, num epochs. And we can keep pushing forward. What's our final thing? Device. So we can leverage device agnostic code. And then one more step. What do we do as the last thing here? Save the model. Oh, we haven't got timing, do we? Well, let's just copy in some timing down here. And we'll go here. Timer. And end the timer after the model training. And then we need to make sure that we're importing timer. Oh, we do it there. I might just put this up the top. And we can go this here. Beautiful. Okay, one last thing. Save the model to file. And what can we do here? We can go utils.save model because we've imported utils up here. And within utils.py, we have save model. Excellent. So utils.py, save model, and then we pass in the model we'd like to save. And then we pass in the target directory we'd like to save it to. Let's save it to the models directory. And then we will set up a model name. And we'll call this one 05 going modular script mode tinyvgg model.pth. Now, you could also do .pt or pth, which stands for PyTorch. Oh my goodness, look at this train.py script. Are you ready? Let's save it, see what happens. Overriding going modular train.py. One of our biggest scripts yet. Trains a PyTorch image classification using device agnostic code. We've got our imports, we've got our hyperparameters, we've got our directories, device agnostic code, our transform, our data loaders, our model, our loss and optimizer. We start the timer. We train the model using our engine script, we end the timer, and then we save the model to file. Oh my goodness. Let's see, can we do what we set out to do at the very start of this section? Can we train our model with one line of code? Mind you, this is going to be one line of code, but it's going to leverage all of the other code that we've written here. Over the past, however many sections we've been through, what are we up to? Section 5? We started at 0, so 5 sections prior to this one. We've written a lot of PyTorch code, and now we're going to condense it into a single line. Are you ready? Let's go modular in 3, 2, 1. No errors. Oh my goodness, we're training. Here we go. Oh, look at that. Look at it go. There we go. Epoch number 1. Epoch number 2. Epoch number 3. Epoch number 4. Oh, look at that. We get a printout. And finally, we get to save our model to models 05 going modular script mode tinyvgg. And if we look, we refresh this, we now have a models directory. Beautiful. Well done. So that whole time we were working towards training our model with a single line of code, a train.py script. And we did it. Now let's have a look at our final directory structure. We have our data, which is our standard image classification data. We have our Python scripts, which is all of our PyTorch code and Python code that we've written across various different sections, but now condensed into 5 scripts that we could just import. Look what we did to import those scripts. Within the train.py, we just imported them with one line. And all of that training loop code happened with engine.train. How good is that? And now we have a directory to save our models. And so I want to emphasize the fact that the data folder here, that can be whatever data you're working with. And these going modular scripts, the data setup.py, that can be whatever code you need to set up your data. The engine, you might have quite a similar engine to what we have for training and testing loops because the steps are quite similar. The model builder, you could customize this to be almost any PyTorch model that works with the data that you're using. Utilities? Hey, the sky's the limit there. We only have one utility, but there could be many more. And then finally, models here. We have our saved models. So give yourself a pat on the back. We have written a lot of code here, and this is a very important step in becoming world-renowned machine learning engineer, is being able to go from notebooks to Python scripts. So let's in the next video do a quick summary and talk about some extra resources / exercises to practice what you've learned. Welcome back. In the last video, we created train.py, a script that leverages all the other scripts, and all these scripts leverage all the code we've written throughout all of the other sections so far to train our PyTorch model in a single line of code. How cool is that? And so what we've done is we've gone modular. We've gone from working notebook code to working Python script code. And if you want to compare, see what we've done, we took part one of going modular, so the notebook in cell mode, and we turned it into script mode. But I'm not going to spend too much time talking about the comparisons between these two. I'd rather you investigate that yourself. But just know what we've done is we've taken part one and we've essentially turned it into part two. But if you'd like to learn more, what I'd recommend is extracurriculum, is to go back through section 5, PyTorch going modular, have a read through this. This is everything that we've done so far. It explains why you'd like to go modular, the pros and cons of notebooks versus Python scripts, an example of what I do, my workflow. So we've just gone through my exact workflow. I use Google Colab to explore different options, see if some code works, and if it does, I turn it into a Python script, just as we've done. And you'll often find PyTorch code in the wild in the form of scripts. So that's why it's good to be familiar with script mode PyTorch code. And there are some things that we didn't quite cover just yet. So that's argument flags like this for training with different hyperparameters. But that's actually the first exercise. So if we come down to exercises, one of the exercises, the second exercise. So the first one is to turn the code from get data, section 1. So maybe you could turn this into a script. We didn't do this. Get data. You might be able to turn this into a script. I'll leave that as a challenge for you. Give you a hint. You can use very similar code to what we've used to create these scripts. And then exercise number 2 is use Python's argparse module to be able to send train.py custom hyperparameter values for training procedures. So this is a little bit of a tricky one, but I think that you can figure it out. So if you look up Python argparse, you want to see how to use this module from Python to create arguments that you can pass to your Python programs. So I'd recommend the documentation for that. I'd also recommend Real Python argparse guide. How to build command line interfaces with Python in Python with argparse. So that's another resource that you can check out. So let's go back here. And then finally, create a script to predict, such as predict.py on a target image, giving a file path with a saved model. So in the last section of section 04, we predicted on a custom image. So the final exercise is to take the code that we used in this section and turn it into a script called predict.py so that you can predict on your own custom image. So I feel like these are some good challenges. Now, of course, if you want an exercise template notebook, there's one in the PyTorch Deep Learning repo under extras/exercises/05 PyTorch going modular exercise template. There is also an example solutions notebook with some solutions to the exercises under extras/solutions. And then of course now I've started to have live walkthroughs of each of the exercises in recent sections of me going through and solving them live. So if you want to check out that, how I would solve the exercises, you can check out the full video on YouTube there. And then finally, to finish off, if you want some more information about things that we've covered in this section, PyTorch going modular, I'd highly recommend going through the extracurriculum, particularly if you want to learn more about structuring a Python project. Like for example, how should you structure the files within going modular. So why did I put going modular, and then have Python scripts in here? How should you structure these? This article is going to help you out. If you want to look at more style information about styling your PyTorch code, I'd highly recommend checking out this PyTorch style guide by Igor Sasmilij. I'm pronouncing that name wrong, but it's what I've used to inspire the styling of the PyTorch code in this notebook, as well as various other resources. And then finally, we've seen this one, but for an example train.py script to train state-of-the-art image classification models, check out the PyTorch repo. Now, there's a fair few things that we haven't covered in this train.py, but there's a lot of things that we have. So I'd encourage you to read through this. Even if you don't understand some things, it's going to give you an idea of what you could work towards to start training state-of-the-art models. So our model is quite small at the moment, but this model, or this training code here, is what trains PyTorch image models to state-of-the-art results. So with that being said, find everything you need and learn pytorch.io section 05 or the GitHub repo here. But this has been Going Modular. I will see you in the next section. Ooh, it's going to be an exciting one. If you thought training a PyTorch model with one line of code was exciting, well, our model's not performing very well. How can we step that up a notch? I'll give you a hint. It's in the next section. I'll see you there. Hello and welcome to Transfer Learning with PyTorch. Now, this is one of my favorite topics in all of machine learning, so let's get started. First of all, where can you get help? Number one is to follow along with the code. PyTorch Transfer Learning, we're going to go through Google Colab and we're going to be writing code together. Remember the motto, if in doubt, run the code. Try it for yourself. Press Shift Command and Space to read the docstring, but if you find it's hard to read in Google Colab, you can always go to the PyTorch documentation. And if you're still stuck, well, you can ask a question on the course GitHub discussions page. If you come in here, it's pretty empty right now because the course isn't out yet as I record this video, but you can click New Discussion, put in your info there, and then someone can help you out here. And of course, we've got the course GitHub with all of the materials. This particular notebook is going to be number 6. Right now, as I record this video, there's 2 versions of this, but by the time this video is out, it's only going to be 1 version. I've made 2 versions because what we're going through uses the latest PyTorch versions, so I had to upgrade the original one. And then we've got all of the course materials, and then of course, we've got learnpytorch.io, which is the book version of this course. See how we've got V2 and this one doesn't have a V? Just by the time this comes out, it'll only be 1 version. I had to make V2 because this is the updated version of what was originally going to be in there. So without any further ado, let's get into the keynote. You might be asking, what is transfer learning? Now, we've built a few models so far, but you might be thinking as well, surely someone has spent the time crafting the right machine learning model for the job. And in fact, that's exactly what transfer learning is. So let's have a look at some examples. So we're working on a computer vision problem, and we are because we're working on Food Vision Mini right now, a neural network to take photos of food and classify them. Now, what if you had a large data set of images? For example, there's a data set out there called ImageNet, and a lot of people have trained computer vision models on ImageNet, and in fact, there is actually a challenge, well, there was a challenge until it sort of neural networks got too good for ImageNet. This one has close to 14 million or just over 14 million images, but the traditional ImageNet dataset has just over 1 million images of 1,000 different types of classes. So you train a neural network on that, and then what if we could use the patterns in that neural network that is trained on 1 million images, but then customize those patterns for our own problem, specifically for Food Vision Mini? So that's an example of transfer learning. You're taking what one model has learned, for example, a computer vision model, on a large data set like ImageNet, and then customizing it for your own use case. And so if we look at natural language processing, which is the idea of using a model to find patterns in natural language text, or natural language full stop, what if we had a neural network that is trained on all of Wikipedia to create a language model. Then we could use what that model has learned about the structure of language itself. So, for example, where a certain word should be in a sequence of a sentence, such as the word, the something jumped over the fence. The something will be more than likely be a dog than a car, for example. Then we could customize that model to make a spam engine to predict, is this email spam? Well, I don't think it is because, hey, Daniel, this deep learning course is incredible. Wow, thank you so much for the kind words. I can't wait to use what I've learned. Feel free to send me that email if you want. That is my actual email. But this is spam, so if you try to send me this email, actually, try to send me this email and see what happens. So I want to see if that actually gets classified as spam. But the overall pattern here, what we're seeing with transfer learning, well, the main takeaway from transfer learning is we take what one model has learned on one data set, usually a large data set. The term is pre-train that model on that large data set, such as all of Wikipedia, or such as all of the images in ImageNet. And in fact, there are larger data sets out there now than just ImageNet or all of Wikipedia. So our model learns patterns / weights / parameters from a similar problem space to our own. And then the power of transfer learning is that we can use these pre-learned patterns and we can tune them to our specific problems, such as using the ImageNet weights for Food Vision Mini, or such as using the language model from a model reading all of Wikipedia to create a spam or not spam email engine. So let's keep going forward. Now, I've kind of hinted at this question already. Why use transfer learning? Well, let's start with a couple of dot points. You might have gathered this. We can leverage an existing neural network architecture proven to work. So when we built TinyVGG, we were crafting a neural network architecture layer by layer. So the benefit of using transfer learning is that typically some smart researchers have already crafted neural network architectures proven to work on problems similar to our own. So that is one of the main key benefits of transfer learning. And of course, if we leverage a working neural network architecture, we can also leverage the existing learned patterns on data similar to our own. And so this, as we'll see, often results, oh, well, that's a spoiler. Oh my goodness, Daniel, don't give away all the tricks yet. Often results in great results with less data. So that's the power of transfer learning. Use an already existing neural network architecture, proven to work, and because it has already learned some patterns, if we adjust those to our own problem, we can often get great results with little data. And so, here's this in a graphic form. We learn patterns in a wide variety of images. So that gives our model an underlying understanding of the structure of what's generally in an image. So for example, a pre-trained EfficientNet is a computer vision architecture. It already works really well on computer vision tasks. And so we might want to extract those pre-trained patterns from EfficientNet and tune them, the patterns / the weights, to suit our own problem. Food Vision Mini. This is what we're going to be building throughout this section. And so, ideally, if we do that, if we extract the patterns from a pre-trained model, our model that we've tuned to our own use case performs better than a model just trained from scratch, such as what we did with TinyVGG. And so, another reason to use transfer learning, this is a recent research paper, How to Train Your VIT, which stands for Vision Transformer. And I'll let you read through the whole paper if you'd like to, but I'm not going to read this verbatim. If you're interested in being a machine learning practitioner, this is the most important line here. Most practitioners, however, rarely if ever perform pre-training on today's largest data sets, but instead use some of the many publicly available parameter sets. And that is the beautiful thing about machine learning, is that there are so many places now where you can find publicly available parameter sets. And what they mean here is you could swap this out for publicly available pre-trained models. So if you're interested in being a machine learning practitioner, you'll be looking for places where you can find publicly available pre-trained models. There's another quote from this same paper, which is more about the results. So we conclude that across a wide range of data sets, this paper explored how to train a vision transformer model with data augmentation, regularization, and a whole bunch of transfer learning. So we conclude that across a wide range of data sets, even if the downstream data of interest appears to only be weakly related to the data used for pre-training, so recall that we said ImageNet a whole bunch of images. We can use that for our food vision problem. Transfer learning remains the best available option. Oh, that is beautiful. I love that line. So even if your downstream data, your custom data, so your custom problem of interest appears to only be weakly related to the data the model was used on pre-trained, transfer learning remains the best available option. And I'm going to finish here with one more quote of why to use transfer learning. I'd rather see this in action. This is from the video, "Most research in deep learning is a total waste of time," by Jeremy Howard from AI Podcast with Lex Friedman. Now, watch the whole clip or the whole video to get this. This is a little bit out of context, but this is the quote I've ripped from this video. "The things that really make a difference, transfer learning, if we can do better at transfer learning, it's this world-changing thing. Suddenly, lots more people like us can do world-class work with less resources and less data." Now, that is from Jeremy Howard, the founder of Fast.ai, one of the best places to learn AI on the internet. So that's enough of why use transfer learning. Oh, actually, one more. Do you remember our improving our model slide from a few sections ago? I can't remember how far we've come. We've come a long way. So the method to improve a model, reduce overfitting, we could add more data. We could use data augmentation. We could use better data. Or we could use transfer learning. So we could take an existing pre-trained or pre-learned patterns from one problem and tweak them to suit your own problem. Now, okay, that's enough. I've spoken too much about why use transfer learning. Let's, in the next video, cover a few places where you can find pre-trained models. I'll see you there. So we covered in the last video what is transfer learning and why use it. The main reason, suddenly lots more people like us can do world-class work with less resources and less data. So we've talked about pre-trained models. Where do you find pre-trained models? Well, the first place is the PyTorch domain libraries. Then we've got Torch image models. Then we've got the Hugging Face hub. Then we've got papers with code, state of the art, and there's probably even a few more that I'm missing here. But this is more than enough to get started. In fact, we're going to be focusing on just pure PyTorch domain libraries. So if you go into the PyTorch documentation, you can go to different sections such as Torch Vision for vision models, Torch Text for text models, Torch Audio for audio models, and Torch Rec for recommendation models. So let's have a look at the vision. If we go in the PyTorch documentation, docs, we've got PyTorch, Torch Audio, Torch Text, Torch Vision. Here we are at Torch Vision. We've got models and pre-trained weights. Now, this is version 0.12 of Torch Vision. This module that we're working on uses currently, as of the time of recording, it is June 24, 2022. We are going to be using, if you come over to here, the most stable release at the time of recording is 0.12, but we are going to be using an unstable release, an updated version of Torch Vision. However, by the time you go through this will probably be out of beta. That's why I'm recording it now, so that you use the latest and greatest. But if we come down to models and pre-trained weights, we have a whole bunch of pre-trained models that we can use. Using the pre-trained models, this is what we're going to look at when we start writing code. Here's classification. So what problem are we working on? We're working on image classification of different types of food. And we've got AlexNet, ConvNext, DenseNet, EfficientNet, EfficientNet B2, or V2, sorry. MobileNet, MobileNet V3, Swin Transformer, Vision Transformer. Look at all of these models just right at our fingertips. How beautiful is that? Now, don't worry too much about the names of these architectures. They are really just names, but you can access all of these using PyTorch code. And if we go back to the keynote, there's some other magical places such as Torch image models, the TIM library. That's a beautiful library for computer vision. Then we have the Hugging Face hub, which is quickly evolving to be the place to go for a pre-trained model on almost any task you could imagine. There's image classification. And if we clear that, there's image segmentation. There's translation. There's token classification for natural language processing. There's sentence similarity. There's audio classification. So that's a beautiful place you can find pre-trained models as well. Now, of course, we're focused on PyTorch. So you've got Torch Text for text problems, Torch Audio for audio problems. I'll let you explore these on your own time because we're going to be focusing on Torch Vision. But if we come in here, it's a similar setup, Torch Audio documentation. If we go model, torchaudio.models, there we go. Beautiful. And so we'll go back one more resource, which is Papers with Code SOTA, which stands for state of the art. I know when I first got into machine learning, I'd read SOTA a lot. It stands for state of the art, so the best performing type of research. Now, if we go to paperswithcode.com/SOTA, this is going to be browse state of the art. Here's where you can see the latest and greatest machine learning research for different problems. Computer vision, image classification with all different benchmarks, natural language processing, medical, methodology, miscellaneous, time series. So this is when you start a machine learning problem, I would highly recommend you go to one of these resources and look at what already works so that you have a bit of a warm up. You have a head start on getting started on your own problem. So keep these in mind, these resources, where to find pre-trained models. Because we're just focusing on pure PyTorch, we're going to stick with the PyTorch domain libraries. But these are all valuable resources as well, and there's probably a few more that I've missed. If you have any you'd recommend, leave a discussion on the GitHub discussions for this course. And let's finish off what we're going to cover broadly. Getting set up. We don't want to rewrite all of our code from scratch. We're going to import our previously written code from other sections, especially the going modular section. We'll introduce transfer learning with PyTorch code. We've looked at it already from a conceptual point of view, but you know I like to learn hands-on, and I hope you do too. We're going to customize a pre-trained model for our own use case, Food Vision Mini. That is our goal throughout this entire course, is to make Food Vision Mini the best possible image classification model we can. We're starting with a data set of pizza, steak, and sushi. We're going to evaluate a transfer learning model, and we're going to, of course, make predictions on our own custom data and how, well, we're going to be cooking up lots of code. And with that being said, let's code. Okay, time to start coding. I'll meet you over in Google Colab. Let's go colab.research.google.com. And while that loads up, I just want to show you the resource we're going to be using for this section. So right now, at the time of recording, there's two versions of this. A little bit confusing because while I'm writing this, Torch Vision v0.13 is still in beta. So I'm kind of banking on the fact by the time this course comes out, it's out of beta, but I've set it up so that it'll work regardless. So we've got PyTorch Transfer Learning. We're going to be using the V2 notebook. Just again, by the time you watch this, the V2 might not exist. So just refer to PyTorch Transfer Learning as it is. So this notebook is a cloned version of that. So all this notebook is the same as this, but with updated code, and it requires the nightly versions of PyTorch and Torch Vision be installed. So that's all you need to know. We're going to write code to fix all of this anyway. So I'm going to start a new notebook in Google Colab. Wonderful. I'm just going to zoom in here. And I'm going to call this 06 PyTorch Transfer Learning. And I'm going to just use the video tag here so that you know this video was created from the video. And let's make a little heading up here. 06 PyTorch Transfer Learning. And we go, what is transfer learning? Give us a little note. So transfer learning involves taking the parameters of what one model has learned on another data set and applying them to our own problem. A very powerful technique. And just some nomenclature. So pre-trained model, you might also hear these days, a lot of people are calling them foundation models. So I use pre-trained model quite often, but you can also hear foundation model. The term is, they're interchangeable. As I said, machine learning uses a lot of different terms for the same thing. So I want to make sure we're using GPU code here. So I just went to change runtime type. And now we're going to get set up to make sure that we're using, if we go to Torch Vision, the documentation, we want to make sure right now, as the time of recording, version 0.12, we don't want to use that version. We want to use the latest and greatest version, specifically v0.13, which is going to, the latest version at the moment is 0.14, but we want 0.13 plus. So this has got some updated APIs that we want to use, specifically the multi-weight API. support. I'll let you read this blog post if you want. What this is going to enable us to do is use multiple different models. When it says weights, pre-trained weights, they are patterns a model has learned on another data set. So Torch Vision's new multi-weight support API allows us to use multiple of the same architectures with different weight setups. Now, we're going to get hands-on with this later on, but this is why we want to use this latest and greatest version, because it had an upgrade to the last version. So the way we can check the PyTorch versions that we're using: import Torch, import Torch Vision. So if you have, I'll just write down here, we're checking the versions of what we currently have. If you have Torch Vision version 0.13 plus, you don't have to do the next step we're about to do. So want 0.12 plus, or sorry, 1.12 plus, and we want for this one, we want 0.13 plus. Let's see what versions we have. Yeah, there we go. So I currently don't have the version of Torch Vision that I'm after, and I also don't have the version of Torch that I'm after. So we can go to PyTorch Getting Started. And if we wanted to upgrade, we can start locally and we can go preview nightly. So this is going to give you the latest and greatest versions of PyTorch. They are generally unstable. So the stable version is this, but also they get to a point where an unstable means they may have errors, but they also get to a point where the nightly versions are pretty darn good and they're basically about to be stable, which I think is the case with the versions we're after. So with that being said, I've got a block of code here. If you have, I'm going to copy this. So this is from V2. It might be in PyTorch Transfer Learning. So just keep that in mind. It might not be V2 by the time you watch this. But if these versions are already 1.12 plus and 0.13 plus, you don't need to run this next block of code and you can skip the rest of this video and go to the next video. So I'm going to run this. What it's going to do is try to import Torch and Torch Vision and assert that they're a different, or that they're a specific version number. And if they're not, they're going to install, we actually don't need Torch Audio. They're going to install the upgraded versions of Torch and Torch Vision from, we're using the code here. We want pip, there we go. It's using very similar code to what's going on there. So I'm going to run this. It's going to fail the exception. So it's saying info, Torch Vision versions not as required, installing the nightly versions. So I'm going to let this run and install the nightly versions of Torch and Torch Vision. It may take about 4 to 5 minutes or so, depending on how fast the Colab internet connection is to pip. But I'm going to let this run and I'll be back once it's finished. Alrighty, it looks like it's worked. So if we go back through here, we've just got some downloads happening with all the new versions of Torch and Torch Vision that we're after. It uninstalls the existing installations and then installs what we're after there. And so if we're using Google Colab and we've just installed some new packages, we have to restart the runtime. So let's restart the runtime. And then if we run both of these after this is finished restarting, we should have the nightly versions. Beautiful, there we go. It's called dev version there. And there's the date of when the dev version was created. And we've got Torch version 1.13 and 0.14. This is okay because we just want 1.12 plus for Torch and we want 0.13 plus for Torch Vision. And now if we run this, it should pass the assertions. Beautiful. So we've got Torch version and Torch Vision version there. So just keep in mind, if you run this little block and you have the versions that are compatible with this notebook, you don't necessarily need to run this. But if you do come back to this notebook at a later time and you don't have these versions installed, you do have to run this block of code for the later versions of the API to work. So eventually Google Colab will have these versions by default, but just for now, we need to run something like this to install upgraded packages. So let's move on to the next video and we'll get even more set up. We'll import some of the code we've written in previous videos into this notebook. I'll see you there. Welcome back. Let's continue with the setup. So to prevent us from rewriting all of the code that we've written over the last few sections, let's write some notes here. Now we've got the versions of Torch and Torch Vision we're after. Let's import the code we've written in previous sections so that we don't have to write it all again. So if you recall in section 5, which is going modular, we've got PyTorch going modular there. The whole premise of that section was to turn our most useful notebook code and we put it in the going modular directory. And we have going modular. And we have these scripts here: data setup, engine.py, modelbuilder.py, predictions.py, train.py, utils.py. Predictions.py is actually quite a new one, but that's okay. We want these scripts in our notebook. So we want them available here. So we can do that by cloning this GitHub repo, then sorting it out and making sure we have access to the going modular directory over there. So if we go to, this is PyTorch Transfer Learning. Note, this might not be V2 by the time you watch this. It might just be PyTorch Transfer Learning. It will have the same sections. So we're going to go to getting set up. We've already written this block of code here. You might not have needed to if Google Colab has updated to have the Torch version and Torch Vision versions that we needed. But now let's get started with our regular imports. So I'm going to copy this here rather than rewriting all of this. And we'll also set up device agnostic code. So I'm going to copy this in here. And what this is going to do is import all of our regular imports that we've used so often. And it's also going to try and get a few packages such as Torch Info. Torch Info is a great way to get printouts of our model, view summaries in PyTorch. This is a package here, available on GitHub. If we print a summary of our model, we want to get something like that so we can inspect our models. That's going to come in handy later on. And it's also going to try and import the going modular directory. And if it doesn't exist already in the Google Colab notebook, which it won't, it's going to download it from GitHub using this code. So git clone, then it's going to move the PyTorch Deep Learning going modular into the current working directory with the dot. Then it's going to remove all of the extra files we don't need from PyTorch Deep Learning. And then it's going to, from going modular, import data setup and engine, which are these two scripts here, engine.py and data setup. Contains functionality for creating PyTorch data loaders for image classification data. We wrote this in the going modular section, so section number 5. And the same thing with engine.py, contains functions for training and testing a PyTorch model. We've got train step, we've got test step, and we've got train. So rather than rewriting this every single time we start a new notebook, it's very helpful to put them in helper scripts like what we've done. And so this is just one way you can get scripts from, say, a GitHub repository into your notebook. So let's run this. See what happens. It couldn't find Torch Info. So it tried to import Torch Info, and that doesn't come by default with Google Colab. So it's going to import Torch Info for us, or install it with pip install, and then it's going to import it. The same thing with going modular here. It's going to try and import the going modular scripts, and if this try block doesn't work, it's going to download them from GitHub. So we've got cloning into PyTorch Deep Learning. It's copying all the objects. Now if we come over to here, we've got the PyTorch Deep Learning repo. That won't be just updated quite yet, but that's going to copy everything from here. We don't need everything from here. We're just after the going modular folder. So we'll come back. I'll just clean up these tabs. We'll wait for this to run. Beautiful. So it's downloaded all of it and resolving deltas, checking out files. Beautiful. So now if we refresh this, look at that. That is magical. We've now got going modular. We've got going modular. And we've got the scripts that we're after. So we've got data setup and we've got engine. So if we wanted to go data setup dot create, is it going to give me autocomplete? Create data loaders. There we go. And if we wanted to go engine.train, do we have access to engine.train? Yes, we do. And if we look into engine.py, I nearly said engine.train, we have the train function that we wrote in the last section. So that's the whole reason we're doing that. So we don't have to rewrite all of that code there. And now we just want to make sure we have a GPU. So a few steps to get set up here, but once you've done this a few times, you'll know what to do when you're starting a new notebook. So set up device agnostic code. And if we were working locally, like on our local machines, we could have all of this already set up. But the reason we're continuing to use Google Colab is because we get a free GPU. Not everyone has access to a GPU on their local machine. So set up device agnostic code, CUDA.is available, else CPU, and we'll check the device. We'll make sure we have a GPU. Beautiful. And you can check what GPU you have with NVIDIA SMI. So I have a Tesla P100, which has 16 gigabytes of memory. That is a great GPU. Because I pay for Google Colab Pro, you don't necessarily need Google Colab Pro, but just I use Google Colab Pro because you're more than likely going to get bigger, faster GPU than if you use the free version, because compute isn't free. And so Google provide Colab for free, but if you use the free version, you don't necessarily always get the fastest GPUs all the time. That's just something to keep in mind. So we've got our notebook set up. We're ready to do some transfer learning. Just keep in mind, if you take a break and come back to your notebook, you will have to rerun these import cells and getting set up cells. But we are ready to go. Let's now, in the next section, we're going to get some data. We need our pizza, steak, sushi data to build a transfer learning model on. So I'm going to leave that there, and I will see you in the next video. Welcome back. Let's now get our data. And I've just realized that, silly me, we did actually clone the PyTorch deep learning repo, which is up here. And we want the data that lives in the data folder, which is the pizza, steak, sushi zip file. We could go to get this raw URL. So we could copy that link address, bring it in here, and do something like wget that, download it. Or we could have just, instead of deleting everything except for the going modular folder, we could have just got it there. But there is some code that we've written, very similar to what we've done before, to download the data from an external resource. We're going to rewrite this just for some practice, but you could always just copy it from here. Or as a little extension challenge to you, you could turn this into a function called download data. Or another little extension is, instead of removing all of the PyTorch deep learning repo when we clone it, keep the data folder as well as the going modular folder. So that would be modifying this set of lines here. But for now, let's just do it the tried and true way that we've done it before by importing OS and then importing zip file. This is good to practice anyway, even though we've done it a couple of times now, because you often will have to download data or download something from external resources. So we'll import the request module, we'll set up the data path, and then we'll set up the image path as well. Equals path from Python's path module. So that's going to be our data path. Then we'll set up the image path, which is going to be where our pizza, steak, and sushi images live. Pizza, steak, and sushi. And just a reminder, these are images from a subset of classes from the Food 101 dataset. So we're starting small. That's why we're working on Food Vision Mini. And so if the image folder doesn't exist, we want to download the data from GitHub. Download it and prepare it. ... So if image path dot isdir, we will go, so if this path is a directory, it already exists, we will print out F, and then we'll go image path, directory exists, skipping, re-download. Nice little printout there. What have we got wrong there? Oh no. Else, if it doesn't exist, so if it doesn't exist, if it's not a directory, we want to download it. So let's print out another message here. Did not find image path, downloading it. So then we'll go image path.mkdir. So for make directory, we want to go parents. If we need to create any parent directories, we'll create those as well. And if it already exists, a directory named image path with the same path as that, we're going to say that's okay. And then we're going to keep going. So let's download the pizza, steak, and sushi data. This is going to be downloading it from GitHub with open data path / pizza, steak, sushi.zip. So our images are in a zip folder, which is this file name here, data. So we'll open that up as, we need write binary because we want to download this particular file and write it to the file system here. That's where we want it as F. So F is an alias for file. So write binary, WB. So request, we're going to create a request here. Request.get, this is using the request library from PyTorch. So we're going to get this URL, but we want the download URL, which is going to be the raw URL. So there's that URL that we're going to get, and then we're going to go print, go downloading pizza, steak, sushi data, ... And then we're going to go f.write. So this file that we've opened, write binary as f.write the request content. Request.content. Beautiful. And then because this is going to download as a zip folder, we want to unzip it programmatically, right? So let's go unzip pizza, steak, sushi data. We go with zip file data path / pizza, steak, sushi. This time we're going to read the downloaded file that we did with the R permission as the zip reference. So zip ref for short. So this is where we're bringing in zip file from the Python library. Zip file.zip file. Open up the zip folder that we just would have downloaded from GitHub. And then we'll go unzipping pizza, steak, sushi data. This should be relatively quick because there's not too much data there. If it was a large data folder, it may take a little while, but that's to be expected. The more data you have, the more compute it takes. Extract all image path, beautiful. And then we want to remove.zip file. Yeah, we can remove it. We don't need the zip file after that. os.remove data path / pizza, steak, sushi.zip. Now, of course, my challenge to you is to functionize this to be a function such as download data. And you would only pass it, say, a URL, and it would download data and do all these steps for you. Or, of course, as we clone the repo, you could just keep the data folder there because we're cloning this whole repo. Keep the data folder instead of removing it. So there's two little extensions you could try, but let's see how our code goes. Do we download? Yes, we do. Did not find pizza, steak, sushi. Downloading it, and unzipping it. Let's have a look here. Data, pizza, steak, sushi. Let's have a look at the training images. Pizza, steak, sushi, as we've seen before. And there is a delicious, not the greatest photo of pizza, the most aesthetically pleasing, but it is a photo of pizza nonetheless. There's another one. Delicious margarita there. Making me hungry. That's the challenge of working on food vision. Now, let's set up the directories, hey? Set up directory paths. So we want a training and a test directory path. So we'll go train dir equals our image path / train, and we'll create a test dir equals image path / test. Then we can inspect both of those just to make sure we've got paths to the right. Yeah, there we go. Data, pizza, steak, sushi, train. Data, pizza, steak, sushi, test. There's our paths. So we are now up to, can you guess the next step? We've done it a few times now, but if you can't, that's all right. We're going to cover it in the next video. Let's turn our image folders into data loaders. Now there's a little trick that we're going to have to do with this one, but I'll show you that in the next video. I'll see you there. Welcome back. In the last video, we downloaded our pizza, steak, and sushi data and created paths to the training folder, and the testing folder. So now we've got images downloaded to our file system over here. We want to turn them into PyTorch data loaders so that we can load them into a model. And we've done this before, but there's a little tidbit that we're going to have to do for using a pre-trained model for transfer learning. So let me turn this into Markdown. Oh, what have I done there? I don't want that. So now we've got some data. Let's type this out. Now we've got some data. Want to turn it into PyTorch data loaders. And to do so, we can use data setup.py and the create data loaders function we made in 05 PyTorch going modular. So if we go back to going modular, then we had data setup.py. So we created this file. We have data setup.py, and there's a function in that called create data loaders. And what this took was a training directory, a testing directory, and a transform. So this is what we're going to have to pay attention to here when using a pre-trained model. And then what it would do is we use image folder to create the training data, and then we turned the data sets, the PyTorch data sets, into data loaders. And then we return the train data loader, the test data loader, and the class names. And we used our transform here to transform any images we'd like to use from the image folder. So that's what we're going to cover in this video. If we look in here, we've got going modular, we've got data setup.py ready to use. So create data loaders, we've already imported it, but I just want to show you, if we go from going modular import data setup, and then we can go data setup dot create data loaders, and then what do we have here? Is this going to import? Yeah, there we go. Trained-er, tester, transform. So that's what I'd like to talk about now, is train data loader, test data loader, and class names. So recall that the transform, I'm going to write this down. There's one thing we have to think about, but there's two ways to do it. So one thing we have to think about when loading data is how to transform it. And with Torch Vision 0.13 plus, so this is why we are making sure that we're using Torch Vision 0.13 plus. There's two ways to do this. Number one is manually created transforms. And number two is automatically created transforms. So number one is manually. You define what transforms you want your data to go through. And two is the transforms for your data are defined by the model you'd like to use. Now, so we've said, how do we transform our data? And this is an important point. Important point is when using a pre-trained model, it's important that the data, including your custom data, that you pass through it is transformed in the same way that the data the model was trained on. So that's what we're going to have a look here. So we've covered a few things here, and I know they said there's one thing and then there's two things, then there's another thing, but these are kind of all the same point. Is how do you, once we've got images loaded over here in data, once we've got images here, how do we get them into PyTorch data loaders? And so our function here, create data loaders, we have to define a transform. In other words, how do we transform it from images into tensors? Because models like tensors, right? So what we're going to go through is step 1, manually created transforms, and then step 2, automatically created transforms. Now, this one is only introduced in 0.13 plus, which is why we emphasize the fact that we need Torch Vision 1.3 plus, 0.13. So if we go import Torch Vision, just make sure your version of Torch Vision is 0.13 plus. Otherwise, what we're using, so this is 0.14, we're good to go. If it's not 0.13 plus, this step 2 won't work. Let's go through step 1. So we'll create another heading here. 2.1, creating a transform for Torch Vision .models manual creation. And if I haven't introduced Torch Vision .models already, we'll just introduce it here. Torch Vision .models contains pre-trained models, so models ready for transfer learning, right within Torch Vision. So let's have a look at how we can manually create a transform. So I'll just get rid of this. And I'll get rid of this. And I don't think we need that. We might just keep that like that. Beautiful. Okay, so we'll jump into Torch Vision models. And so I'm going to look at the documentation here for 0.12. And then I'm going to go look at the newer documentation. So models and pre-trained weights. Now it's important to be aware of the older version because you probably will see this in PyTorch code you find in the wild, but eventually everything will start to move towards the newer versions. So the main transform you have to be considerate here if you're using a model for classification is, if we come down here, all pre-trained models expect input images normalized in the same way. And now this transform is for computer vision images. However, this whole premise of using transfer learning is for the same for almost any problem. You have to make sure your input data, regardless of whether it's images, text, or audio, is transformed in the same way your pre-trained model is. But since we're focused on images, we're focused on Torch Vision models and pre-trained weights. So we need this normalized transform here. What this is going to do is ensure that our data has mini batches of 3-channel red, green, blue images of shape 3, so color channels, height, width, where height and width are expected to be at least 224. The images have to be loaded to a range of 0 and 1, so their values have to be between 0 and 1. We can do that with the 2 tensor transformation. And then their pixel values have to be normalized using mean equals this list of values here. I'm not going to read them all out. And standard deviation. What this means is that our images, if we normalize them like this, will have the same data distribution as the pre-trained models. And so if you want to learn the process of obtaining these values for mean and standard deviation, they are learned from the ImageNet dataset. So if we look up ImageNet, and if you wanted to calculate the data distribution, now I did have some trouble loading this website the other day. So we'll just go to the Wikipedia version of ImageNet. Yeah, there we go, ImageNet. So the big ImageNet has 14 million images, but the smaller ImageNet has 1 million images. So this is just basically saying, format your data so that it has the same distribution. Recall what a data distribution looks like. There we go. Something like this, a curve. That's similar to a normal distribution, but these values have been calculated to be the distribution, the mean standard deviation of the ImageNet data. So we want our own custom images to have this same distribution. And now these values, there's 3 values here because it's 1 for each color channel, red, green, blue. So that's enough talking. Let's see this in action. I'm going to copy this. I'm going to bring this in here. Now you might not have this. The documentation might be different by the time you read it. So let's jump into the new version of it. And we're kind of mixing and matching a few things here, but it'll all make sense in a second. So models and pre-trained weights. This is a little bit different formatted documentation. Do we have normalize? Yeah, okay. So you're not going to find this what we just found anywhere in the new documentation. So that's why we're covering two different ways of making transforms. The first one is manual. The second one is automatic, which we're going to have a look in the next video. So let's do the manual transform first. So from Torch Vision, import transforms. That's what we want. So what we're doing here is we're formatting our own custom data to be in the same format as the models that we're about to use have been trained on. So let's go manual transforms equals transforms.compose. And if we just jump back to the older documentation, models and pre-trained weights, we're just going to copy this line in here so we know what transforms we need. All pre-trained models expect this. So we can break this apart. And any good documentation where you find pre-trained models will have this information stored somewhere. So normalize. Yeah, that'll do. Okay, so we need three kinds of transformations here. We need height and width are expected to be at least 224, and the images need to be loaded into a range of 0 to 1, and then normalized using these values. So we've got our normalized transform here. Let's now do the first one. So transforms, we're going to resize our image. So as an image comes in, it's going to get resized to 224, 224. Now you can adjust these values to be whatever you want. So say you had a model that expected images of 300, 300. So height and width of 300, 300. You can change that. The importance of the reason why I'm showing you manual transforms is that because you can customize this pipeline to however you want it. Whereas when we see the automatic transforms, they're already made for you. So the flexibility of manual transforms is that you can make them whatever you want. However, the downside is if you have errors in here, or such as you're not transforming your data in the same way as your pre-trained model, you may get performance degradation. So this is what we're doing. We've got one resize image to 224, 224. That's height times width. I've spelled that correctly. And then get images into range 0 and 1. And then make sure images have the same distribution as ImageNet, where our pre-trained models have been trained. So that is this important point. When using a pre-trained model, it's important that the data, including your custom data that you pass through it, is transformed in the same way that the model was trained on. So if we wanted to create data loaders using this manual transform, let's see what that looks like. We can go train data loader. This will be using this function here, data setup. I might just get rid of that. Train data loader, test data loader, class names equals data setup dot create data loaders. So using the function we created in the previous section, train directory is going to be equal to the train dir, and then the test dir is going to be equal to the test dir, and the transform is going to be equal to the manual transforms, what we just created above. So it's going to pass all of our images through this little sequence of transforms. And then what other things do we need here? Maybe batch size? Create data loaders, transform, batch size, yeah. Let's set a batch size of 32. And let's see what this looks like. Train data loader, test data loader, class names. Beautiful. Now we're not going to see those transforms because they're going to happen behind the scenes, but we've now transformed our data using manual transforms. In the next video, let's take a look at number 2 here, automatically created transforms. I'll see you there. Welcome back. We're going through the important step of preparing our data to be used with a pre-trained model. And we learned in the last video that one of the most important steps when using a pre-trained model is that your data is formatted in a similar way to what your pre-trained model, the data that was trained on. And we saw how we can manually construct a transform here by putting together a pipeline. And we learned that the flexibility of manual transforms, manually created transforms, is that they can contain anything we like. We can get as creative as we want here. We can put in data augmentation. We can put in a whole bunch more things if we wanted to. The only real downside of a manually created transform is that if we've transformed our data in a way that is different to our pre-trained model, well, then we might get performance degradations. And so introduced in Torch Vision version 0.13 is a way to automatically create transforms. So creating a transform for Torch Vision.models, and this is going to be auto creation. We're going to go here. This is why we spent a lot of time making sure we're using Torch Vision version 0.13 plus. As of Torch Vision v0.13 plus, there is now support for automatic transform creation or data transform creation based on the pre-trained model weights you're using. So if we just go import Torch Vision, we'll just make sure one more time that we're using Torch Vision 0.3 plus, and we should be, because we've checked this a few times now. Yeah, there we go. And so I'm going to get rid of a few of these extra tabs. So if I come to the documentation here, this is version 0.12, the older version of the API. It's important to be familiar with this because you might find this somewhere on the internet, but this is where PyTorch is going. So main, this might be not the unstable version by the time you watch this, but this is the new Torch Vision pre-trained weights, multi-weight API. Models and pre-trained weights, that's where I'm at. Initializing pre-trained weights, but here we go. As of v0.13, Torch Vision offers a new multi-weight support API, which is much better than the previous one because you can use different forms of weights. So here we go. We've got a model from Torch Vision models, import ResNet 50 and import ResNet 50 weights. You didn't used to have to do this, but now they've added an extra step, which, yeah, it's an extra step, but adding that extra step has dramatically improved how this API works. So the old weights, so we have V1 here, gets an accuracy of 76%, whereas the new weights, trained in a new way, gets an accuracy of nearly 81%, so a jump of almost 5%. So that's the benefit here. We can use multiple different models, and if a better version of that model, the weights for that model, the patterns that that model has learned comes out, well, we can instantiate that with a single variable. So that's what we're going to be focused on here. And if you do see it in the past or in other older tutorials of PyTorch, you might see a model name and then pre-trained equals true. That's the deprecated version, so you will get errors if you write or see code like this from future versions, but we're going to be using, as of recording, the latest cutting edge version. So if we keep going down, using pre-trained models, I'll let you read through that. In fact, this is going to be your extracurriculum, is to read through Torch Vision models and pre-trained weights for 10 to 15 minutes to get an overview of what's going on, but we're going to practice this by writing code. So then if we come down to classification, there's other models here for semantic segmentation, video classification, object detection, all different kinds of pre-trained models depending on your problem. But what are we trying to do? We're trying to classify images of pizza, steak, and sushi, and we have a bunch of different computer vision architectures that we can choose from here, which Torch Vision has so kindly provided pre-trained weights. I'm not going to go through all of these. I'll let you do that on your own. One of the best models that I've found to work is EfficientNet. There's also EfficientNet v2, but beside the point, let's focus on one. So if we jump into this architecture, EfficientNet is from this computer vision paper. EfficientNet, if you'd like to read up how EfficientNet was created, what these do for us is give us access to an EfficientNet B0, B1, B2 architecture. And a general heuristic for looking at computer vision models, or any model in general, is if they have some sort of number associated with them, for example, B0, B1, B2, the higher the number, the bigger the model. that's something you need to take into consideration when you start to deploy your models, is that if your model is too big, yes, you might get the best performance from EfficientNet B7. However, it might not run in your application because it's just such a large file. So to begin with, we're going to start small and scale up when necessary. Let's dive into EfficientNet B0. What do we have here? In fact, EfficientNet B0 is what's running my computer vision app, Nutrify.app. So if you take a photo and upload that, it's running an EfficientNet B0 in the browser. That's my little bias towards EfficientNet. So if we jump in here, what do we have? We have some weights, parameter, torchvision.models, EfficientNet B0, weights. That's what we're going to be looking at. Weights, and we find the EfficientNet B0 weights available from PyTorch have this performance on ImageNet. 77.692, accuracy at 1. So that's predicting on ImageNet with 1,000 classes. It predicts out of 1,000 classes and 1,000,000 images at nearly 78% accuracy. That's pretty good. And the accuracy gets even higher if the predicted class is in the top 5 predictions of the model. So let's focus on using this one. How could we create automatic transforms using this model? And the same process will go from whatever model we'd like to use. If we'd like to use ConvNext or Vision Transformer, this process will be much the same. Let's just focus on EfficientNet B0. If we want to get the automatic transforms, we start by importing the weights. Let's see what that looks like in code. So get a set of pre-trained model weights, and we'll go weights. So this is going to be patterns that a model has learned on ImageNet. And we want to leverage those patterns for our own custom data. So EfficientNet, torchvision.models.EfficientNet B0, and then we're going to go weights. So the model name, and then .default. And so this is another benefit of using the new API. Default equals best available weights. So the best performing weights. Now, of course, if we jump back into here, EfficientNet B0, if we look at this, the model builder above accepts the following values as the weights parameter. .default is equivalent to EfficientNet B0 weights.ImageNet 1K v1. So this means that default is the same as using the ImageNet weights, so ImageNet 1K. So if we import this, that means we're getting an EfficientNet B0 architecture that was trained on ImageNet 1K, so the 1,000 class ImageNet. There's also ImageNet 21K, which is 21,000 classes, which is quite a big model and quite a big amount of data. So let's have a look at what this does. There we go. EfficientNet B0 weights, ImageNet 1K v1, default. Oh, this is so exciting. This is some cutting edge stuff. This is barely even released right now. So let's get the transforms used to create our pre-trained weights. We will go auto transforms equals weights dot, so we've got the weights here. Look how easy it is to create these transforms. Dot transforms. And then auto transforms, let's have a look at what they look like. Wow. Okay, so instead of manually creating this pipeline up here, we've just gone, okay, we would like to use EfficientNet B0, and you could choose whatever model you want here. And then associated with the weights is how those weights were created now. That's the beauty of the updated Torch Vision API. Now, if it's your first time using Torch Vision, this is going to be the standard for you. So congratulations, this is an amazing piece of code. We have crop size 224, which is very similar to what we've done here. Resize. Then we have, well, it resizes to 256. Then it gets the center crop of 224. And then it uses mean and standard deviation to normalize the image, which is the exact same as what we've got here. Except this one is manually created. This one is just giving us this transform automatically. Now, let's create the same data loaders that we did above here with the automatic transforms. So create data loaders using automatic transforms. So train data loader and test data loader, and then class names equals data setup dot create data loaders. Trained-er is going to be our training directory, and then tester is going to be testing directory. Transform is going to be auto transforms, and then the batch size is going to be equal to 32. Now, is it transform or transform? Let's run that and see what happens. Beautiful. So train data loader, test data loader, class names. We get basically the same thing as what we got above. Well, exact same thing as what we got above. So the things to keep in mind here is that when you're preparing your data to use with a pre-trained model, it's important to consider how that pre-trained model, such as the one in torchvision.models, you'll have to pay attention depending on the source where you're getting the pre-trained model as well. It's important that your custom data is transformed in the same way the data the pre-trained model was trained on. And for Torch Vision in particular, we can create a transform manually. We just have to create a pipeline like this. The benefit of this is that it's infinitely customizable. The downside is that if we put a foot wrong and create the wrong transform, our model's performance may be degraded. And as of Torch Vision version 0.13 plus, there is now an automatic way to create transforms when you use a pre-trained model, and that is by leveraging the weights from that pre-trained model. So say we wanted to use EfficientNet B0, but this would be replicated basically with whatever pre-trained model you want. So if you go into here, there's classification, whole bunch of different models here. And then if we scroll down, we have table of all available classification weights. So we have weight and then a whole bunch of different models here. We'll go through that in the next video actually. And then you can call .transforms on those pre-trained weights. And you can use those transforms when creating your data loaders, just the same as we used a manual transform up here. So as I said, the extra curriculum for this is to read through this documentation, models and pre-trained weights. Make sure you're on a version that's using v0.13 plus. And if you want to look at the old style of doing things, you can look at v.12. At the time of recording, that is the stable release, but we're focused on the latest and greatest here. I'll see you in the next video. Let's discuss how to choose a different model. Welcome back. So we've seen two different ways to format our data for using with a pre-trained model, and that's automatic transforms and manual transforms. Now let's figure out how to get a pre-trained model. How do we load one in? So getting a pre-trained model. And so we'll write down here, there are various places to get a pre-trained model. Such as we have one is PyTorch domain libraries. Two is libraries like TIM, which is Torch image models. I'll just put that in brackets. Torch image models. And then we have three, which is Hugging Face Hub for plenty of different models. And then four, another place is Papers with Code, which is going to be machine learning research papers for models across different problem spaces / domains. We're focused, of course, on just pure PyTorch, but you've also got these other things. So yes, there are places to get a model, but how do you choose a model? That's an important step. That's really the million-dollar question. Which pre-trained model should you use? Now, there's no definite answer to this. So like much of machine learning, I'm going to encourage you to adhere to the machine learning practitioner's motto of experiment, 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 to try and find out which model best suits your problem. But what do we want to do? What's the whole idea? The whole idea of transfer learning is to take an already well-performing model from a problem space similar to your own and then customize Customize it to your own problem. And so when I pick a model, there are usually three things that I consider. Three things to consider. One is speed, because a slow model is not really a model, right? We want things to work fast. Two is size. Three is performance. And they're usually tied all together, right? Speed, size, performance. So speed is how fast does it run? Size, how big is the model? Once a model gets pretty big in terms of number of parameters, you need a specific set of hardware to store that model. And performance is how well does it go on your chosen problem? E.g., how well does it classify food images for our problem of Food Vision Mini? So speed, let's think about this, right? If we had a Tesla car, images, do we have self-driving on here? Tesla self-driving. So here, a Tesla model, the model needs to be quite fast because you're driving. So if you had a slow model while you're driving, that's not really a good thing, right? So Tesla have to consider how fast their model needs to perform on the car. And so another thing to consider is if we look up compute server, two kind of real ways to deploy a model is by storing it on a compute server. And then what would happen is the Tesla car might take a video of the scene, upload that to a compute server, and then the compute server would send patterns back to the car. Now, just think about that. Would that work in a driving space? Well, it wouldn't really, because you can't really wait for that time to upload the video to the compute server and then download it back to the car. So the model needs to be on the car. So that's something you'll have to consider is where does the model live? Is it on device, as in like a self-driving car, because you need it to be fast. You can't have it upload, self-driving car. Or does it live on a server? These are kind of all tied together, right? You want the fastest model you can at the smallest size you can with the best performance. Does that make sense? The fastest model you can get at the smallest size you can get at the best performance. Now, of course, there's no real silver bullet here as the most ideal model, but these are just things to consider. What is your problem? So for Food Vision Mini, if we wanted to deploy our model to a mobile device, we'd want it to run fast. We'd want it to be relatively small so that it can fit on a mobile device, and the performance would have to be pretty good, otherwise people won't use our model. So that's just things to consider. And so if we go into looking at, we come into here, say we've got a whole bunch of array of models that we could choose from. I'm just going to close all of these tabs so we don't get, there's a lot going on here. But that's all right. It's going to all come together. Things to consider. We're working on a classification problem. Let's keep our ideas in mind. Speed, size, performance. So if we scroll down, we have table of all available classification weights. So these are pre-trained models. How do we choose one of these? I'm going to bring this in. Looking at this, which model should we choose? So let's keep our three parameters in here. Speed, size, performance. So Food Vision Mini, we want to run it on a mobile device. That's our criteria. So we need a fast model, we need it relatively small, and we need good performance. So if we look at all these, I'm not going to go through all of them. You can do that as extra curriculum. But look at all these pre-trained models. This is the beautiful thing about machine learning is most of the best research gets open source. So where's EfficientNet? Or let's just look at this. So the weights, these are the different pre-trained model weights. Most of them are on ImageNet 1K. This is their accuracy value. So this is the performance. How well does a model classify certain images? And then the parameters here is the size. And you can kind of say that if the parameters is relatively small, it should be fast. It's not always the case, but generally the less parameters, the faster they run, because a parameter is essentially a computation that you have to go through. So the higher number of parameters, the slower the model is going to run in terms of inference, in terms of making predictions. Generally, not always the case, but just generally. So in our case, we'd look for the best trade-off between highest accuracy and lowest parameters. Now you could go through all of these and figure it out, find the highest accuracy to number of parameters ratio. The reason why I choose efficient nets is because they are generally very good in terms of performance with a lower number of parameters. For example, look at efficient net B0 weights. We have, let's just call this 78% accuracy with 5 million parameters versus, let's find another model. Inception V3, we have less accuracy than efficient net B0, but 6 times as many parameters. That's something to keep in mind. Then if we scroll down, we have other models. What's a similar? Where's 78? 78, 77. There we go. RegNet X. These model names can get creative. Okay, this is pretty close to efficient net B0, but you could keep going through this. So for our criteria, we want best performance with lowest number of parameters. So efficient net B0. And then another thing to consider, if you wanted a mobile specific device, a specific model, there's also the concept of mobile nets. So these have quite a good accuracy performance, not as high as efficient net B0, but a low number of parameters. So if we look at mobile net V3 large, we've got 75% accuracy versus efficient net B0, which is 78 thereabouts, rounding up. And we have quite the same number of parameters. So that's just something to keep in mind. When you're choosing a model, you want speed, size, and performance. For our case, it looks like FNet B0, efficient net B0 for short, or FNet B0 for short, is one of our best options in terms of performance versus size. And so we're going to set this pre-trained model up in a second. I just want to introduce you to one more important thing, which is a great essay in the world of AI. However, for our case, let's just say our use case, our end case is deploying Food Vision Mini on a mobile device. So we have a compute restriction because an iPhone doesn't have as much compute as, say, internet server. However, in light of the bitter lesson, I'm going to show you what this is in a second. If we had infinite compute, we'd likely pick the biggest model plus most parameters we could, plus most general. That's another thing to consider. We could. And so the bitter lesson is one of my favorite essays in the world of AI. I'll let you read this. The bitter lesson. So the biggest lesson that can be read from 70 years of AI research is that general methods, so the more general the method, so a neural network is considered a general method, that leverage computation, so as much computation as you can get, are ultimately the most effective and by a large margin. So I'll let you read through all this, but my main takeaway from this is that generally the more data you have, the more compute you have, the more general your method, such as a neural network, a learning algorithm, the better your results will be. So if you had infinite compute, go for the biggest model you can. But we don't. We're keeping things small and we're scaling up when necessary. So that's which pre-trained model you should use. Keep in mind your speed. How fast does it need to run? Does it need to run? Are you deploying it to a device and it needs to run on that device, or can it run on a bigger compute, say in the cloud, on a server? How big is the model? What kind of hardware do you need to store it? Because the bigger your model gets, the more advanced the hardware needs to be to store it. And what performance do you need? What's the minimum level of performance you need to get out of your model, out of your chosen problem? So for our Food Vision Mini, we probably want it classifying images at close to 90 or 90+% accuracy. For a self-driving car, you probably want even higher than that. So keep these 3 things in mind. For your extra curriculum, go through here and find out, is there a better model than efficient net B0 in terms of accuracy and parameter ratio? If there is, let me know on the GitHub discussions. Otherwise, I'll see you in the next video. Let's see how we can set up our very own pre-trained EfficientNet B0. Welcome back. In the last video, we discussed a few criteria to choose which pre-trained model you should use. And inevitably, this is going to be quite a hard decision to make. However, you can't go through all of them, so we're going to stick with EfficientNet B0 for now. If you think there's a better one, please let me know. I'd love to know. So 3.2 is setting up a pre-trained model. Let's see how we can do it. So we want to create an EfficientNet B0. We want to create an instance of a pre-trained FNet B0. So let's jump into here. If we go into this EfficientNet B0 weights, we can instantiate this model using EfficientNet B0. And so again, this is from the paper. A lot of these pre-trained models are from some sort of research paper, and PyTorch have baked them into the library. So that's just something to keep in mind. That's where these models have come from. And they typically don't make it into the library unless they're a good model. So if you use one from the Torch Vision library, you can probably bank on it being at least pretty good. So let's write in this code, or just copy in this, pre-trained EfficientNet B0. I want to just show you the old way of doing things, old method of creating a pre-trained model. So this is prior to the Torch Vision v0.13. I'm showing you the old version because at the time of recording, version 0.13 is very new. It's not even out yet, but you might come across this way of doing things in older PyTorch code, but it is going to start to error over time. So just keep that in mind if you see this out in the wild. So torchvision.models, we can create it by going EfficientNet B0. And of course, you could substitute this for any of the models within Torch Vision models. And then if we set pre-trained equals true, what happens if we run this? It's going to download some weights. That was that download bar, so it's downloading the pre-trained weights. However, look at this. The parameter pre-trained, so pre-trained equals true, is deprecated since version 0.13. That's why we've been focusing on 0.13. And will be removed in 0.15. Please use weights instead. So that's an error message there. And so new method of creating a pre-trained model this is Torch Vision v0.13 plus. So I'm going to comment this out. And then we're going to go model equals, or first and foremost, we set up the weights. We don't actually need to reset them up because we've got them above, weights. But I'm just going to do it again for completeness. If we go weight equals torchvision.models dot EfficientNet B0 weights. And then we're going to go .default because if we go here, .default equals best available weights. This will depend on what model you're using, of course, right? .default. Default is the best available. And so there's a .default because some models, this is the benefit of using the updated, some models have different versions of their weights. So if a better recipe, such as version 2, comes out, is it got recipe here? Yeah, so now you can see how the weights were obtained. So some of these have V2. Look at that, ImageNet B1 V2. So if the new version of the weights get improved, instead of just setting pre-trained equals to true, we can download a different set of weights. So that's the benefit of using this. So a whole bunch of different other model weights here. If you want to use a different model, make sure you're lining up the model that you're using with the weights that you'd like to use. So now let's set up the model in the new way. Torch Vision. We've got the weights.models. Now we're going to go EfficientNet B0. Then we're going to set the weights parameter and make sure this is weights because I went a long time recently of just having this as weight. So weights, make sure it's weights. Weights equals weights. So all we're doing is downloading this weights, pre-trained weights, and putting them into our model. And then if we have a look at our model, let's see what happens. Oh, look how easy that was to create a pre-trained model. Now this is the EfficientNet B0 architecture. Have a look at how many layers are here. Oh my goodness. Keep scrolling up. We've got some convolutional layers here. Conv2D. We've got a Silu activation there, batch norm 2D. All of these are in the PyTorch documentation if you wanted to look up. We keep going. Oh my gosh, still going. This is how many layers. This is the benefit of using transfer learning. We get all of these layers someone has built, so handcrafted these layers for us. And now we get to leverage them for our own problem. Remember when we were building tiny VGG? If we go into here, custom data sets, when we created tiny VGG, these are our layers. So we had how many layers? That's what we had for tiny VGG. That was our previous model we built by hand. Now look at our model. Now I'm going to get you to just concentrate on the three big sections here. We've got features, and if we scroll down, all of these layers, this is what happens when we've imported it from Torch Vision. This will be a similar process, all of these layers from a lot of the other well-performing models. Keep going. Model. Oh, we at the bottom yet? Oh, we're getting close to the bottom. Beautiful. Now, average pool and classifier. All right. So we're going to break this down into three main parts. So if we go model.features, these are the feature layers, all of these layers. And then we have model.average pool. We've got an average pool. So that's going to collect all the features and average them. I'll discuss what this means in a second. And then we have a classifier head. So this is what we're going to be altering for. We're going to alter the features and the classifier head for when we want to customize this model to our own problem. So this is the output layer of the final layer of our pre-trained model. And what you'll notice is that it has out features equals 1,000. So that 1,000 comes from our model being pre-trained on ImageNet. So if we go into here, ImageNet 1K, so 1,000 is because ImageNet has 1,000 different classes. So I just want you to think, what do we need to change this value to for our pizza, steak, and sushi problem? If this is trained on ImageNet and ImageNet has 1,000 classes, how many classes do we have? Pizza, steak, sushi, so 3 classes. So we're going to need to change this to 3 because instead of outputting 1,000 features for 1,000 classes, we want to change it to 3 for 3 classes. I've got a colorful slide that explains this a bit better. Let's code. So the type of model we're going to be building here is an efficient net feature extractor. You may have never heard of feature extractor before, but we're going to discuss what it is. There's another way that these models are referenced is EfficientNet B0 backbone, but this is just a truncated version of what we just saw, the output. So we've got features. This is going to extract features from an image. Now, what is a feature? A feature could be anything that you could imagine. Now, these layers are going to look at our image of pizza, steak, sushi and extract a feature. For example, it could be the fact that pizzas are curved, they're circular shape. It could be the fact that steak is darker color. It could be the fact that sushi is usually small. So this is what's going to happen with this features section of layers. It's going to try and extract, I was thinking of the right word there, extract features from our image. And then this average pool layer is going to convert all of these features into a single feature vector. So it's going to compress everything that this features section has extracted from our image into a single vector. And that vector is going to be of size 1280 because our linear layer here takes 1280 input. So essentially what this whole process is doing is compressing our image into a single vector of 1280. But we'll see this later on. We're going to get hands-on with this. I'm just discussing this out loud. Then the final classifier layer is what turns that feature vector, or the compressed version of our image, with hopefully some learned representations of what's in there. All of these features, by the way, are going to be flavored by what our model has learned on ImageNet. Then we're going to adjust this classifier layer to turn those feature vector, or that feature vector for each image, into an output of prediction probabilities for 3 classes instead of 1,000. So we can adjust this depending on the number of classes we have. So to break it down, we're using an EfficientNet B0 backbone. We have a features section. This is going to extract patterns out of our images. and we don't define what those features are. This features is using patterns learned on ImageNet. So it's going to define those. That's the whole magic of machine learning. This average pool section is going to compress those features into a single vector of size 1280. This is the input and output shapes that we've discussed so much. And then this classifier head is going to further either compress those features, 1280 into 1000, or into 3 for the number of classes that we have. So we've got lots and lots of layers, but that is the power of transfer learning, is we are taking a working computer vision architecture and applying it to our own problem. So this is a feature extractor model. It's called that because we generally keep all of these layers intact, and then all we do is we change the last layer. So there are other types of transfer learning, and we're going to discuss that in the next video, and then we'll get hands-on building these feature extraction models that I've been talking about. I'll see you in the next video. Now we've downloaded and sort of inspected a model from torchvision.models. Let's just discuss some of the different types of transfer learning. The model we're going to be focusing on is an EfficientNet feature extractor. So this is what we just printed out. We've got EfficientNet. This is from torchvision.models.efficientnet B0. Of course, the output will be slightly different depending on the model you have here, but the idea of a feature extractor transfer learning model is quite similar regardless of the backbone you're using. That's another term here, EfficientNet B0 backbone. So you're going to hear quite a few different terms around transfer learning. They all mean different versions of the same thing. So we have our overall architecture here, which is an EfficientNet. Then we have this features section. Now this extracts features from an image. Now, what is a feature? A feature could be almost anything. It could be the fact that pizza is a little bit curved in some positions. It could be that steak is a little bit darker than other foods. It could be that sushi often has many small items on a plate. The important thing and the magic of machine learning is we don't actually tell our model what a feature is. It learns those features. And in our case, a feature extractor, we keep all of these features layers or base layers or backbone layers frozen as they've learned patterns in ImageNet. All we really want to change in our feature extractor model is the output. So an image will go through all of these layers, and then what the average pool layer here does is it turns the features our model has learned, which might be a big tensor, into a single feature vector. So it compresses it. It compresses all of the information that our base layers, our feature layers have extracted from the image into one single vector. And in this case, for EfficientNet B0, the vector will be of size 1280. So that's an important thing to take note, is the size of the input to the last layer, 1280 in features, and the output. So features is going to turn an image into a big features matrix. Average pool is going to compress that, or tensor, is going to compress that features tensor into a single vector. And then this classifier layer, or the classification head, we can adjust this to our own problem and change the number of out features. In this case, EfficientNet B0 has 1,000 out features, but that's because it's been pre-trained on ImageNet. So we can change this to 3 for pizza, steak, and sushi. So if we keep going, let's have a look at the original model. So the original model that you would find on torchvision.models versus a feature extraction model. So there we have the original model. We start with a large data set. We have a number of different layers here. And the number here is quite arbitrary because it will really depend on the architecture you use. I think EfficientNet B0 has something like 200 layers, but you can correct me if I'm wrong. Then we have an output layer with the shape of 1,000 for ImageNet's 1,000 classes. So we use a working architecture such as EfficientNet to create the original model. And then for feature extraction transfer learning, we're going to keep all of the base layers here frozen. That's a terminology you'll hear in machine learning quite often, is with the base layers stay frozen. This means they don't get updated, their parameters don't get updated during training. They've already been learned on ImageNet. So the original model layers don't update during training. So then we create a feature extraction model, and we change the input data and the output head. We keep this the same, these feature layers. So now the input data to our feature extraction model is going to be our own custom data set. 3 classes of food, pizza, steak, and sushi in our case. And then we change the output head, so the output layer gets trained on new data. So this is the only trainable section of this whole feature extraction model. We're going to see this in code in a minute. I just want to talk about this from a conceptual overview. So the original model, then we move to feature extraction. Now this, we could change this to be 10 if we had 10 classes of food. We could change it to 100 if we had 100 classes of food. The point being is that the base layers, the feature extraction layers, stay frozen, and that we customize the input data and the output data. So that's the power of transfer learning. And there's one more type. So we've discussed the original model. Then we move on to feature extraction transfer learning, where we keep the base layers frozen. Then the final form is fine-tuning. Now, fine-tuning is best suited when you have large amounts of training data. In our case, we don't necessarily have that much data. We only have about 100 or so images of pizza, steak, and sushi. But if you had 1,000 images of each different class you had, you might want to look into fine-tuning. So with feature extraction, we only changed the base data set and the output layer. But with fine-tuning, we can unfreeze some of the base layers and update their weights to suit our custom data. And now this usually works best with large amounts of data. Otherwise, it's best to just keep the base layers frozen and do feature extraction. And this order is also important. Usually start with an original model, then move to feature extraction transfer learning, update the base data set and the output head, and then slowly unfreeze layer by layer from the top down when you want to fine-tune your model. So we're focusing on feature extraction. We're going to see that in a second. And if you want a tabulated version, we're not going to spend too much time on the tabulated version because it's what we've just discussed, but this is just for reference later on if you'd like to inspect that. We have different kinds of transfer learning. We can have the original model unchanged. That is if you have the exact kind of data the original model was trained on. We have feature extraction, which is very helpful if you have a small amount of custom data like we do. And then finally, you have fine-tuning, which is helpful if you have a large amount of custom data. But the order of this is also important. You start with an original base model, also called a foundation model. You would feature extract and train the last output layer to suit your own custom data, and then slowly fine-tune it by unfreezing the base layers. So let's go see feature extraction transfer learning in action. We first have to prepare our original model to be able to be used for feature extraction. We'll do that in the next video. I'll see you there. Welcome back. In the last video, we had a look at the different kinds of transfer learning. And we know that we're going to be focusing on feature extraction, but if we had a lot more data, and in fact, you can consider this your extracurriculum, is to look into fine-tuning after you finish this module. So let's jump in. Before we prepare our model for feature extraction though, let's just get a summary of our model. This is going to help with the concept behind feature extraction. So getting a summary of our model with Torch info. This is why in the beginning we made sure to install Torch info. So if you come up the top, we installed Torch info up here. This is going to help us get a summary of our model. Let's see it in action, hey? We've got this printout that we got before. This is just the regulation PyTorch printout. But Torch info gives us a little bit more detail of what's going on with our model. So print a summary with Torch info. So we're going to go from Torch info, import summary. We don't actually need to do that again, but I'm just doing it for completeness. The model we're going to pass in here is our model. And then we're going to put in a default input size for what size of our data would we like to pass to our model. 1322424. Now, this is an example of batch size, color channels. So this would be an example of passing a batch of an image of one image, and then height, width. That's the input size we would generally give to our efficient net B0. So we also want to put some column names here, col names. Now you see I'm getting a doc string here from Torch info summary. I've played around with this a little bit before, so we're going to just keep pushing forward. We're going to get an input size column so we can see the shape of our input data. We're going to get an output size column so we can see the output shapes of each of our layers. We'll get a number of params so we can see the number of parameters, the weights and biases for each layer. And then we'll see if the layer is trainable or not. This will make a lot more sense when it gets printed out. Col width equals 20. This is just for formatting. And then row settings is I want to get the var names. And of course, the documentation for Torch info is on the GitHub. Torch info, if you'd like to read more about that. Thank you to Tyler Yep for creating this. We've got Torch info documentation there. But let's see this in action. Let's get a summary of our model, which is fnet b0. Oh, beautiful. Look at this. Okay, so here's our efficient net, and here's a sequential, which is the features that we just went through. What it's going to do is take in an input image shape with size 1, 3, 224, 224. And the overall output shape of our whole model is 1 and 1,000. That's because if we come down here, this is the output shape here. But essentially our image is going to go through all of these different layers. It's going to be manipulated in shape, input, output, input, output, input, output, input, output. You can go through those step by step if you like. Each one of these layers has a different number of parameters. This is going to mean that as our image goes through these different layers, these parameters are going to hopefully learn something useful from our image. Then we get down to here, adaptive average pool 2D. So you notice that the input shape here is 1,1287.7. That gets compressed into 1,1280.11, then gets further compressed into 1,1280. So this is a feature vector of our single image that is going into the sequential or the classifier head of our model. And then this vector gets compressed even further into 1,000 classes. Where did the 1,000 come from? Well, it's because that this model, fnet b0, was pre-trained on ImageNet, and ImageNet has 1,000 classes. So what would we like to change this to if we're customizing the classifier head to our own problem of pizza, steak, and sushi? We'd like to change this to 3. And of course, that will vary depending on the number of classes that we had. And so if we look at this, is the layer trainable? So right now, all of these base layers are trainable. However, we discussed with feature extraction, if we just jump into original model versus feature extraction, we want to convert our original model, which is currently this, to this. So we want to freeze all of the base layers. So in the next video, let's see how we might do that. In essence, we want all of these to be trainable equals false, and the only layer we want to be trainable is this output layer here, the classifier head. And then of course, we've got some more information here. The total parameters of our model is over 5 million, so far more than our tiny VGG model. And currently all of them are trainable. So we want to alter, especially this value here, the trainable parameters. That will mean the more trainable parameters you have, the longer your model will take to compute. That's another benefit of transfer learning. Feature extraction models are generally quite fast to compute. And then another thing here is the estimated total model size in megabytes. This might not always be the case, but it's something to keep in mind when you go to deploy your model. As we talked about before, we have 3 big considerations for using a pre-trained model. How fast does it need to run? How big is the model in terms of how much storage does it take up? And performance, does it perform as well as you need it to? So the output of torch info.summary gives us a little hint at what the actual size of our model might be. Now, this won't always be 100% correct. Best to just check your model as it appears here when it gets saved to file system. That'll be the actual size of the model. This is just an estimate. So with that being said, we've inspected all the layers. We've discussed the concept of feature extraction. We now know that we want to freeze these layers, use those patterns that our model has learned from ImageNet, and then we want to change the classifier head to suit our own problem. So freeze these base layers, and change the classifier head to suit our problem. Let's do that in the next video. I'll see you there. Welcome back. In the last video, we got a layer by layer breakdown or summary of our model, thanks to torchinfo.summary. And we see if we pass in an image, it gets manipulated quite a bit in terms of input and output shape as it goes through our efficient net model. And we've got a various number of parameters per layer here, the parameters here. Hopefully they extract some useful features from our input image. And right now, all of the base layers are trainable. However, for a feature extraction model, we'd like to freeze the base layers and just use the patterns as they already are. And then we also want to update the classifier head to suit our own problem. So this is very exciting. We're going to customize, we're going to create our own feature extraction model using an efficient net B0. Let's jump into it. So let's go freezing the base model, create another heading here, and changing the output layer to suit our needs. So we'll just put a little note here. With a feature extraction model, extractor, that'll do, model, typically you will freeze the base layers of a pre-trained / foundation model and update the output layers to suit your own problem. That's what we're moving towards, an efficient net B0 feature extractor model. So let's see how we can first freeze all of the base layers. Freeze all of the base layers in fnet B0. So for param in, we're just going to take our model.features because we're taking .features, which is this section here, .features. Let's just see what that is. Model.features. There we've got all of these layers. We would like to freeze all of these layers. We don't want them to be updated during training when we're training on our own data because we're using the weights that these layers have already learned from ImageNet. So, .parameters, we can set there param, I've got im, not in. Param.requires grad, so we're turning off their gradient tracking. So PyTorch is no longer going to track the gradients of all of the parameters. We might actually just print the param before we turn them off. Let's see what this looks like. Param. Print param. Look at all these weight and bias terms here. These are all the pre-learned weights or pre-trained weights our model has learned on ImageNet. So there we go. Requires grad equals true. Recall that requires grad is an attribute of a parameter. That means PyTorch is going to track the gradients of this particular parameter. It's going to use the optimizer to tweak this parameter to better suit the data. So if we turn this to equal false, PyTorch won't track the gradients of these parameters and won't update them with the optimizer during training. So we could keep scrolling here. These are all just numerical representations that our model has learned. I'm not sure if these mean anything to you, but you could keep going. There's a lot of pre-learned parameters here. So essentially, all of these are what power, 5 million of them, are what power the backbone of our efficient net. And hopefully, if an image goes through here and some mathematical operations get done to that image, hopefully these equate to something meaningful for our model. That's the beauty of machine learning, and kind of one of the curses is that you don't necessarily know what your model has learned behind the scenes. Okay, that's enough scrolling, but you know there's a lot of numbers here. Let's comment that out. And if we set the param.requires grad, so this is going to set it all to false. That's essentially going to freeze all of these parameters. That's all we have to do. Have a look at that. We've just frozen all of these base layers. So now, if we take this same code here, summary model equals model, we've just frozen all of the base layers. This should have worked. Let's see. We print the same code as above. Have a look at that. Efficient net. Is it trainable? We've got partial trainability now. We've set all of these to false. Their requires grad is now false. So none of these layers, if we were to run this model through a training loop, none of these layers will update their parameters. They will just stay frozen in place. However, the output layer here is still trainable. So that's good. We just want to customize this output layer to our own problem. And if we have a look here, these numbers have changed. Our model still has the same number of total parameters. However, only 1.3 million thereabouts are trainable. And that's the output layer, the linear output layer. So if we go back up here, this one has every parameter is trainable. Our frozen base model only has the output layer as trainable. So let's keep going here. I'm going to keep this summary code here. We now need to update the classifier head. Update the classifier head of our model to suit our problem. So let's have a look at the classifier in our model. Model.classifier. So currently, this is another important topic, is that if we use an input size of 1322424, which is what we do, if we look at our transforms, we created some transforms up here. We resized our images to 224224. So this might be different, the input size, if we used a different value to 224224. So just keep this in mind. We pass this 224224 image through here, and it gets compressed into a feature vector of 1280. So we need to make sure that if we're going to alter this sequential, we have to keep these layers similar if we want to adhere to the original architecture of the model. And I'll show you what this means here. So say we wanted to update the classifier. I might just put that down there. Let's create model.classifier equals nn.sequential. We're going to replicate this with nn.dropout. So I'm going to import nn. I don't need to, but I'm going to anyway. Dropout, p equals 0.2, in place equals true. See what we've done there? We've just replicated that layer. And if you're not sure what dropout is, you can search that, nn.dropout. We get dropout here. Let's read the documentation. During training, randomly zero some of the elements of the input tensor with probability p, using samples from a Bernoulli distribution. Each channel will be zeroed out independently on every forward call. This has been proven to be an effective technique for regularization. What does regularization mean? Regularization means preventing overfitting and preventing the co-adaption of neurons as described in the paper Improving Neural Networks by Preventing Co-adaption of Feature Detectors. So let's look at it again. Dropout neural networks. Let's find an image. Images. There we go. So standard neural net, after applying dropout, here's what's going to happen. If we have some input neurons, usually they're all connected to each other. However, after applying dropout, we're going to randomly zero some of these connections. Now, why would we do that? So recall, dropout up here is a regularization technique. We're trying to prevent overfitting. And so if we randomly drop out some of these neurons, what it means is that hopefully the patterns that the remaining ones learn are more generalizable and thus reducing overfitting. So the whole idea of dropout is that we remove some at random with a probability p. By default, it's 0.5, but we're using 0.02, so 20% of our neurons here are going to be dropped out. So hopefully the remaining ones learn better patterns because some of their friends have been dropped out. So that's the concept of dropout. But if you'd like to learn more, I'll leave that as extra curriculum to research. And that goes with any layer in our model. Our model has a lot of layers, and if you'd like to learn more about them, just try looking it up, like SILU. What is that? NN SILU. Here we go, SILU. Applies the sigmoid linear unit function, element-wise. The SILU function is also known as the swish function. So this is similar to our ReLU, but we've got a little space here. So it's a SILU activation function. That's how you can learn more about each of these layers. But let's keep going. We've just learned what dropout is. It's going to help prevent overfitting by randomly dropping out some of the neurons. Now we want in features. This is important to be the same number as before. Otherwise, we'll get a shape mismatch. So if we set this to 1,000, we're going to get a shape mismatch because the layer that feeds our classifier layer has an output of 1280. So if that comes into here and we've set it to be 1000, or this linear layer, sorry, the input to be 1000, we're going to get a shape mismatch. So this is the feature vector coming in. Let's do that. Feature vector coming in. And if we've used dropout with a probability of 0.2, it means 20% of the values in this vector will actually be zeroed. And then we want out features. What are we going to set this to be? Well, we can do len class names. Why would we do that? Because we've got, let's go len class names. We've got how many classes? 3. So instead of 1000 classes, we want, how many classes do we have? Beautiful. And now, because we're instantiating a new layer, I'm going to set the random seed here, torch.manual seed, because behind the scenes, when it instantiates linear, it's going to do so with random weights. So for reproducibility, I'm going to set the seeds, torch.CUDA. I'm going to set the CUDA manual seeds because I'm going to put this to the device as well, to the target device. That way, all of the components of our model are on the target device. And what I might do now, so just take note of what this is. Before I forget, I'm going to send our model that we imported before to the target device. Model equals torch vision models, EfficientNet B0 to device. So now our model is going to be on the GPU. Then if we have a look at our current model.classifier, we've still got dropout, in features 1280, out features 1000. That's still for ImageNet. We get a summary. This is all of our models' base layers are still trainable because we haven't set their requires grad parameter to false. Now if we do that, and if we do that, and here we're going to update the classifier head of our model. Just take note of the output here. Watch how this changes based on what we've set here. Model.classifier equals the sequential here. We'll run that. Beautiful. Look at that. How exciting is that? We've got a feature extraction model ready to use now. So we've changed the out features to 3. Let's have a little look here at the difference between the previous summary and this one. We've got a partially trainable EfficientNet. We've frozen all of the base layers and we've updated the output layer here, the classifier head, to suit our own problem. Now notice we've got quite a dramatic difference in parameters now. The total parameters of our model is all of these values here. However, all of these parameter values are frozen. These are directly from ImageNet. The only trainable parameters in our whole feature extraction model is the output layer. So with that being said, how about we train this model? Let's see how it performs. Do you think it's going to do worse or better than our tiny VGG model on our pizza, steak, and sushi data? Well, I guess there's only one way to find out. I'll see you in the next video. Welcome back. So this is the model that we've created, an EfficientNet feature extractor. Our input data for when we train the model is going to be images of pizza, steak, and sushi. We've got the EfficientNet B0 architecture, which we've frozen. It's pre-trained on ImageNet, so we're going to use those weights to find patterns in our own custom data. And we've also updated the classifier head layer here so that it works for 3 classes, in other words, pizza, steak, and sushi. And if we keep going, this is what we did. We started with this, a model that had all of the layers as trainable, and it had 5 million or just over 5 million trainable parameters. But then, what did we do? We updated it so that it no longer has all of the layers of trainable, and the output layer here no longer has 1000 classes, it has 3 classes suited to our problem. And so, we changed the classifier head. We've got, this is the original, and this is the new one. We keep the features the same. Classifier head, out features gets changed. That's all we've done. Keep the features the same, change the classifier head. And we're left with this. Now, most of the layers in our model are not trainable because we set their requires grad attributes to false. but the output layer is trainable. And we've got 3 output neurons. And so we have a dramatically less number of trainable parameters. So hopefully our training should be quick. And let's test it out. We will create here. Section 4 is train model. So let's see if we can beat our tiny VGG results that weren't too good. So to start off, we will define a loss and an optimizer. The loss function is going to be nn.crossEntropyLoss. And the optimizer is going to be the faithful atom optimizer that we've used plenty of times. And we want to optimize our model parameters. We'll set the learning rate to 001. Shift and enter. Beautiful. We've got a loss function and an optimizer ready to go. Now, because we've imported the Going modular scripts over here, we've got engine.py, which contains our train function that we created previously in section 5. There we go, train. This is going to leverage test step and train step. So let's import the train function from engine.py. Import train function. Or in fact, we'll just from Going modular, modular.going modular, we will import engine. And then we can set the manual seeds, because whenever we train, we're going to leverage randomness to optimize our model. And we'll go torch.manualSeed 42 and torch.CUDA.manualSeed. We'll set that to 42 as well. Now we'll start the timer. These are steps we've seen a few times before, so we're going at a little bit of a faster pace now. So from timer to import default timer, default underscore timer that is, as timer. And then we'll set the start time equal to timer. And let's set up the training. This is so exciting. Our first transfer learning model, and save the results. So we're going to save the results to a dictionary, and we'll set engine.train to train the model. Model equals model. The train data loader is going to be what? The train data loader that we've created before. The test data loader is going to be the test data loader that we've created before. Then we've got our optimizer in the cell above. And we've got our loss function, is our loss function in the cell above as well. We'll keep it nice and short, just 5 epochs to begin with. You could always train for longer if you wanted to. And then the device is going to be our target device. You see how beautiful it is? The fact that we can just leverage our train function now. That's only a few lines of code, and we've mimicked the functionality of what's in here. We've got all of this functionality by calling this engine.train. How beautiful is that? So let's now end the timer, and we're going to train our first transfer learning model. This is so exciting. This is my favorite topic in all of machine learning, transfer learning. And print out how long it took. So end time equals timer. And then we're going to print out a little info tag here. Info, and we'll go total training time is going to be the end time minus the start time. How do you reckon this is going to go? Let's place some bets now. Is the transfer learning model, the EfficientNet B0 trained on all of ImageNet, going to outperform our tiny VGG? Do the extra parameters help? So our model has 4 million total parameters, but only 3,000 of them are trainable. So let's see. 3, 2, 1. Have we got any errors? Maybe we do, maybe we don't. Ooh. Oh, I've got a space there, do I? Oh, what happened there? Excuse me. We did have some errors. There we go. Training started. Oh, this is beautiful. Oh my gosh, already at 55. 81% accuracy on the test data set. 85% accuracy. 86% accuracy on the test. 88. Oh my goodness. We have reached 90% or nearly 90% accuracy in 5 epochs in 13 seconds on our pizza, steak, and sushi data. What? Now, just a reminder, don't worry too much if your numbers aren't exactly the same as what I've got. The trend should be quite similar, as in your test accuracy should be going up, your test loss should be going down. But don't worry if the numbers aren't exactly the same. That's due to the randomness of deep learning. and it will be quite random despite setting the random seeds depending on the hardware you're using. So does that mean we've beat our tiny VGG model with transfer learning? If we go back, this is custom datasets, section 4. Our tiny VGG ended up with about 20% test accuracy in, how long did that take? 65 seconds? Why did that take so long? Was that on the GPU? Oh my goodness. We just wiped the floor with our tiny VGG model. All with the power of transfer learning. Look how, all of these layers contributed to our model performing at nearly 90% accuracy. I would be happy shipping a model that was that accurate. But let's not take these values as numbers on a page. Let's keep going and evaluate our model. We're going to evaluate our model with plotting loss curves. So we've done this previously. You might want to go to here and go plot loss curves and look how we plotted loss curves in the past and give that a go. Otherwise, we have a helper functions.py on the GitHub with a plot loss curves function. So you might want to either import that into this notebook and plot the loss curves from the results dictionary, which looks like this, and inspect them. So give that a shot, try to plot the loss curves of our first transfer learning model, and we'll continue with the evaluation in the next video. We just trained our best performing pizza, steak, and sushi, or Food Vision MIDI model throughout this whole course. That is super exciting, all with the power of transfer learning. We got nearly 90% accuracy on the test data set in 13 or so seconds on my Colab instance. Your time may vary and your exact numbers may vary, but don't worry too much if they're slightly off. Now let's continue with the evaluation and see if these numbers on a page are really as good as they seem, or are they not as good as they seem? They're just numbers on a page that look good. So we're going to start plotting our model's loss curves. You might have already given this a shot because I issued the challenge in the last video. We evaluate our model by plotting loss curves. Let's create a section here. So we've got a helper function, plot loss curves. We could just copy that in, or we could write some code to download this helper functions.py script into our notebook. So let's do that. So I like to work with things programmatically. We will try to import from helper functions. We will import plot loss curves is the function we're after. So that means it will look over here to see if there's a helper functions.py file. This will fail. So print failed. Then we might need except print failed. Failed the try. There we go. So this didn't work. So what we need to do is fill in some code here to download this file into here so that we can import helper functions.py, or particularly the plot loss curves. So let's write some info here. Info couldn't find helper functions.py. Downloading. Oh, excuse me. Downloading. And then we'll go with open. We're going to use the request library here as well. Helper functions.py. We want to create. So this is write binary as F for file. We're going to import the request library here. We don't actually need to do that here, but we're going to do it anyway, just for completeness. Request equals requests.get. So we want to get the download or the raw version of this. So this is PyTorch Deep Learning, and this is helper functions.py, and we want to copy the link of the raw version. So paste that in there. This needs to be as a string. Wonderful. And then we're going to write it to F, which is this file up here. So it's going to write the contents of this request to helper functions.py. Write request.content. And then we can, because we've got it now, we're going to import the helper functions, plot loss curves function from helper functions.py, and this should work. Plot the loss functions or loss curves of our model. So this is the loss curves of our first transfer learning model. Plot loss curves results. Downloading it. Beautiful, look at that. So we got helperfunctions.py over here. Now we've got access to all of the functions in here if we wanted to. But look at those loss curves. They are some good looking loss curves. We've got the train loss and the test loss going down, and the train accuracy and the test accuracy going up. So do you think if we were to train this for longer, our model's results would improve? Potentially, right? They're heading in the right direction. We want the loss to go down, how wrong our model is, and we want the accuracy to go up. So that could be some extra curriculum for you, is to try training this model for longer and see how low the loss goes and see how high the accuracy goes. But also another challenge for you is to, if we look into here, this is section 4. We had a look at what should an ideal loss curve look like. So I'm going to just copy this here and I'm going to write, what do our loss curves look like in terms of the ideal loss curve? See here for more. So I'm just going to get rid of this, turn this into Markdown. So if we go back, recall, here is what the ideal loss curve, the Goldilocks loss curve, train and test loss go down similarly. Overfitting is when the train loss is lower than the test loss, and underfitting is when both loss could be lower. So to me, this looks like our model is doing pretty darn well. Our train loss and test loss aren't too dissimilar, and they're both going down quite rapidly. That's what we'd like to see. But if we would go here, how to deal with overfitting, so our train loss is lower than the test loss, one way to improve that is transfer learning, which is what we've done here. We've used pre-trained weights for our own problem. Transfer learning is one of the most powerful techniques to not only prevent overfitting and underfitting. So we've seen that in practice. So if you'd like to read a little bit more on this, we've covered this in a previous video, but now that we've seen some good loss curves, just go back and have a read of this again and see what it jogs in your memory in the terms of the loss curves that we've got here. So we've seen some loss curves, we've seen some numbers on a page. Let's keep going. Let's keep evaluating our model, but this time we're going to do it qualitatively. Let's make some predictions on images from the test set. In fact, you might want to try this yourself, is use the trained model, we've done this before, and make some predictions on random images from the test set. Give that a go, and I'll see you in the next video. Let's make some predictions with our best performing model. We've seen how well our model performs quantitatively by plotting the loss curves and evaluating it here with the test accuracy metric. But now let's do one of the most fun things in machine learning, and that is make predictions on the test data and even some custom data. So make some predictions on images from the test set. And there's a few things we have to keep in mind when we're making predictions on images or on any kind of custom data. Do you recall what they are? And it's okay if you don't, that's why we're going through this again. So let's adhere to the Data Explorer's motto of visualize, visualize, visualize. And make some qualitative predictions on our test set. Let's write down some things to keep in mind. When making predictions / inference on test data / custom data. This comes all down to formatting. So we have to make sure that our test / custom data is the same shape. So images need to be same shape as model was trained on. Of course, you can vary the shape. You could make them smaller, you could make them larger, but to get similar performance to how your model went during training, you have to make sure your data is in the same shape. And then we need the same data type. So custom data should be in the same data type. what else is there? We need the same device. So custom data / test data should be on the same device as the model. We've seen all of these errors before: shape errors, data type errors, device errors. There's one more that we've gone through in this notebook, and that is, what did we do? Right up here, we created transforms for our images. So this is kind of the same shape and same data type, but I'm going to put it here as an extra one as well. Same transform. If you've transformed your custom data, ideally you will transform the test data and custom data the same. Now, of course, these are all come with an asterisk. You don't necessarily have to do all of this, but to prevent errors and to ensure you get similar performance as to what's been printed out here, you'd like to go through all of these steps for your test and custom data. So how about we create a function to do all of this magically? Let's create a function called pred and plot image. Now, we've done a similar function to this back here. Yeah, there we go. This is section 4. Putting custom image prediction together, building a function. We're going to use a very similar function to this, but with a few tweak steps, just for some practice. So I'm going to put this in here. We'll go here. The function will be similar to the one here. So you can go read that if you'd like. But let's start with step number 1. We want to take in a trained model. We'll start with a model. Take in a trained model, a list of class names because we want to map our model's predictions to the class names, a file path to a target image, an image size for how much we should format the image, and a transform and a target device. So that means we're just taking care of all of these shape, data type, device, transform steps. Particularly transform will take care of most of them. Then what do we want to do? So 2 is open the image. We need to open the image. Open the image with, let's use pill this time. Pill image.open. Step number 3, we want to create a transform if one doesn't exist, because we want to make sure our images are transformed by default. And then 4, we want to make sure, no typos here, Daniel, come on. Make sure the model is on the target device, very important. That's going to take care of this one here, same device. We'll have to subsequently also make sure the data is on the same device, won't we? And then we want to turn the model to, we want model.eval mode to make sure it's ready for inference. This will turn off things like, and then dropout gets turned off during inference. And recall, you can find out what is dropout by going like this. What is dropout? There is plenty of different resources for that. It's mainly a regularization layer to prevent overfitting. Then we will go, we want to transform the target image and make sure its dimensionality is suited for the model. This mainly relates to batch size. We want to make sure if we're passing in a single image, it has a batch size of 1. We can do that with the unsqueeze method. We're going to see all this in code. We're just typing out our steps here. Make a prediction on the image by passing it to the model. We'll do the forward pass. And then we want to convert the model's output logits to prediction probabilities. We can use Torch softmax for that. Torch.softmax. We've seen this in the past. And number 9 is convert model's prediction probabilities to prediction labels using, what do we do here? We use torch.argmax because we want to take the prediction probability or the index where the prediction probability is the highest, and that is the model's predicted label. And then we want to plot the image with matplotlib because we want to get visual after all, don't we? And set the title to the prediction label from step 9. And for a little bit more, why don't we also add the prediction probability from step 8? Oh my goodness, this is going to be one full-on function, but I think rather than do it in this video, I'm going to issue you the challenge to try and create a function that goes through all of these steps. I think you can do it. And if you want a reference, we've done this in section 4, a very similar function here. 11.3, go and check that out. You can reference this function as much as you want, but try to go through these steps and see if you can get our model to make predictions on a random set of images from the test data. And we'll go through these steps in the next video. I'll see you there. Welcome back. In the last video, we left off. I issued you the challenge of creating a function called pred and plot image that goes through these steps. You might have already done that. So if you did, I applaud you for your efforts, but if not, let's do it together now. See how I might make it. And again, there are many different ways to do these sort of things. That's the beauty of programming. So this is just one of many. I'm going to import some typing modules. Now I'm also going to import image. So I can take care of this step here, number 2. And let's start it off by going through step 1. Take in a trained model. I'm not going to type out everything. I'm just going to refer to step 1 here. We want def pred and plot image. And we're going to go model is going to be of type torch nn.module. This is going to be our trained model. And then we're going to pass in an image path. That will be a string. So that will be a path to a test image up here. Then what else do we need? A list of class names. We'll go here. Class names. This will be a list of strings. And then we want an image size. This is going to be a type of tuple int. And we'll set this by default to be 224, which is the size that we've used for training so far. Then we want to transform. We'll set this to torch vision, or the type hint will be torchvision.transforms. We'll set this to none by default because we can create an automatic transform in this function. And the device is going to be torch.device, and we'll set that by default equal to the target device. I think that looks pretty good for step 1. So step 2, let's open the image with pill. Step 2, open the image with pill. We want to set up img for image equals image.open, and then we'll pass it in the image path. So the image path is just going to be a file path to an image. We'll open it up. Beautiful. Now what do we need to do? Step 3, create a transform if one doesn't exist. So create a transform if one doesn't exist. So by default, we've set the transforms equal to none. So let's write a little check here. If transform is not none, so if there is a transform passed to this function, we want to go image transform equals, or transform equals the transform. However, if one doesn't exist, let's just create one manually, like we did up in section 2.1, I believe. Yeah, a manually created transform. Recall that there are 2 ways to create transforms with the new Torch Vision API, manually or automatically. So this just gives us, having a parameter here like this, just gives us an opportunity to use either. So image transform equals transforms, or what we might do is just make sure we don't need to import all of these other things, but we're going to anyway, just so this function is complete in itself. From Torch Vision, import transforms. And then we go transforms dot compose. Then we're going to create a list of transforms here. The first one will be transforms dot resize, and we're going to resize that to be the image size, which will be a tuple. By default, it is 224. Then we're going to transforms.toTensor, turn all of the values between 0 and 1, and then we will normalize using transforms.normalize, and then the mean is going to be, well, I always forget these numbers, so that's why we go normalize. Yeah, there we go. We can just copy this down into there. So we'll just jump back down to here. We just want to normalize our image values to have the same distribution as the ImageNet dataset. Wonderful. So then we've got an image transform. So now what are we up to? We're up to step 4. Make sure the model is on the target device. Okay, let's start our prediction pipeline here. So predict on image. And we'll go step 4 is make sure the model is on the target device. Otherwise, we'll get device errors. So model.toDevice, that's easy enough. And then what do we want to do? Turn the model to model.eval. I will have to turn on inference mode as well. That's one thing I left out there, but that's okay. Turn on inference mode and eval mode. So model.eval, that'll turn off things like dropout. And with torch.inference mode, that'll turn off a whole bunch of things such as gradient tracking and whatnot, so our inference is as fast as it can be. So we've got inference mode there. 6, transform the target image and make sure its dimensionality is suited for the model. So what we're going to have to do here is 6. We've got a transform above, our image transform. Let's go transform the image and add an extra batch dimension. We need to add an extra batch dimension because we're only dealing with one image at a time through this function, and our model expects a batch dimension. So transform image is going to be image transform, which is what's above, image transform, working on image, and then we're going to call unsqueeze to add an extra dimension on the 0th index. So this will result in an image with batch size, color channel, or a shape, sorry, color channels, height, width. Then what do we have next? Step 7, make a prediction on the image by passing it to the model. Now, we have to also ensure that our data is on the same device, don't we? We haven't done that yet, so we might do that right here. Make a prediction on the transformed image by passing it to the model. Also ensure it's on the target device. So we're taking care of device issues here. So target image pred is going to equal model. We'll pass through the transformed image from the line above and we'll send that to the device. So that way our model and our target image are on the same device. Beautiful. We are now up to step number 8, which is convert the model's output logits to prediction probability. So this is going to be our output logits here. So let's convert the model's output logits to pred probs. So target image pred probs equals, we'll call torch.softmax on those logits. So target image pred, which is from the line above, on the first dimension. And then we are up to step 9. Look at us go. This is going to be one hell of a function. So convert models prediction probabilities to labels, and then the next one is plot the image with matplotlib. Okay, I think we can do both of these in one hit. So convert the models pred probs to pred labels. We want to take target image pred label equals torch.argmax. We want to take the index number where the prediction probability is highest. That's going to be our model's predicted label. So target image pred probs on the first dimension. And then step number 10, we've got the pred probs, we've got the label. Let's now plot the image. So plot image with predicted label and probability. So plt.figure to create a plot, and then plt.imshow. We're going to show the image. Now, we're showing the image here. We're showing the unformatted image. Now, that's important because matplotlib will error if we try to pass it in the transformed image because it's not the right dimension size. So we'll just take the image as it's been opened by PIL. And let's keep going here. We'll go plt.title. Let's create an F string. The pred is going to be class names indexed with the target image pred label. And let's create another F string here with the prob will be target image pred probs, and we'll set that to 3 decimal places. All right, I think we're on here. And we'll turn the axes off so we get a nice, beautiful plot. Oh my goodness. So there's bound to be some sort of error in this function, but I'm going to leave that as a challenge for you to try out. I think we've got what we need, and if there is an error, we could probably fix that quite quickly. But now here's your next challenge for the next video. We've got all of these steps, we've coded them out. So now we want to make predictions on the test dataset images. So my challenge to you is write some code to get random image paths from the test dataset, maybe 3 random paths of all of these images, and pass them through this function in a loop and plot the images as well as our model's predictions. So give that a shot, and I'll see you in the next video. Let's make some predictions on our test data. In the last video, we created one hell of a function, pred and plot image. Now, I haven't tested this out yet. Maybe you have, trying to predict on random paths from the test data set. And if you have, well done for the effort. Otherwise, let's try it out in this video. This is so exciting. Making predictions on the test data set is one of my favorite things to do with a trained model. So what we want to do is get a random subset, because I love the power of randomness in machine learning. Get a random subset of image paths from the test data set and run those image paths through our function, and hopefully it returns some plots of those images and the correct prediction labels for those passing through our model. So let's start off. We'll write some code to get a random list of image paths from the test set. And we'll import random for that. And 3 images should be enough. We could always increase this. Num images to plot equals 3. And then let's go test image path list equals list of path. And then we're going to pass in the test directory, which recall is tester. So we'll pass in, we'll get the list of path, and then we'll get a glob. I love that word, glob, of star.jpg. So what this means is that we are going to match this file path, so data, pizza, steak, sushi, test, for star, so any of these options, pizza, steak, or sushi, and then star for any file path, so anything.jpg. So that's going to be hopefully all of the images in our test data set, or their paths, that is. So let's have a look at what this is. Wonderful. So we've got now a list of all of the images in our test data set. I love the glob module. So if we go, how many test images are there? Should be about maybe 100 or so. I can't remember exactly, 75. Okay, so now let's randomly select 3 of those so that we can create another list. Test image path sample, a list sample of the full path list. We want to go random.sample. The population we're going to sample is the list that we just created, test image path list in the line above. And then the number of Ks we want to get, or number of samples we want to randomly select, is num images to plot, which is this value here. So this is just saying get 3 random paths from the path list. Path sample. Beautiful. Random pizza, pizza, sushi. Now what do we get? Pizza, sushi, sushi. Pizza, sushi, sushi. Steak, sushi, steak, sushi. That's it. Wow, try to say sushi fast 20 times. Now, let's use those paths to make some predictions. So, make predictions on and plot the images. So, we can go for image path in test image path sample, which is just the 3 image paths that we have here. We're going to loop through that, and this is where we're going to test out our big dog function above. Pred and plot image. The model is going to be the model, and the image path will be equal to the image path, and then we'll set the class names equal to the class names. So we've got a list of class names already, just to make sure. We'll just reiterate. Class names, wonderful. And then finally, we can set the image size to 224, 224. but that's going to be set by default, right? So you ready? We're using our transfer learning model, our best performing model on paper, to make predictions on our test images. So these are images our model has never seen. 3, 2, 1, let's go. Or didn't see during training, that is. Oh no, what did we get? Unsupported format string passed to tensor format. Class names, image size. Okay. Do we get the same error if we run it again? Oh no. Okay, this is good. We have an error. Unsupported format string passed to tensor format. What have we got up here? We've got something wrong here. I'm going to find this error and I will pause the video and I will come back and I'll show you once I've found the error. Okay, I've found the error. So you see here, this prob is what we're getting wrong. This error is saying unsupported format string passed to tensor format. So we're trying to reduce the target image pred probs to 3 values. However, let's print out target image pred probs as we go through. Look what happens. It's a tensor. So we need to take the max value of this, dot max, or if we just go here, see what happens if we take dot max, run. And there we go. Okay, beautiful. So we can comment this out. Little error there. I knew there would be at least one error, but let's have a look at our best model yet predicting on our test data set. So we got steak, sushi, steak. Very good. Okay, let's try one more. What do we got here? Sushi, pizza. Our model is looking pretty good. Is it going to get one wrong? Sushi, steak. Oh, that's close to being... Oh, that's steak, yeah. Okay. And we'll go again. One more. What do we get? Pizza, yum, steak. Oh, got that one wrong. That's pretty blatantly sushi. And pizza. Okay, so our model could still be improved, but that's okay. It's doing a lot better than what it did in the past. So now, the real final challenge, looks like our function is working to predict on images. How about we predict on the image we've been using a few times now, and that is Pizza Dad. So if you go into PyTorch Deep Learning, there is an image here in Images under 04, Pizza Dad. Try and predict on this image with our trained model. So you might have to download it into the notebook with this link address and then pass it through our function. That will be the ultimate test. Or you can get one of your own pizza, steak, or sushi images and run it through this function and see how the model goes. So that's your challenge for this video, and we'll do it together in the next video. In the last video, we made some qualitative predictions or qualitative evaluations with our model using our pred and plot image function. We saw that our first transfer learning food vision mini model that is doing pretty darn well. But one of the real tests of a machine learning model is predicting on your own custom data. So making predictions on a custom image. Let's get in Pizza Dad, what we've been using so far. So let's make a prediction on the Pizza Dad image. So of course, ideally, our model will predict pizza on this image because there is a pizza in the image. So let's download the image if it's not here. You might have already tried this, by the way. So if you have tried it yourself, I applaud you, but if not, that's okay. Let's do it together. Let's set up the custom image path. We're going to go custom image path. We'll set it up to equal the data path /04. We'll just use the same name as we've got here. 04 pizza dad.jpg. And then we'll go download the image if it doesn't exist. So this is where we're going to use the request library again. So if not custom image path .is file, so if the file doesn't exist, we want to go with open custom image path. And again, because we're writing a file here, we will set the permissions to write binary as F for file, and download image from GitHub with raw link. So when you're downloading from GitHub, you want the raw link. So you want to copy this link address. And so let's see what that looks like. Request equals request.get. We'll pass it into there. So we see how we've got the raw value here. That should download the file. And then we're going to print F. We're going to go downloading custom image path. ... Beautiful. File.write request.content. So the content of the request. That's all we're doing, writing that content to the F, to the file. And then let's print out a little else statement. If the image already does exist, else, let's go print F. We want to go custom image path already exists, skipping download. Beautiful. So let's download the image. Downloading Pizza Dad. Now if we go into here, data, do we get Pizza Dad? pizzadad.jpg. Pretty big image, so I think Colab might have a little bit of trouble visualizing it. Okay, let's just pretend that it's there rather than, okay, it's visualized. Just had to be patient, Daniel. There's my dad. And there's the pizza. Big image, but that's all right because we've got our pred and plot image function that's going to format the image for our model. So predict on custom image. This is super exciting. Let's go pred and plot image. How do you think it'll go? Do you think it'll beat tinyVGG? Model equals model, and then we'll pass in the image path equals the custom image path, which is what we created here. pizzadad.jpg. And then we're going to go class names equals class names. And everything else should be by default. You ready? We're using our first transfer learning model for Food Vision Mini, predicting our own custom data. 3, 2, 1, let's go. Oh, pred pizza probability 0.517. That looks good to me. Of course, don't worry too much if your number isn't exactly here. Model should be pretty close to being right though. So let's check up here. This is 04. This is tinyVGG. It got a prediction probability. It got it right, but only a prediction probability of 373. So this is leading me to believe that this model is more confident in its prediction of pizza on this custom image. In fact, what we've done is we've built a model. We've created a backbone of EfficientNet B0. If we go here, customized it to our own data of pizza, steak, and sushi over here. And now that model is using patterns that it's learned on ImageNet plus the custom data that we've passed it to predict on data from the wild. Now, you could use this same function to predict on your own custom images. And in fact, I encourage you to do so. And if you do, please share them with me. I would love to see that. But this is the same model that I'm using in production, same type of model, EfficientNet B0, on my project, Nutrify, to take a photo of food and learn about it. If we upload an image, the same image here, 04 Pizza Dad, have a look at this. Predicted food, pizza. So this is working on a website. You can go to Nutrify.app right now and try this out. And then it's going to tell you some information about that. So this is some ideas of where Food Vision Mini could go. Nutrify works for about 100 foods right now, but that's going to increase. Food Vision Mini only works for 3 foods. So potentially, if you want to expand this, you could try to add more training data and see how good of results you can get with transfer learning. And recall here, we've only got about 70 or so training images per class, which isn't too many in the context of deep learning. So that's the power of transfer learning. Let's now finish this up. We'll go through some main takeaways, and I've got some exercises and extra curriculum ready to go for you. So we'll discuss that in the next video. I'll see you there. A big 2 thumbs up for how well our first ever transfer learning model is going. But let's now jump into here. We're going to jump into PyTorch Transfer Learning V2 for now, but just so you're aware, this will probably not be V2 by the time you watch it. you can just go to PyTorch Transfer Learning. And if we scroll down here, we've got the main takeaways. So we've kind of hashed over this stuff already, and you've seen it in practice, which is more important. But transfer learning often allows you to get good results with a relatively small amount of custom data. And knowing the power of transfer learning, it's now a good idea to ask at the start of every problem, does an existing well-performing model exist for my current problem? And recall that we went through a few places to get pre-trained models. You can have a look at those here. Then if we go back, when using a pre-trained model, you have to ensure that your custom data is formatted and processed. We did that using transforms in the same way that the original model was trained on. Otherwise, you may get degraded performance. And the same thing goes for when predicting on custom data. So we saw how we had to write a big function to format our own custom data when making predictions for the model. And we rehashed on this. There are several different places to find pre-trained models. So a big takeaway from this is when you're starting a new machine learning problem, if you want to leverage the power of transfer learning, ask yourself the question, does an existing well-performing model exist for my problem? So to practice everything we've learned, I've set out some exercises. I'm going to delete that and just copy this one in here, because by the time you watch this, it'll be PyTorch Transfer Learning, not V2. So let's create a heading here. Exercises. See exercises and extracurriculum to practice what you've learned here. So that'll be in the book version of the course, PyTorch Transfer Learning /exercises. And we've got some options here. I'm not going to go through them all. That will be for you to explore. There's also some extracurriculum to look up some things that we've mentioned in this section, but haven't necessarily gone through. And if you want an exercise template, there's also solutions notebook, and there is also a video walkthrough of the solutions on YouTube. So I'm just going to pause that, of me going through the exercises myself. Here's a solutions notebook. You can see that on PyTorch Deep Learning Extra Solutions. And here's a template that you could start with this and fill in the code here. So you'll have some to-dos and to-do. That's for you to fill out. I've only put in the boilerplate code here that we've covered a fair few times. To do. Beautiful. But this will be under PyTorch Deep Learning Extras Exercises. You can find that there. Otherwise, the links are at the bottom of the book version of the course. But thank you so much for following along with the transfer learning, my favorite topic. Let's now go into the next one. Number 7, PyTorch experiment tracking, but no spoilers. I'll see you there. Welcome to experiment tracking with PyTorch. Now, experiment tracking is such an important topic in machine learning. You can consider this your first milestone project. So welcome to Milestone Project 1, Experiment Tracking with PyTorch. We're going to be putting everything we've learned so far together into one big project and track several experiments for our Food Vision mini project. But let's get started answering the most important question: where can you get help? The first thing you can do is to follow along with the code. If in doubt, run the code. If you're not sure of something, see what its inputs and outputs are. Try it for yourself. Press Shift Command and Space to read the docstring for help of any of the functions we're using. If you're still stuck, try searching for it. You'll probably come across Stack Overflow or the PyTorch documentation, which we've had plenty of hands-on practice with so far. Then, of course, try again. If in doubt, run the code. And if you're still stuck, you can ask the question on the course discussions page. So you can click New Discussion here and then give some information about what you're working on. And then, of course, the notebook we're going to be working through is number 7, PyTorch experiment tracking. You can find this notebook on GitHub. We're going to be referencing this throughout the series of videos coming up. And then, of course, there's the book version of the notebook, which is searchable and has a bunch of different headings at learnpytorch.io, number 7 here, PyTorch experiment tracking. So let's jump back into the keynote. You might have the question, what is experiment tracking? So we've built a fair few models so far. We've started with tiny VGG. We saw that didn't work. And then we tried the power of transfer learning in the last module, and we saw that did work pretty well. So experiment tracking is the answer to the question, how do I know which of my models has done the best? And so if you refer back to one of the beginning sections where we covered the how to approach this course, first and foremost is to code along, write the code, try it out, explore and experiment, visualize, ask questions, do the exercises, and of course, share your work. We have 3 mottos. If in doubt, run the code, experiment, 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 visualize, visualize, visualize. And so what we're going to be covering in this section is we're going to be diving deep into the experiment, experiment, experiment motto, and we're going to be tracking our experiments, more specifically, our modeling experiments with Food Vision Mini. So put on your scientist coat, let's get started. Now you might be wondering, why would we track experiments? And I've kind of hinted at this already, but and we've seen it. If we were to build multiple different models, experiment tracking can quickly get out of hand. So let's say we started with number 0 and we tracked it in a dictionary called results. Then we had model 1 results, model 2, model 1 v2, model 2 v2, model 2 v3, model 2 v... Oh my goodness. And we just keep going. And I've cut it off here. And we've got a lot of experiments here. And you can see this is only 13 models. And in reality, you're going to be building a lot more than that when you start to work on your own machine learning projects. So it's important to have your experiment tracking in some form of reliable way that you can go back and investigate. So, how do you know which one of your models performs the best? Well, that's what we're going to answer the question with experiment tracking. So if all of these are like, no, 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 yes, number 11, and then no, 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 what should you do less of? And what should you try more of? That's the whole purpose of experiment tracking. Figure out what doesn't work, so you can figure out what does work. Now, there are a few different ways to track experiments in PyTorch and machine learning in general. The first is what we've been doing so far, such as using Python dictionaries, CSV files, or printouts. The next is TensorBoard. We're going to be looking at this in this section because of how baked in it is to the PyTorch library. There's also other services like Weights and Biases, which is one of my favorite third-party experiment tracking resources. I'll let you look into that if you'd like. It's a beautiful user interface to track all of your different modeling experiments. For example, look at the accuracy measure there, the loss curves there, validation accuracy, how much GPU is being used. And then there's also libraries such as MLflow, which is an open source library for the entire machine learning workflow, essentially. And then, of course, because experiment tracking is such a large problem in machine learning, if you just searched track machine learning experiments, let's just see what happens. Track machine learning experiments. What comes up? 15 best tools for machine learning experiment tracking. Oh, this is one of my favorite resources, actually. This is in the extracurriculum section. Made with ML, experiment tracking by the amazing Goku Mohandas. So this is your extracurriculum if you'd like to read up a little bit more about experiment tracking. In fact, I recommend all of Made with ML's resources. So go and check that out, especially this resource here. But let's jump back in. We've got a few places. We're going to be focusing on TensorBoard, but really the principles of experiment tracking that we're going to be going through are relatable to any service that you use. So this is what we're going to build. We're keeping going with Food Vision Mini. We're going to introduce experiment tracking. So say we ran a bunch of different modeling experiments. This is only 4 here. We're going to be running more than that. So 1 didn't work, 2 didn't work. Oh, number 3 works. And say, this is the results here. We've got some loss curves down here, some accuracy curves. We're going to see this in action. We're going to be writing code that we can generate something like this to build a series of models on our Food Vision Mini problem and see which one is the best. And to get a little bit more specific, here's what we're going to cover broadly. We're going to get set up, so importing our previously written code that we've done in last sections. We'll introduce experiment tracking with PyTorch and TensorFlow. We'll build several different modeling experiments for Food Vision Mini. We'll evaluate those modeling experiments with TensorBoard. And of course, we're going to be making predictions with the best performing model on our own custom data. And how? Well, we're going to be putting on our scientist coat to track our experiments, but also our chef's hat, because machine learning is part art, part science, so we're going to be cooking up lots of code. And speaking of, I'll see you in Google Colab. Let's code. All right, let's code. We'll jump over into Google Chrome or whatever browser you're using, and I'm going to go to colab.research.google.com. I'm going to load up a Google Colab notebook. Wonderful. And I'm going to name this one PyTorch Experiment Tracking. And I'm going to give it the video tag at the end here, just so you know when you look at this notebook on GitHub, it's from the video. And I'm going to give this a heading 07 PyTorch Experiment Tracking. And I'm going to write a little note here just to introduce it. Machine learning is very experimental. We've seen this so far. We've run a bunch of different modeling experiments so far. And in order to figure out which experiments are worth pursuing, that's where experiment tracking comes in. It helps you to figure out what doesn't work, because that's the nature of science, right? If you figure out what doesn't work, so you can figure out what does work. So in this notebook, we're going to see an example of programmatically tracking experiments. And so I'll just put some resources here so you know where they are. So of course, we've got the book version of the course. We'll actually just go to the top of the heading here. This is learnpytorch.io, number 7. This is the notebook we're going to be going through. So we'll just come over into here. So book version of notebook. Wonderful. And then ask a question, very important. We'll get up GitHub discussions if you are stuck for anything related to this course. And then this is not part of the course, but it's some great extracurricular material. Madewithml.com is one of my favorite sites, so I'm going to put this here, extracurriculum. Just to start it off, we haven't even covered any code and we're already covering the extracurriculum. So let's get started. I'm going to clean up some of my tabs here. And so to begin, I'm going to make sure I'm using a GPU, because this might restart the runtime. Yeah, there we go. So click to connect, making sure I've got a GPU. Otherwise, we'll have to restart the runtime again later on. GPU backend. Beautiful. Now, this section uses some updated PyTorch and Torch Vision APIs, which currently aren't installed at the time of recording, that is, into Google Colab. Well, they aren't actually even released by PyTorch just yet. So that's how cutting edge this course is at the time of recording. So I'm just going to print this out just so we see. We need Torch version 1.12 plus and Torch Vision 0.13 plus. So as you can see, my Google Colab instance doesn't yet have those. If yours does, you can continue with the code here, but I've got a block of code in the book version of the course. So just at this link here, number 7, if we go down to getting set up, if we run this block of code, I'll copy that. Bring this in here. What it's going to do is going to try to make sure we've got the right versions of PyTorch and Torch Vision. And if we don't, it's going to run this install command to install the nightly versions. And that's from PyTorch getting set up. We go to get started. We've got start locally. We want Linux because that's what Colab runs on, pip, and CUDA for GPU. We're just running this command here so we get this one. So we get the nightly versions, which aren't yet out and aren't yet the default in Google Colab. So if you have the right versions, this will run automatically. If you don't, it will install them. So let's run this. It'll take about 3 to 4 minutes to run, and I'll just pause the video there and I'll see you in a few seconds. Alrighty, so it looks like that took about just over 3.5 minutes on my Google Colab instance. But what you can see here is that the info prints out, Torch/Torch Vision versions not as required. If you do have the right versions, this try block should pass, and it should just say, hey, you've got these versions. But now we've installed the nightly versions, we're going to restart the runtime. Otherwise, I don't have access to those versions I just installed. So I'll click Restart Runtime. We'll see it restart over here. And then I'll just wait for that to load up. And I'll make sure I've got a GPU as well. GPU, beautiful. Save. Have I got a GPU? Yes, I do. GPU backend. So if I rerun these, I should have the nightly versions of Torch and Torch Vision. Wonderful. So there's Torch 1.13, 0.14. These are the minimum versions you'll need for this notebook. So the minimum versions. So if you have a later version by default, well, that's okay. You should be able to run the code we've got in here. And if not, if there's any issues, just leave one on the GitHub and I'll get to it and fix it up. But now we've got the upgraded versions of Torch and Torch Vision. We can also, this is in the Getting Setup section as well, PyTorch Experiment Tracking. We can also import our regular imports, as well as the code we created in PyTorch Going Modular, rather than rewriting all of it. So import our standard imports, Torch Vision, Torch, matplotlib. Even though we've already got it, we'll do it anyway. See if we've got Torch info. If not, we'll install it so we can get a printout of our model summaries. And we'll get our Going Modular scripts from the course GitHub. So I'll just run this. Couldn't find Torch info, installing it. This shouldn't take too long. I'll just let this run. I'll be back in a second. Beautiful. So that only took about 18 seconds on my machine. So now we should have access to all of our Going Modular scripts that we've previously created. For example, here's engine.py. There's all of the functionality we've written in previous sections. And we're going to be altering our train function later on to track our experiments. Well, we've already got them tracking kind of, but we're going to use TensorBoard this time. So that's a little spoiler. That's why we needed to import that code. And while we're here, we might as well finish off by set up device agnostic code. Device agnostic code. We'll set the device equals CUDA if torch.CUDA is available, else CPU and device. We'll just make sure we've got a GPU. And I've got a little helper function in here, section number 7, which is just to set the random seeds. Now, we've done this a fair few times. So if you want some information on what a random seed does, it flavors our randomness. So to try and make things reproducible, I'm just going to create a little helper function, just def set seeds, default on 42, our favorite number. This could really be anything, but we're going to use 42. And we set the manual seed, and we set the CUDA manual seed. So we'll run that so that in our upcoming cells, we can just run set seeds, and we know that the seeds get set. Beautiful. So that's getting set up. Just a note, if you do take a break from this notebook and come back, you will have to rerun these. So just make sure you've got the latest versions of Torch and Torch Vision. Otherwise, some of the code we write with Torch Vision especially might break later on. So just keep that in mind. If you take a break and come back, make sure you rerun these cells up here so we have all of the code that we need. I'll see you in the next video. Now we've got a few helper functions set up with set seeds, we've set device agnostic code up, we've copied in our scripts from the Going Modular section to save us rewriting a bunch of code, and we've made sure we've got the latest versions of PyTorch and Torch Vision. Your versions may be further on than this, so say 1.14 if you're watching this in the future, but for now, these are the minimum versions we need to run this section. So let's keep going on to the next most important step other than getting set up, and that is getting data. So previously, want to get pizza, steak, and sushi images so we can run experiments building Food Vision Mini, because that's the whole goal of this section, is to track various experiments and see which model performs best. So I issued you the challenge in PyTorch Transfer Learning to create a helper function for getting the data. So get data to turn this into a helper function. And you'll be happy to know I gave that a shot myself so I can practice what I preach. So let's check it out. Here's what I would have done. We'll go import zip file. We've written code similar to this before, but we're going to do it again just to practice, you know? There's nothing like writing a bit more code to practice. If in doubt, code it out. So let's set up a little function here called download data. And the goal is we want to be able to pass in a source. So for example, a link from GitHub. And we want to be able to pass in, oh, I've got a typo here. From path lib import path, because we're going to be dealing with file paths. And we want a source and a destination. So source, download data from somewhere. For example, GitHub data, open this up, one of these files. And then destination, we want to save it to somewhere in here. And then we can also go remove source, which could be a bool equals true if we no longer want to keep the source after we've downloaded it. And this is going to return a path. So path. So let's keep going. We want to write a little doc string here of what's going to happen. Downloads a zipped data set from source and unzips to destination. So in our case, as I said, the source might be a zip file in the data folder here, and the destination will be some folder over here, so we have access in our Colab notebook. Now let's get started just like we did before. In previous sections, we'll set up a path to the data folder. We will go data path. This is where the path module comes in, equals path data. And we'll also go image path equals data path slash destination, because this is where we want our images to live, our destination folder. And then we'll go if the image folder doesn't exist, create it. Let's go if image path dot isdir print. We'll get a little info tag here. Info image path directory already exists, skipping download. If it doesn't exist, we'll go else print. We'll get another info tag here with an F string. I love F strings. Info did not find image path and directory, creating one. So this is where we're going to create and download an image path directory. So we'll take this, and if it doesn't already exist, we'll make sure we create it by going imagepath.mkdir, and we'll set up the parents if we need to, so the parent directories. And then we'll set up exist OK equals true. And then let's download the target data. So from here, target file is going to be path, and we'll get the source. So we'll turn the source string, not a piece of source. We'll turn the source string, the source destination of our data, into a path, and then we'll get the name of that path. So for example, if we clicked on this, this is a path here, PyTorch Deep Learning Data Pizza Steak Sushi. The name of this is this. So this is what we are using the path library for from path lib. And I'm just going to get out of a few of these extra tabs that we don't necessarily need. Beautiful. Let's come back over to here. Tab, tab, tab. With open. Now let's open a data path. So we created this before. Data path slash target file. This is where we want to write a file that we download as F. So write binary, that's the WB there. And we'll keep going. We'll create a request here. Request.get. And then we're going to pass in the source. So the source is going to be a download link from here. So if we copy that, so this is what source will look like. Example source. We want the raw link from GitHub. Raw. And we'll keep going. We'll print out another info tag. Info. We will go downloading target file from source. ... Beautiful. Once that is downloaded, let's write that target file to the file. So F, because we're opening up an F and we're going to go to that F, so F for file, write the content of the request. Request.content. Beautiful. And now let's unzip it because we know it's going to be a zip file. Unzip target file with zip file. This is where zip file comes in. Zip file up here. With zip file.zip file, we're going to pass it in the data path / target file. This time it's going to be R permissions for read as zipref. So we're going to read the downloaded zip file, and then we're going to print out another info tag. We don't necessarily need all these info tags. I just like seeing them play out. Unzipping target file, and we'll go data dot dot dot, and then we'll go zipref, which is this up here, zipref dot extract all. So we're going to extract all of the contents of the zip file, image path. Now we'll remove the .zip file if needed. So this is where that remove source bool comes in. So if remove source, let's go os remove data path / target file. This function could actually be improved a fair bit. We've typed out this a fair few times, data path / target file. You might want to save that to a variable or something like that. But let's just finish off this function so we can have some data. We've seen this play out a few times now. Return the image path. So we've set up the image path here. Let's see what happens if we pass in this link as the source. The destination will be a file over here called pizza, steak, and sushi that will store our data. And yeah, I think that should be enough. Let's try out our function, see if it works. Image path equals download data, source. And you might be saying, Daniel, finally, in module 7, we've written a code to functionize the downloading of the data. And you're right. Sometimes it takes me a while to functionize things that I do all the time too. And then destination, pizza. You got to write a fair bit of code to know what to functionize, right? That's my excuse. Destination. And so we should be ending up with an image path here. Let's see if this works. Did not find it. Oh, I've got 3 L's. Did you catch that? Oh, skipping download. What happened here? Did we... Looks like our function could be improved. Okay, so this file is empty. Maybe that's another thing you could do to improve this function. If you do, let me know. So now, if pizza, steak, sushi is empty, it still doesn't download. So let's remove everything in data. There we go, and we'll rerun this. Beautiful. Did not find pizza, steak, sushi directory, creating one, downloading, unzipping pizza, steak, sushi data, and now we have our path is going to be data, pizza, steak, sushi, test. Beautiful. Pizza. Let's have a look. Pizza image. Wonderful. We've got all of our data and it's now functionized, so we could use this function later on. It could be improved though to see if the target directory, if it is empty, pizza, steak, sushi, it still downloads. So maybe that's an enhancement that you could try as some extra curriculum. But let's keep moving forward. We've got our images downloaded. In fact, here's a challenge. In the previous section, we created data loaders and data sets. So my challenge to you is to turn the data we just downloaded, pizza, steak, and sushi, into PyTorch data loaders. And you could use one with manual creation or automatic creation. I'll let you choose. But give that a shot and we'll do it together in the next video. In the last video, we left off by downloading some data. Now we have our data path here for our pizza, steak, and sushi data for Food Vision Mini. And I also issued you the challenge of turning our downloaded images into tensors, but more specifically PyTorch data loaders. And we saw in the last section PyTorch transfer learning with the latest Torch Vision 0.13 Plus. There's 2 real ways to make transforms, and that's manual creation or automatic creation depending on the model weights you're using. So let's take a look at this. You might have already done it, and if you have, I applaud you for your efforts, but let's check it out together. So we're going to be creating data sets and data loaders. So let's start off with 2.1 is create data loaders with manual transforms. And the goal here with our transforms, I'm just going to write this down. The goal with transforms is to ensure your custom data is formatted in a reproducible way, as well as a way that will suit pre-trained models. So that's an important point. We saw that in the last section, transfer learning, that if you're going to use your own custom data with a pre-trained model, whether it be a computer vision model or a natural language processing model, it's important to make sure that your custom data is formatted in a very similar way to what the pre-trained model was trained on. Otherwise, you may get performance degradations compared to the pre-trained model's results. So let's see how we can create a manual transform. Let's go set up the directories. We'll get a train dir for a path to our training directory, image path, and train, and then we'll get a test dir. So our image path is just this path we've created up here from our download data function, and test. Then we can have a look at both of these, train dir, test dir. Beautiful. And since from the last section, PyTorch transfer learning, we're building upon that here in section 7. We saw that our transfer learning model performed quite well. So we're going to be reusing transfer learning models in section 7 when running multiple different experiments. So we also learned that if we go to Torch Vision, the documentation, many of the pre-trained models are pre-trained on ImageNet. So if we look up ImageNet, here we go. So all pre-trained models expect input images normalized in the same way. So that means they'll be normalized in this way. And again, this is with the PyTorch documentation Torch Vision 0.12. This documentation will change slightly when you get to 0.13 onwards, which is, if I go to the unstable version, this is 0.14 onwards. But with, do we have 0.13? No, it's not going to show up, is it? Models and pre-trained weights, maybe it will in here. 0.13. Yeah, there we go. So this is what I'm talking about. As of version 0.13 onwards, there's a way to automatically create transforms. So the reason why I'm showing you the manual version as well as the automatic version is so you're familiar with both ways. The manual version will just give you more flexibility, but it has the downside of potentially mistransforming your images if you're creating them by yourself. But let's just start off with the manual version. I'm going to copy this normalization transform. What that is going to do is make sure our images have the same distribution, in other words, mean and standard deviation, as the pre-trained model. The pre-trained model is trained on ImageNet, so the same data distribution as ImageNet, and this is how that distribution was found. So let's jump into here. We will go set up ImageNet normalization levels. We'll go normalize equals that, and see here. So just beware if you're using Torch Vision 0.12 or onwards or 0.13 onwards, the documentation might be slightly different. So just keep that in mind. The principles still remain. So create transform pipeline manually. So what I'm going to do is from Torch Vision, import transforms. We'll go manual. I didn't need to re-import it. We've already imported it. I'm just making sure you know where it's coming from. Transforms.compose. And then we're going to fill this in with transforms.resize. And then I'm going to, by default, resize things to 224, 224. Transforms.toTensor. That's going to make sure all of our images are in the range of 0 to 1. And then we will normalize them there. So this pipeline, resize, in line with what it's saying here. Height and width are expected to be at least 224, 224, loaded into a range of 0, 1, and then normalized using these values here, which is what we've got there. Wonderful. Let's keep pushing forward. So let's get a printout of our transforms. So let's go manually, created transforms. And now, of course, if we wanted to add more transforms in here, such as different forms of data augmentation, we definitely could do that. So that's the benefit of creating our own transforms pipeline. Now let's create some data loaders. We can do that with train data loader, or actually, I'll just show you here. From going modular, this is the power of reusing our code that we've written before. Import data setup. So if we go over into going modular, we have a little Python file here called data setup. And inside there, we've got create data loaders. So this is going to help us create a data set using the image folder method from PyTorch datasets. And then it's going to return a train and test data loader. So we've written that code before, but the benefit of using our own script is that we don't have to rewrite everything over and over again. We can just import it and use it here. So I'm going to go data setup.create data loaders here. And then I'm going to pass it in a train dir, which will be what? It'll be our training directory above, training directory up here. Then I'll pass in the tester, which will be tester. And then I'll pass in the transform, which will be the manual transforms. This is going to perform the same transform on the training and test data set. An enhancement to our datasetup.py create data loaders function would be have a different transform for training and test. So you could go test transform would be transforms.compose, and then you could change that down here to have data loader, or sorry, here, test data would use the test transform. So that's one enhancement we could do if we wanted to perform different transforms on each split. So that should still be fine. And we'll set our batch size to a default of 32. So let's see how this goes. Train data loader, test data loader, class names. Beautiful. So there's our manually created transforms pipeline. We can compare this to the automatic one we'll create in the next video. And there's our class names, pizza, steak, and sushi. Wonderful. So let's in the next video create some transforms automatically. You might want to give that a go yourself because we've done this before in the previous section, creating a transform for torchvision.models auto creation. So since we're going to be running multiple different model experiments, we're going to be using EfficientNet B0 as one of them. So give it a go, practice creating an automatic transform, just like we've done in section 6, 2.2, but do it for this notebook here. And then we'll do that together in the next video. I'll see you there. Alrighty, in the last video, I issued you the challenge to 2.2, create data loaders using automatically created transforms. And we'll put here, the same principle applies for automatic transforms. We want our custom data in the same format as a pre-trained model was trained on. Now, this will ensure we get the best performance possible. So if we jump into the documentation here, I'm going to go to the latest version, currently unstable. Your version may be stable, but just make sure it's version 0.13 onwards. We go into models and pre-trained weights, and this is the new multi-weight support API. So if we look into here, there's now a way to make transforms. Yeah, here we go, beautiful. So we can initialize the transforms required to use a certain pre-trained model from the weights of that pre-trained model. So say we wanted to use ResNet 50, which is a computer vision architecture. We could get its weights and the default weights. Recall that default means best. And in fact, this is some of your extra curriculum here is to make sure you read through the Torch Vision documentation, especially the models and pre-trained weights section, because it's so valuable for transfer learning. And then if we take those weights, we can call the transforms method on the weights and then use those transforms to pre-process an image. So let's see this in action. If we go to classification, we've got a whole bunch of different model options here. We're going to use EfficientNet because we've seen it work quite well in the past. And we're going to stick with EfficientNet B0. And we want, there we go, Torch Vision Models EfficientNet B0 weights. So let's see this in action. We'll come back to the notebook. And we did this in this section, so you might have already given this a go. And if you did, I applaud you. Otherwise, let's practice together. Equals, we don't need to recreate this. We're just doing it for completeness. So both of these cells are complete on their own. Equals image path / test. Now, here's our step that's a little bit different. Is we're going to set up the pre-trained weights. So there are plenty of these weights available in Torch Vision models, and now it needs to be version 0.13 plus. That's why we spent some time up here installing the latest versions of Torch Vision. Your Google Colab instance might already have them by default. So let's jump back down here. So we can come into here. If we wanted to select a different model, we could try it. The process is going to be very similar regardless of the pre-trained model you use. We've got a bunch of them here. And we've also discussed that oftentimes you want the best trade-off between performance, accuracy level, and number of parameters. And EfficientNet offers a pretty good balance there. So pretty good performance, accuracy with a lower number of parameters. So we'll jump back into EfficientNet B0 weights, and then we can get this and copy that. We'll come back to here. So from Torch Vision, import models. We didn't necessarily need to do that. We could just go import Torch Vision actually, import Torch Vision. I just want you to be able to see where all of these things are coming from. So let's set up our weights. Is going to be torchvision.model. I copied this for a reason because sometimes you have to get the cases correct, otherwise you'll get errors. So we're just copying that down there. And then I'm going to call .default, which means default is the same as best available. So the beautiful thing about the updated version of the PyTorch Torch Vision multi-weight API is that if these weights ever get updated, so PyTorch train a new recipe of EfficientNet B0, or in fact any of the other models in torchvision.models, we can use the updated version of the weights. So if these get better, that means we get to use those improvements. So let's keep pushing forward. We'll get the transforms from weights. So these are the transforms used to train a particular or obtain a particular set of weights. So pre-trained weights, pre-trained patterns, depending on the model architecture. So automatic transforms equals weights dot, we'll call the transforms method. So we're getting some pre-trained weights here for EfficientNet B0, the default ones, the best available, and we're getting the transforms that we need that were used to create these weights. Why? Because we want our custom data, if we're going to be using transfer learning, we want our custom data to be in the same format as the pre-trained models we're trained on. So we'll go test data loader. Now we're going to create the data loaders. We're going a little bit faster pace this time because we have covered this material before, but nothing like a little bit of practice. So trained-er equals our trained-er. Our tester equals tester. And we could do a little printout, actually. I might do that as well. So our transforms is going to be the automatic transforms, and our batch size is going to be the ever-reliable 32. You could, of course, customize these settings. Let's print out. Oh. This is meant to be an F string. So we'll go here. Automatically created transforms. This will be our automatic transforms. Automatic underscore transforms. Beautiful. And then we will have a look at here. Train data loader, test data loader, class names. Let's see what's going on. Oh, what did we get? A little typo. Did you notice that? We had triander. Wonderful. And we see that our automatically created transforms are basically the same as our manually created transforms. The only difference here is that for manual creation, you have a bit more flexibility in how you create them, so you could add some more steps in here if you wanted to. However, you just have to make sure they're not too different from the pre-trained model that we'd like to use. Otherwise, there might be some performance degradation. The benefit of using automatically created transforms based on the model weights you'd like to use is that, well, they were used for that model weight. So you know that if your data goes through here, that it will be in the same format as what this model was trained on. So with that being said, speaking of getting pre-trained models, how about in the next video, we get a pre-trained model, we freeze the base layers, and we change the classifier head to suit our problem. In fact, we've already done this in Section 6, PyTorch Transfer Learning. Section 3. So I'd encourage you to go through here, try to get an efficient net B0, freeze all of its base layers, and change the classifier head to suit our own problem. Give that a go, and I'll see you in the next video. We'll try it out together. Let's now get a pre-trained model. So getting a pre-trained model, we'll freeze the base layers and change the classifier head. So you may have already done this or given it a shot because we covered it in the last section, getting a pre-trained model, but let's now do it together. So I just want to show you the old way of doing things because you might see this in other old PyTorch sort of demos and whatnot. So note, this is how a pre-trained model would be created prior to Torch Vision v0.13. So we would go model equals torchvision.models.efficientNet, let's say efficientNet b0, our old faithful, pre-trained equals true. And then we could send that to the target device if we wanted to. And then if we had a look at the model, it's going to download a model. It's going to work, but it gives us this little warning message. So let's scroll up here. If we go up, yeah, user warning. The parameter pre-trained, which is this, is deprecated since 0.13. There we go. And will be removed in 0.15. Please use wait instead. So let's see what the new version looks like. And just remember, I'm just showing you that because it's good to be aware that this is a pretty major change in terms of how PyTorch pre-trained models are created. So it's good to be aware of how they were created. So download the pre-trained weights for EfficientNet. So this is using the new version, so 0.13 onwards. EfficientNet b0. So we saw this before. Weights equals torchvision.models.efficient, I have to spell these things out, EfficientNet b0 underscore weights dot default. So just a reminder, default equals best available weights. And if we wanted more of them, some models have multiple different types of weights. This is in the documentation. You just have to make sure you're on the version 0.13 onwards. So for me at the moment, this is the nightly version. And then if I go to models and pre-trained weights, classification, we've got a bunch of different model weights here that we could try, each with varying results on ImageNet and each with varying numbers of parameters. So that's where you can find pre-trained models in PyTorch. Don't forget, there's also other places such as the Hugging Face Hub. We have weights equals torchvision.models, EfficientNet b0 weights default, the best available for EfficientNet b0. Now, to create a new model, this is the new way. Set up the model with the pre-trained weights and send it to the target device. So just as we've done above in the line that's commented out, this is how we would create that same model, but using the new API. .models, EfficientNet, b0, and then in here we're going to do weights equals weights, and then we have a look at our model. Beautiful, we get the same model here. So using that weights, and just a little tidbit, make sure this says weights, not weight, because I've been caught out on an error for quite a long time with the wrong parameter name in there. So I'm going to comment that out to save some space. Now, let's freeze all of the base layers in this EfficientNet b0. So if we go have a look, before we freeze them, freeze all base layers by setting their requires grad. So PyTorch, requires grad attribute to false. So PyTorch will automatically behind the scenes track the gradients of our model parameters. And if we wanted to update them and have them better represent our data, our optimizer would update that gradient as our model looks at data. So if we set the requires grad parameter to false, requires grad equals false, it's going to freeze them during training, so they won't have any gradients to track. So let's just print the param. We're going to see quite a few things here. Yeah, there we go. So these are all the pre-trained features that our model comes with. So these are all learned from ImageNet. We've got a whole bunch of different things, all numbers, numericals, numerical patterns, representing what our model has learned on ImageNet. And as we've seen in 0.6 or 0.6, that it turns out that these are actually pretty good patterns in terms of computer vision. So let's comment that out. We'll set all the parameters requires grad to false, and then we will change the classifier head. So we might just do that in the next cell, equals false. Beautiful. And if we inspect our model, so model.classifier, some models will have a different head on them. So if we inspect our model one more time, we've got a few components here. We've got the features component. This is for EfficientNet. We come down, all the way down. Look at all those layers that we get to use. Average pool and classifier. So some models may call this a different name. You just have to be aware of how to inspect it. So for us, it's the classifier head, but the principle is very similar across different model types, is you want to adjust the output layer, whether it's a classifier head or something else, you want to adjust the output layer to suit your own problem. And for us, instead of having 1,000 out features, we want 3. So adjust the classifier head. We want nn.sequential. We're just going to reproduce it just the exact same, but with our number of classes. We want 3. So I'll bring in dropout and p equals 0.2. In place equals true. Just going to copy exactly what's there. And then we'll go nn.linear. The in features is going to be 1280. That's going to be a feature vector of our whatever image is going through the network. And we'll change this to 3 or len class names, which will also be 3. Beautiful. So let's adjust the classifier head. We might also send that to the target device, and we might set the seeds here because this is going to instantiate a linear layer, and behind the scenes, the weights of this layer are going to be initialized randomly. So for as much reproducibility as we can get, we'll set the seeds, we'll send it to the target device because this is a part of our model. And when we downloaded the model, we didn't actually send that to the device either. I've written it there, but maybe I didn't do it. So maybe you caught that error, but we'll just rerun all of those cells. And now we can use Torch info to get a summary of our model to check out what's going on. So from Torch info, import summary. And so let's get a summary of our model, and we'll put the input size. Let's set this just to a batch of 32. 3 color channels, 224, 224 for height and width. That's going to be our image data. Verbose equals 0. We'll get a big printout. Col names. We can set up some col names here. So we want to see the input size and output size of each of our layers. That's a very important thing to inspect in deep learning models is input and output shapes. We'll check out the number of parameters each layer has, and we'll see whether the layer is trainable or not. And then we'll just set some values here for aesthetics, column width to 20, and row settings. Let's print out the var names. So let's see what this looks like. Wonderful. So this is what we covered in the last section. We've got an EfficientNet, and we've got our features section here, which is comprised of multiple different groups of layers and some activations here. We've got input and output shape of each layer, and you can see our image data gets manipulated as it goes through the network. And each layer has a certain number of parameters. And right now, all of the base layers are frozen, so they won't be updated during training. So we have a feature extractor model here. And we have updated the classifier layer to suit our own problem of only having 3 output units. And so that is the only layer that is trainable. So hopefully training goes pretty quick. As we saw in the previous section, we have just under 4,000 trainable parameters. And if we want to see that in the colored version, we go back to the keynote. Here's what we've got. Torch Vision models EfficientNet B0. Many of our layers are untrainable. In other words, they're frozen. Only our last layers are trainable. And we've updated the final layer to suit our own problem. If you had 10 classes, what would this value be? It would be 10. And now, because we've set a lot of the layers to be untrainable, our trainable parameters is greatly reduced. So therefore, the number of calculations that PyTorch code will have to make behind the scenes is greatly reduced. So training speed is hopefully reduced as well. So let's go back. It's now time to train a model. But this time, instead of tracking our model's results in a dictionary like we have been, we're going to save them to a file. So you might want to have a look. This is, if you want to go ahead, a challenge for you is use TensorBoard with PyTorch. If you search that, we've got a tutorial here. Beautiful. You might want to go through that and see if you can figure out how to use TensorBoard with the code that we have here. Otherwise, we'll cover that in the next video. I'll see you there.